Bahadır abi bir şey yazmış bana.
Hocam, should we start on time or wait a few more minutes for more participants to take?
I think we still have 2 minutes, 2 more minutes. We can wait. Ibrahim Hocam, you will start to announce the first 2 speakers, and then I will announce the last one.
Sergey geldi. Nerede? Geldi ama katılamadım mı? Ha. Welcome, Sergey.
Welcome, Ekrem.
How are you today?
Very good, very good. Ready for.
Nice to meet you.
Yeah. Thank you.
Thank you very much. You accepted our invitation.
Where is my video? I don't see it.
You are co-host. You can open your video.
Yeah. Strange. It was away.
Ibrahim, your sound is very low. You please check your sound.
It's time. Shall we start or shall we wait a few more minutes for more people to come in? Can't you hear me? Ekrem hocam?
Yes, I hear, but still your sound is low.
To me, it's okay right now.
Yeah, maybe your
yes,
your speaker is turned down, maybe.
Yeah, I mean,
Mithat says it's okay with me.
It's very good.
Different?
Now it's low.
Okay.
Before it was better.
I plugged in myself.
Yeah.
Okay, maybe I should start with the introduction and we'll see. Is that okay, Ekrem?
Yes, we can start.
Okay. Yes, our first speaker is Eric Train from Monash University in Australia. He received his PhD in University of Washington, and he's working on cosmology, astrophysics, and gravitational waves. In particular, analysis of data from gravitational wave observatories. Phenomena he is interested include formation of compact binaries, fate of massive stars, and in connection with that, properties of matter at extremely high densities. He's a data team leader for OSGRAV, the Australian Center for Gravitational Waves, member of the LIGO collaboration, and author of 300 plus papers. We are fortunate to have him as a speaker on this day. And please, Professor Train.
Thank you very much, Ibrahim, for the nice introduction. And thank you to the organizers for inviting me here to speak today. The title of my talk is The Population of Merging Compact Binaries Inferred Using Gravitational Waves Through GWTC3, or the Third Gravitational Wave Transient Catalog. And I'm giving this talk on behalf of the LIGO, Virgo, and COGRA collaboration. The bulk of my talk today is going to cover results in a paper which has the same title as my talk. The archive identifier, if you're interested, is here. And if there's a little bit of extra time, depending on how my pacing is, I'll maybe throw in a couple results from another paper as well at the end. So before we get into the results from this paper, I'll just give a brief review of gravitational wave astronomy, which really got started as a discipline in 2015 with the very first detection of gravitational waves from GW 1509-14, a binary black hole system that emitted gravitational waves in 2015, the 9th month of that year, on the 14th day of that month. And here is a plot from the discovery paper, which has become iconic in astrophysics, showing the gravitational wave strain in our LIGO Hanford detector in the northwestern part of the United States, and the LIGO Livingston detector in the southeast part of the United States, separated in time by just a couple milliseconds and matching very precisely the predictions of what a gravitational wave signal ought to look like from a binary black hole merger according to general relativity. Since this Nobel Prize winning discovery, we've continued to detect gravitational waves, so that at present there are 90 candidate events, 90 candidate gravitational wave events with a p-astro value of at least 50%. And by this, we mean that the probability that the LIGO-Virgo-Kagra collaboration assigns to this event being a genuine astrophysical event is at least 50%. And as these events are collected, we publish them in catalogs, which get numbers as the catalog is updated. So we're currently on the third catalog, which is GWTC3, or Gravitational Wave Transient Catalog 3. This is a visualization of all of the gravitational wave signals in our catalog, and also just everything we know about compact objects, black holes and neutron stars. So there's a lot going on this plot. Let's start up at the top with the blue circles. So the vertical axis on this graphic is the mass of different compact objects. And the blue circles represent black holes that have been seen merging with LIGO, Virgo, Kagra. And you'll see that they're to make a 100 solar mass black hole. And in addition to these blue black holes that we know about from gravitational wave astronomy, of which there are about 80 or so, there are these red black holes on the side as well. And these are black holes that we know about from electromagnetic astronomy, and these in particular from X-ray astronomy. And these black holes are local black holes in our Milky Way galaxy. And one thing that is quite striking when you look at this graphic, comparing the black holes that we've observed from gravitational wave astronomy with the black holes in our own Milky Way galaxy that we know about from X-ray astronomy, is the significant disparity in mass. The black holes we knew about prior to the advent of gravitational wave astronomy were typically 10, 15 solar masses, maybe up to 20 solar masses. But the black holes that we're probing with gravitational wave astronomy include masses that are much higher than that. Let's turn our attention now toward the bottom of the graphic, where the neutron stars live at about 1.5 to 2.5 solar masses. The vast majority of neutron stars that we know about are known from radio astronomy. These are pulsars, but we also have a handful that we've observed in gravitational waves, and these come in two varieties. First, there are double neutron stars or binary neutron star mergers, like this one. Hopefully you can see my arrow here. These are two neutron stars that merged together and made something here. It's color-coded as half orange, half blue. And that's because we don't know for sure if this created a very light black hole or a very massive neutron star, probably a black hole though. We also have neutron star black hole binaries, where a neutron star merged with a black hole to make another black hole. And this region here between 2.5 and 5 solar masses is labeled mass gap, ? And that's because somewhere in here is the transition region where black stars, collapsing stars, stop making neutron stars and start making black holes. And it's thought that from theoretical reasons that there might be a sort of a dearth of compact objects here. So there are a lot of compact objects on that previous graphic. And so in order to sort of set the stage for the analysis that follows, I'm going to go through these 90 detections. Don't worry, not all one by one, but just give you a highlight reel of some of the most exciting discoveries, starting with the one that kicked it all off, GW150914. This event is famous not only because it was the first gravitational wave detection, but it was also the first observation of a binary black hole system. And as I mentioned, most black holes that we knew about previously, stellar mass black holes at least, were very light compared to this one. This one had component masses of 30 solar masses, roughly, which made this system unlike the black holes that we know about in the Milky Way. The next iconic event occurred in 2017. This is GW170817, which was the detection of gravitational waves from a binary neutron star. And this event is arguably the most studied astronomical transient ever in astronomy. The gravitational wave signal was coincident with a gamma ray burst and kilonova. And there was a huge amount of science that came out of this discovery, including the confirmation of the connection between short gamma rays and binary neutron star mergers, as well as exquisite limits on the speed of gravity, among many other discoveries. While I bet most of you are already familiar with those two events, you may not be familiar with GW 190521. This was a discovery in 2019 of a binary black hole merger with a total mass of 150 times the mass of our sun. And this event was quite interesting because the two black holes that are in this binary are so massive that it's difficult to see how they could have evolved through normal stellar evolution. Most massive stars, as I will describe in greater detail later, stars big enough to make black holes like this ought to explode in something called a parent stability supernova, leaving behind no remnant whatsoever. Shortly after 1905-21 came GW 1908-14, which was an extremely interesting object. This was a binary merger with a 2.6 solar mass compact object. This was the secondary, or the lighter, of the two black holes in the binary. But at 2.6 solar masses, we can't be sure that this secondary object was a black hole or a neutron star, because if it's a black hole, this would make it by far the least massive black hole known to science. And if it's a neutron star, it would make it by a lot the most massive neutron star known. So that's quite interesting. But the binary is also interesting because of its mass ratio, which is defined as the secondary mass divided by the primary mass. And we measured this with gravitational waves to be about 0.1. And it turns out that very massive stars that are the progenitors for black holes and neutron stars tend to be in binaries with other very massive stars of about the same mass. And so they tend, we think, from astrophysics theory, to make binary systems with roughly comparable mass compact objects. And so the huge disparity in mass between the primary and secondary object in this binary make it very interesting for that reason as well. Finally, and most recently, GW 2001-05 and GW 2001-15 were discovered. And this was a pair of neutron star black hole mergers. And the discovery of these two events completed the sort of possible gravitational wave signals that one can see with merging binaries. We had the black holes, the binary neutrons, and with these two recent discoveries, neutron star black hole mergers. Now, all of the events that I highlighted for you in that highlight are interesting because of the masses that we measure them to have. So how do we in the LIGO-Verhaeghe collaboration work out the properties of these binaries? It turns out that compact binaries have 15 parameters that describe them. These include the masses of the two compact objects, but black holes, in addition to having mass, have spins. So there's each black hole gets a spin vector, which has a magnitude and a direction. And then there are parameters describing where the binary is on the sky and how it's oriented with respect to Earth. Changing the different parameters of the binary changes the gravitational waves that we see in our detectors. So for example, let's put a binary black hole out there in space somewhere, and let's fix all of the parameters to be constant, except the masses. Let's change the masses and see what happens to the gravitational waves that we see in our detector. Well, as we increase the masses of this binary so that they become larger, the gravitational wave signal that we see in our detector is going to become shorter and have more low frequency content in it. And then if we now turn the knob the other way and make these black holes less massive, it will make a relatively longer signal with higher frequency content. So by measuring things like the duration of the signal and the amount of frequency content we can, low versus high, we can sort of get a handle on the masses. The spins of the black holes can also leave an imprint on the gravitational waveform. And it's a little bit more subtle than the mass, but let's just take one of the spin degrees of freedom to be concrete. And let's look at the component of the black hole spins. Hopefully you can see my hands here because I'm gesturing. The component of the black hole spins, which are pointed upward in the same direction as the orbital angular momentum of the binary. So here's the orbital angular momentum, here's the black hole spins. Everything's pointing in the same direction. if the two black holes are spinning quite rapidly in the same direction as the orbital angular momentum, this leads to something called the orbital hang-up effect. In essence, the two black holes resist each other. Their spins kind of push them apart and slow the speed at which the binary merges. This causes the binary to merge at a higher frequency than it would otherwise, spending more time in our observing band than it would otherwise. So in order to work out these properties of the binary, the spins, the masses, how far away it is, we take our data, which is represented here, and we plug it into a Bayesian inference pipeline represented here by the Reverend Thomas Bayes. And what this pipeline does is it compares templates or predictions from general relativity to our data and does this for many different combinations of parameters in order to yield output that look like this plot here. This is a corner, what's called the corner plot. And in this example, this is from the famous the first GW150914 paper, we're able to obtain constraints on the parameters of the binary like this one. Here we're looking at the primary mass and the secondary mass of the black holes in GW150914. In this particular case, we can constrain the primary mass to be about 35 times the mass of the sun, and the secondary is about 30 solar masses. Once we've measured the masses, spins, redshifts of all of the binary systems in our data set, one of the next things that we do is we try to look at the data set as a whole in order to say what it all means when taken together. And in order to do this, we attempt to reconstruct the distribution of black hole mass, spin, and redshift, the population properties of these quantities. The information encoded in these distributions tells us really interesting things, like what are the stellar progenitors that form black holes, and how and where in the universe do binary black holes get assembled? In order to help explain how we extract that information from these distributions, it's useful to just look at a single example. So I'm going to start off by talking about primary black hole mass, and we're going to pretend that we are workshopping this together on the whiteboard. And our first step is going to be to just draw a whiteboard. Well, what do we think? If you had to guess before you looked at any measurements of binary black holes, what would you guess the distribution of primary black hole mass would look like? So this is a investigation my PhD student and I did in 2018, Colum Talbot. Here is our basic whiteboard drawing that we came up with. Let me walk you through it. So the first thing that we did is we drew a power law. We drew a power law because black holes are formed from stars, and the stellar mass distribution is a power law. There are many more low mass stars than there are high mass stars. So a reasonable place to start, at least a first guess for what you might think the primary black hole mass distribution might look like, is to assume there's some sort of power law inherited from the stars that create black holes. But this power law can't continue indefinitely to arbitrarily low masses, because we know that somewhere out there in the universe is a minimum black hole mass. We know that if the mass of a progenitor star gets to be too small, it collapses to form a neutron star. So somewhere there has to be some minimum mass. So we're going to put a cutoff in here. But now I also believe that nature abhors sharp edges. So it seems improbable to me that there's a really very sudden cutoff going from a power law to the minimum black hole mass. And so in my whiteboard drawing, I'm going to round off the edge here and guess that maybe there's some smoothing function, so that, for example, a 4 solar mass black hole is possible, but probably pretty rare compared to a 7 solar mass black hole. Now let's turn our attention to the high end of the black hole, the high mass end of this mass distribution. Now, just like we believe the power law can't continue to arbitrarily low masses, we also, the power law can't continue to arbitrarily high masses. It has to cut off, we think, and there might also be a bump. The reason for this cutoff and possible bump is due to something called pair instability physics. So we're going to pivot away from our whiteboard drawing in order to talk about pair instability supernova, or why there's a cutoff in the black hole mass distribution. This comes from astrophysics theory, or stellar theory, which tells us that some of the most massive stars, weighing more than 80 solar masses, zero age mean sequence, become so hot in their cores that they produce electron-positron pairs. These pairs take energy and kinetic energy out of the core of the star, which causes the core to contract, which causes from the drop in pressure. But then the contraction causes the star to heat up, which causes more positron-electron pair production, ultimately leading to a runaway process. And if the star weighs more than 130 solar masses when it's born, this process cannot be quenched. And it's believed that the star is completely disrupted in what's called a pair instability supernova. It explodes and it leaves behind absolutely no black hole at all. So if you pack matter onto a star trying to make the biggest black hole in the universe, you'll fail and the star will just blow up instead. On the other hand, if the star is a little bit less massive, say between 80 and 130 solar masses, zero age mean sequence, then you still get this pair production. But what happens is that star, when the runaway process begins, you get what's called a pulsational pair instability supernova. And tens of solar masses of stellar envelope are ejected and shot out of the star. And this relieves the pressure on the core and prevents a complete runaway process. So pulsational pair instability supernova is that stars that are born between 80 and 130 solar masses ought to shed mass throughout their life so that they end up behaving as though they were born at only 80 solar masses. They make a black hole, but still the black hole they make is less massive than you might have naively guessed it ought to be. If we combine both of these ideas together, pair instability supernova and pulsational pair instability supernova, we get the prediction that there ought to be a cutoff in the black hole mass spectrum at about 40 solar masses, and maybe a bump from all of these binaries that get shifted into the sort of 80 solar mass star range. Now, you might be wondering, well, if this process becomes relevant at 80 solar masses, why is the cutoff not at 80 solar masses? Why is it at 40 solar masses? And the reason is that even if you don't have pair instability and pulsational pair instability supernova, stars that are this massive lose about half of their mass during their lifetimes through stellar winds. So an 80 solar star to leave behind a remnant of about 40 solar masses. Now, while I said all of this with a lot of hopefully confidence, this is currently a theoretical idea. It is a theoretical idea that stellar theorists hold dearly and think is true, but there is currently, as far as I'm aware, not an unambiguous electromagnetic detection that everyone agrees is a pair instability supernova or a pulsational pair instability supernova. Okay, so let's go back to the whiteboard. We've now justified in our drawing, our prediction, that there ought to be maybe a cutoff here and a bump. So now that we have a whiteboard drawing or a model, what's going to turn into a model for what the distribution, what we think it ought to look like, the next step is to turn this into something that we can compare to the data. And we do that by introducing parameters. So the first parameter we introduce is an index, alpha, which describes the shape of this power law. We parameterize it. We say that the minimum black hole mass is a free parameter. The turn-on length is a free parameter. The location of the maximum black hole mass is a free parameter, and the location, height, and width of this peak is a free parameter, and so on. And then by fitting these parameters, we can see if the data support the existence of a peak like this. If so, where do the data want to put it? How sharp is this turn-on length, etc. The model that I showed you on the previous slide is an example of what's called parameter. In this case, the parameter is the black hole primary mass, and the hyperparameters are all those knobs that control the shape of that distribution. In a couple of slides, we will apply this specific model to GWTC3 data, and I'll show you what we learned from it. We do a combination of models. The one that I just showed you is an example of an astrophysics. I to employ models that are minimal assumptions. So things like histograms, in order to make sure that we're not, as best as possible, not seeing things in the data because we believe so strongly that they ought to be there a priori. And where possible, we also try to use different kinds of parameterizations to minimize the model dependence of our results, though this is quite hard. All right, so now that I've described to you the sort of machinery of what we are going to be applying to the data in order to learn about the populations of black holes and neutron stars, I'll tell you about a little bit more about the data itself. We are going to take a subset of the events in gravitational wave transient catalog 3, looking only at the most confident events that were observed through all of the current observing runs. And this is 76 out of the 90 I mentioned earlier. And all of these will have a false alarm rate of less than 1 per year. So we can be pretty confident that there's minimal contamination. There are 5 events that I'll not be talking about today. I won't be talking about in the subsequent slides, the 2 binary neutron star events that we've seen and the 3 neutron star black hole candidates, one of which I suspect is a binary black hole. And that's because I want to focus my time on these 71 binary black hole candidates with component masses ranging from 5 to 91 solar masses. I'm doing this because of time constraints, but also because with 71 events, there's a much bigger population here to analyze, and it's hard to say that much with only a few events of these other populations. I also want to highlight that there are other gravitational wave candidates that have been identified by groups working outside of LIGO, Virgo, Kagra, and I will not be, these are not part of the LVK analysis, but I want to highlight that these other catalogs by Nitz et al. And Zakeh et al. Also exist. All right, so without further ado, let's take a look at the results. Start with the distribution of binary black hole masses. We see a number of very interesting things. The first thing we find is that there is a term low masses. So here we're looking at the merger rate density as a function of primary black hole mass. And we see that if you're reading from left to right, it shoots up at 10 and turns on. This is the reason that the way we're able to infer this is that we do see binary black holes merging here, and we can get some idea of what the slope of this, this distribution is. And if we extrapolate it up to lower masses, around 5 solar masses, we should be seeing way more of these events. And the fact that we aren't seeing them must mean that this turns over quite sharply. The fact that it turns over at 10 solar masses and with the rising time that it does is telling us something about supernova physics, and presumably about the efficiency with which the massive stars on the, maybe let's say 10, 15, 20 solar masses at 0 age mean sequence, the efficiency with which they can make black holes, and when that process stops working effectively. The second jumps out at us, and we see both of these, I should say, with very high statistical significance, is this bump at about 34 solar masses. And this is quite interesting because, as I described before, one might expect a bump at about 35 solar masses from pair instability physics. And so it may well be that we are seeing some pileup here from pulsational pair instability supernova. That said, the interpretation of this feature is currently quite uncertain because the way that black holes have the path by which they get the final mass they get is complicated. They evolve from stars, which lose mass through winds. They can interact in binary systems. And so this bump may be due to some other physics as well. But it is quite curious and interesting that it does happen at this pair instability mass scale, even though the parameters allow it to are free to be able to put this bump anywhere. The third thing I want to talk about with this plot is not something that we observe, but something we don't observe. And keen viewers of the talk may have already picked up on what it is. We do not see the pair instability gap the way that we thought we would before we started finding binary black holes. So recall, there ought to not be really massive black holes at above, let's say, 80 solar masses. There just shouldn't be black holes here. This is the pair instability gap. We don't know exactly where this gap ought to be from theory, but stellar modelers tell us it should end at about 130 solar masses and it should begin at about 40 to 70 solar masses. But events like GW 190521, these are two black holes, one of them is at least 75 solar masses. And there are other events like 190521 that are even edging even further here. And so the fact that this distribution doesn't seem to cut off, that it just continues into this, bleeding into this mass gap is a really interesting observation and a bit of a problem requiring an explanation in astrophysics. So why are there black holes in the mass gap? I think that there are two plausible sounding explanations that I'm familiar with. One is that there are just fundamental problems with our understanding of massive stars. And while stellar astrophysics, it's considered to be very solid, the idea of pair instability supernova, maybe there's just something we don't know. I think we have to be open to that possibility. But this is a less interesting possibility to contemplate for me, a gravitational wave observer, because there's not a lot I, as an observer, can do to address that hypothesis. So I want to talk about a different hypothesis, which I think is another compelling explanation for the black holes in the mass gap and is one that has observational signatures for astronomers. This is the idea of hierarchical mergers. The idea of hierarchical is that there are different generations of black holes. First, or 1G black holes are formed directly from stars. So most of the binary black hole mergers that take place in the universe ought to be these 1G plus 1G mergers. However, you can have two 1G black holes merge, and these certainly do create second generation black holes. Now, suppose these second generation black holes are able to merge again. Now you could have a 2G plus 1G merger. Or suppose you have four 1G black holes, they merge making two 2G black holes, and then you have a merger of two second generation black holes. If this happens with enough regularity in the universe, then this could explain how these first generation black holes could be 40 solar masses. They could make approximately 80 solar mass second generation black holes. And if events like GW 190521 are 2G, that would explain why they are in the mass gap. The idea of hierarchical mergers is something that was proposed prior to the discovery of events like GW 190521. So this is not a new idea. It is thought that hierarchical mergers might take place in dense stellar environments like globular clusters or active galactic nuclei through a process called dynamical assembly. So you can visualize these dense stellar environments as like clouds of interacting particles, where the particles in these clouds are stars and black holes. So in this cloud of this gas of stars and black holes, the heavy stuff tends to sink into the bottom of the potential well, and the lighter particles get flung to the exterior. And in that center of the potential well, interactions between particles, black holes, can harden binaries so that they merge, and then sometimes the merger remnants could potentially merge again. So in order to give you a visual understanding of what we're talking about, I have here a numerical simulation. I got this from Mike Zevin's webpage. So we just saw a binary interaction, and you can imagine that these were two black hole binaries inside one of these dense stellar environments. And you started out with 4 black holes, but then when they interacted with each other, one of the black holes got shot off, and this hardened the remaining triple systems, that now these black holes are much closer together than any of the original 4 black holes were to each other. And now we have chaotic motion in this triple system. And in a moment, one of these black holes there had just happened is going to get kicked off. And so now we just have a single binary, and a lot of angular momentum has been carried away by the ejection of those 2 other black holes. So much so that this binary is just going to merge essentially right away in real live time for us there, making gravitational waves. And now we have a 2G black hole. And if that 2G black hole doesn't get ejected from this dense stellar environment, it might blunder into another binary and eject one of the black holes from that binary, and then get subsequently hardened and before merging again. If this is happening, in order to make some of the most massive LVK binary black holes, then we should be able to test this in the not so distant future. All second generation black holes possess fairly large dimensionless spins. So this thing chi here is the dimensionless black hole spin. It can range between 0, which means not spinning, up to 1, which means a maximally spinning relativity. And since second generation black holes are created from the a binary system, they inherit a lot of angular momentum from that binary motion of the progenitor system. And so almost all these systems have fairly large spins of about 0.7. Moreover, the orientations of these spin vectors are random isotropic. So here is our orbital angular momentum. Here are 2 black holes. The spin vectors are chi1 and chi2. And these, I'm now gesturing with my hands if you're following along. These 2 spin vectors can point any which way. And if they point into this orbital plane, then this causes the binary to undergo orbital precession. So basically the orbital angular momentum vector pivots around while the spin vectors pivot around. And since more gravitational waves are emitted in the direction of the orbital angular momentum than are emitted in the direction of the orbital plane, if this precession is very strong and it causes the orbital plane to pivot around wildly, this causes a pretty clear signature in the gravitational waveform. So this is an example of gravitational wave strain as a function of time with rather extreme precession, and these modulations are due to precession. So if we could observe a really massive system in the mass gap that has precession, this would be a pretty good clue that we might be seeing a hierarchical binary. Speaking of spin, I think that transition to the next part of the talk, which is about this distribution of binary black hole spins. So I've already told you about one of the scenarios that we're looking for, and that's the dynamical scenario where we have 2 black holes wandering into each other at random with random spin orientations. This is actually sort of the less popular scenario. The conventional scenario is called the field scenario. And in the field scenario, the black holes are formed from a stellar binary. So you have 2 stars that are already in a binary. One star blows up, makes a black hole. The other star blows up and makes a black hole. And then those go on and merge. And the original binary was formed from a single cloud of gas. And since the black holes can interact, or one of the black holes can interact tidally with the second with the star, the other star in the binary, everything in the problem has a tendency to align all of these vectors so that the spin vector pointing in the same direction as the orbital angular momentum. However, supernova kicks can serve to misalign these black hole spin vectors a little bit, but probably not so much that they would be lying in the orbital plane. So like before, like we did with the mass distribution, we can concoct a model for what we think the distribution of physical black hole spin parameters ought to look like. Here, we're looking at the cosine of the black hole spin tilt. So a cos tilt of 1 means perfect alignment. A cos tilt of -1 means anti-alignment. If we think about the field model, this blue distribution would be what you might expect if supernova kicks are absolutely tiny. Everything is essentially perfectly aligned. This green distribution, on the other hand, is what you might expect from more modest supernova, or more reasonable supernova kicks. They're larger. And so we have some free parameter, sigma, that we have that allows this distribution to be peaked at cos tilt 1, but with some unknown width. We also allow, though, for there to be a contribution from the dynamical channel. And if the spin vectors are isotropic oriented, then that means that the cosine tilt is uniform. So we have a second parameter, zeta, which controls the fraction of the events in the catalog that are from this dynamical channel, which should be isotropic, or the field channel, which is highly peaked. We also need a model for the dimensionless spin magnitude chi, and for this we employ a beta distribution, which is convenient because it has two shaped parameters that allow us to achieve a wide range of distributions on a smooth distributions on the interval 0 to 1. However, the feature and drawback of particular parameterization is it's unimodal, going to become important in a couple of slides. While we frame our models often with these physical parameters, useful to visualize the data using this quantity, which is an effective parameter called chi effective. This is the effective in-spiral spin parameter. In essence, what this is it's the projection of the spin vectors, the black hole spin vectors, along the orbital angular momentum axis. And the reason that we use this in gravitational wave astronomy is because this is a constant of motion. But what matters for the next couple of plots I'm going to show, your rule of thumb is that if you have binary black holes forming in the field, you expect chi effective to always be greater than 0 because the spin tilts ought to be less than 90 degrees. Otherwise, this would imply enormous supernova kicks. On the other hand, dynamical formation allows for both negative chi effective and positive chi effective. And in fact, you need to get exactly equal proportions of negative and positive chi effective if the dynamical channel is the true one. So let's now look at our distribution of reconstructed chi effective using data from GWTC3. The first thing is that this distribution is not symmetric about chi effective equals 0. It's shifted to the right. And that means that alignment is more common than anti-alignment. And this shows quite convincingly, I think, that at least some binaries must be assembled in the field through the standard channel. This conclusion is supported by the fact that individual binaries, the ones we detect that have unambiguous imprints of black hole spin, are all measured with positive chi effective, whereas the ones that we see that show some hint of negative chi effective are more ambiguous. Also find that, however, that about 27% of the population has negative chi effective, where at least one black hole spin vector is tilted by more than 90 degrees with respect to the orbital angular momentum. And this would imply you can't get this through field evolution. And so this implies formation through this dynamical channel. However, other studies which have come out that are not written by LIGO Virgo Pagra one of them by Roulet et al. And the other led by my PhD student, Shanika, have reached different conclusions. Pardon me, because I'm now going to be defending two antagonistic positions at the same time, one for LVK, one for my PhD. In these other studies, it's been pointed out that maybe the reason that we fit this long tail here to negative chi-effective is because of what's called model misspecification. In essence, you're assuming a model that just is not a good fit to the data, is what these papers argue. So for example, it could be the case that there is a subpopulation of black holes with basically zero spin. And in fact, there's very good reason for believing that there might be such a subpopulation, because studies of angular momentum transport suggest that when a black hole is formed in the wild, most of the angular momentum in the progenitor star is probably in the outer envelope to get blown off during the supernova. So most black holes are probably born not spinning. Some are probably born spinning, but they probably have to, the progenitor system probably has to get spun up through, and that would happen in nature. If the true distribution is more like this green distribution, then this is a bimodal distribution. There's a peak here and there's a peak there. And if you try to fit both peaks, two peaks with one, it makes sense that you would get this tail extending out here. But the tail from that fit is not because there really are events with negative chi-effective. It's just because you're doing your best. Your algorithm's doing its best to fit something that it's just not well matched to. All right, just paying attention to the time. Okay, I think I have time for, yeah, I'll do redshift and then I'll skip ahead to my conclusions. The last thing I'll tell you about is our measurement of the redshift evolution of the binary black hole merger rate. So here we are now looking at the merger rate as a function of redshift. And with GWTC3, we can, for the first time, see this changing as a function of redshift, so that as you go further back in the history of the universe to higher redshifts, the merger rate goes up. This is quite exciting. It's not necessarily so surprising because as we see from this dashed curve, the star formation rate also is known to be higher in the past than it is today. And since black holes come from stars, it's not necessarily surprising that the merger rate in the past used to be higher than it is today. However, there's expected to be a delay time between when a black hole is formed and when it merges in a binary system. While the massive stars that make black holes don't live very long, the binaries, when you put two black holes together, it can take a very long time for that binary to decay all the way and so that it merges. And so we're able to measure this distribution more precisely. We should be able to start to learn about this delay time distribution and what the typical separation is of binary black holes when they are formed. I'm going to skip ahead to make sure I finish on time and leave time for questions, and conclude by saying we see clear mass spectrum that may point to either pair instability or supernova physics. Mass gap systems like GW1905-21 seem to suggest a possible dynamical origin for at least some of the LVK binaries. However, events with unambiguous positive chi-effective also imply that at least some of LIGO, Virgo, Kagra binaries must be assembled in the field. So maybe we have dynamical and field binaries. Teasing out signatures for negative chi-effective in the population has proven to be complicated and controversial. Some analyses find support for dynamical assembly by looking at the spin, others do not. And then we have events like GW1908-14, which are just a complete mystery. The fourth LVK observing run will begin later this year. And as we turn back on, we should continue to grow the catalog substantially over the coming years. And this ought to clarify some of the questions raised in my talk today. If binaries like GW1905-21 are assembled hierarchically, I do think we should start seeing unambiguous signals for precession sooner rather than later. And one of the interesting things that's developed out of the last year or two of research in this field is increasing interest and work on model criticism, which is a field of applied statistics concerned with stress testing models in order to make sure that the models that we're applying to our data are robust and that our conclusions are reliable. I'll end here to take questions. Thank you.
Thank you very much for this exciting and especially clear talk. And so I would like to see if there are any questions from the audience. Okay, I don't see any questions, so I will ask one. Ekrem, are you asking?
Yes, I have a question. What does it mean, memory effect of the gravitational waves? Is it can be measured?
Sorry, your audio broke up. Could you ask the question again?
Yes. What does it mean, memory effects of gravitational wave?
Yeah. And, okay. The memory effect.
It can be measured.
Yes. So the question was, can we measure the memory effect? So for those who aren't already familiar with it, let me just describe what the memory effect is. And I'm gesturing here with my hands. So normal gravitational waves that we measure with binary black holes, for example, oscillatory. So the space-time is oscillating back and forth. But the gravitational wave memory effect, this is something, a gravitational phenomenon that's been derived from general relativity, which states that there ought to be a permanent deformation in space-time called gravitational memory. So after the oscillatory waves pass, or as they are passing, this source is a permanent deformation in space-time that persists. Now, observatories like LIGO can detect the memory effect. We obviously cannot literal permanent displacement of test masses because our test masses are hung by wires. And so the wires push them back into the position and we can't measure at frequencies below 10 Hertz. But we can see the memory effect as a little low frequency burst that accompanies all of the mergers, all of the binary black hole mergers we see. They all get a little extra bump at the moment of maximum energy emission. And that little extra burst of gravitational waves is the memory. It's probably going to be hard to detect memory from an individual binary black hole. But sometime around here in the A+ era, we should have enough binary black holes that if you stack these all together and combine them, you'll be able to see all those little bursts will add up to a statistically significant signal at about 5 sigma. So I think this will happen in about 2026, 2027, but it will come from a lot of little memory bursts, not from a single dramatic burst.
Thank you so much. Thank you for very nice talk.
Any other question? Okay, then let me ask one. If we want to use these mergers for making cosmological conclusions, we need to measure the redshift and luminosity distance independently. Now, you did talk about redshift, but I had the impression that one couldn't measure the redshift of these the binary black hole mergers. One could only measure luminosity distance. Am I wrong, or can you measure the redshift, or which of these can you measure?
You're correct. So on this plot, when I showed the redshift reconstruction, this is assuming a cosmological model. Okay. It assumes a relationship between luminosity distance and redshift. The thing that we measure directly when we measure a gravitational wave signal is the luminosity distance.
Okay.
So in order to here we're assuming cosmology in order to figure this out. If you want to do cosmology, then you need to have some additional information. And there are a couple of different ways of doing it. One way is with associations with host galaxies, which have, so you have to bring in electromagnetic information into the equation as well. The other idea that has been proposed, let me go back here, is people have pointed out that this feature in the black hole mass distribution, if it's stable in redshift and it exists at all, it doesn't change as you go back further in time, then you can use, you can make statistical arguments to use this, this bump basically and track how this bump evolves as you go further away in luminosity distance. And what you measure with gravitational waves is the redshifted mass. But if you know where this bump is supposed to be, if you know that at 0 redshift it's here, and then you measure at redshift, you know, some other far distant object, and you see this, you measure many events far away, and you see it, you know, over here, then you can figure out how much the bump has been redshifted. So you can't do that for a single event, of course, but you can do that in a statistical sense. So there are a bunch of different proposals that people have for how you can add redshift information to the luminosity distance.
But for that, you would need tens of thousands of events.
Yes, I think for any scheme, you need lots of events, whether it's using associations with host galaxies, using features in the mass distribution, or what have you.
But I mean, if you could, I mean, you are not using a single event. You are using like a bunch of events at the same luminosity distance just for one data point. Otherwise, I mean, if you could use each single event as a data point, that would be much more useful. That's why I said tens of thousands. You know,
yeah.
You know, if otherwise hundreds would also be fine. You know. Any other questions? I guess not. Then let us thank our speaker again for this, as I said, exciting and clear talk. Thank you. Yeah. And okay, let me introduce our next speaker, Sergey Odintsov. He is from, I hope I'm pronouncing this correctly, ICREA, or ICREA professor at Institute for Space Sciences in Barcelona. I didn't attempt to pronounce this in Catalan. He got his PhD in University of Tomsk. He works on cosmology. He does a lot of work. He focusing on modified gravity explanations of the evolution of the universe. This includes bouncing model for eliminating the initial singularity, models that explain inflation and late time acceleration in the same framework, includes study of possible pre-inflationary and reheating eras. He is the recipient of numerous awards, including the Amaldi Medal. He's a foreign member of the Royal Norwegian Academy of Sciences, editor-in-chief of the journal Symmetry, editorial board member of several journals, author of 500 plus papers, and 2 books. Please, Professor Odintsov.
Okay, thank you. Can I? Okay, I see. Now, you see? Okay.
Yes.
Okay, you see my screen. Thank you for very nice presentation. So today I'll give the talk which consists of 2 deeply, not explicitly, but still deeply related parts. So first part of the talk is unification of inflation with dark energy in axion FR gravity, which was announcement announced in the program. And second part of the talk is how fundamental is entropy. And I will explain what is the relation between these two pieces of my talk. So let me start the introduction. We know that quantum effects, when we do any quantum field calculation, induce high derivative terms. So when we do calculation in quantum field theory, for example, in curved space-time, then among the high derivative terms, we have terms which are proportional to some invariance of curvature invariance or their squares. For example, R-mu square term, R square term, box curvature term, etc., etc. That means that even if we do believe in general relativity, we still somehow prove by existence of quantum field theory that general relativity is definitely very approximate theory, so it's incorrect theory. It's getting even more serious when we consider quantum gravity, whatever type of quantum gravity. It could be string theory or whatever else. So when we do quantum calculation in quantum gravity, again, we induce high derivative terms. And at the beginning of the universe, we have gravitational theory, which is completely different from general relativity, even if we started just from quantum general relativity. Okay. That means that apart from general relativity, we should consider number of extended or modified gravity theories, and the gravities they should be responsible for description of the universe, perhaps even better than general relativity. For instance, when we study early time inflation, we know very well that early time inflation may be described without any scalar field or vector or spinor field or whatever, just by changing of gravitational theory. It could be some high derivative gravity or some non-minimal scalar gravity coupling terms which are responsible for early time inflation. But the important point is that early time inflation is possible in such context using theory which is different from general relativity. Moreover, when we move to the current universe, to the dark energy epoch in the current universe, again, we know that it may be described by some gravitational theory. Now there are many, many, many different examples of such sort, but the first example was given by Capozziello some 20 years ago. We also quite naturally may get this unification of inflation with dark energy in modified gravity. The first example of such unification was indicated in our paper some 19 years ago. Furthermore, if we go further, we can describe the whole universe evolution. So inflation, then radiation and matter domination, and then transition to dark energy era in modified gravity. Of course, that is quite complicated numerical approach, but that can be done, and that can be realized in practice for different modified gravity theories. For example, for FR gravity, or for more complicated or different modified gravity, like modified Gauss-Bonnet gravity or string-inspired string-inspired gravity. As one benefit from the use of extended gravity, which goes beyond of general relativity, is the fact that we also can get dark matter from modified gravity, and that dark matter may proceed as kind of composite degree of freedom in some modified gravity theories. Good example of that sort is FR gravity. Again, first example of such dark matter was given by Capozziello some 15 years ago. Currently, we have many proposals for modified gravity. And let me list just some proposals for such theory. So one of the most popular proposals is based on so-called FR gravity, where we consider some function of curvature. So we may consider this function as kind of dynamical cosmological constant. And in such theory is rather interesting because it does contain ghost problem, as many modified gravity theories have, and it gives quite a realistic description of the current universe, including the fact that in some respect it may better describe lambda CDM epoch. I mean, better if compared with traditional lambda CDM using several different observational bounds. Another interesting example is so-called FG gravity, where G is Gauss-Bonnet topological invariant. It's known that in 4 dimensions, it's just a total derivative. But when we consider some function of FG, such theory becomes rather interesting and not trivial. Still, it has some reduction of number of derivatives. So when we write a Friedmann-Robertson-Walker equation in such theory, we may have Friedmann equations with not 4 derivatives, but with just 2 or 3 derivatives. However, this theory, unlike to FR gravity, contains ghosts and seems to be not completely consistent. So it may be at most some approach. Still, one can propose some extension, simple extension of such theory with adding scalar field so that to make such theory be ghost-free. So example of such sort have been presented. There is some interest to non-local gravities. One of the best model of that sort was proposed by Deser and Woodard in 2007. And later on, several even more interesting modification of such theory were proposed by Richard Woodard. And this theory may also describe quite well inflation or dark energy. However, it's a rather complicated theory. We can consider string-inspired gravity, which comes just from string effective action and subsequent compactification. So we get some scalar tensor theory with string-induced terms. For instance, they appear the term related with Gauss-Bonnet invariant, and this theory also may provide quite interesting and realistic dynamics for description of the universe evolution. There is also generalization of Born-Infeld theory of electrodynamics, that is Born-Infeld gravity. And Born-Infeld gravity is quite complicated theory because that is square root of determiner. So it's quite complicated to formulate it. There are more complicated theory, for example, theories which depend on some function where we have curvature and energy momentum tensor trace, or some power of such tensor. And again, we can study cosmology within such theory. There is also recently the development of related with teleparallel gravity, different version of teleparallel gravity, including even non-metric gravity, which is somehow related with teleparallel gravity. And generalization of such theory with some higher order terms. But that theory is somehow beyond of our standard metric formulation. So it's, in my impression, less interesting theories. So there are a number of reviews in this field, and I just mentioned my own review. Now, the question is, why we are interested in so many different modified or extended gravity? The answer is very simple. Some 40, 50 years ago, we thought that the only one gravity theory which easily pass local tests or solar tests, so gravitational tests inside of solar system, was only general relativity. However, now with more complicated theoretical background and with more and more developed observational bounds which come from different sources, we can show that from above series I mentioned, most of such series may quite easily pass solar system tests. So, of course, not all within any class of theory, but huge classes of such theories, which I presented above, they may pass solar system tests. And that means that if we present the theory which is best fitted with our observational bounds and cosmological bounds to describe the universe evolution, that will be the best proposal and the most reasonable theory. Of course, effective theory, because we are talking more on classical approximation, so we don't talk about quantum gravity effects, for instance. So that will be the point. And interesting that in relation with that many different extended gravities, we have number of the points and interesting phenomena, which may appear, for example, in stellar astrophysics, where we can find the violation of standard bounds, or we can find the interesting examples of stars, relativistic stars, which are impossible in usual standard astrophysics. It's more easy to create wormholes as solutions in modified gravity theories. And also in relation with the second part of my talk, it's interesting that we can study black holes, and we have new black holes in new families of black holes in different modified gravity. But in relation with modified gravity, we also have some new and interesting approximations to black hole thermodynamics, and I will mention this. So let me talk about a specific class of models, that is FR gravity with axion dark matter. The action of the theory I'm going to talk today is gravitational action, which consists of usual FR gravity. Then we have scalar field, and scalar field we consider just axion field, one of several axion fields which we have currently in the market. And in addition, we have some coupling, non-minimal coupling between gravitational sector and axion field. So the point is the following. Imagine that we successfully describe the inflation which comes from, for instance, gravitational path. Then we consider axion field in such model, and in specific model, we can get a realistic preheating scenario within such axion theory to give a realistic dark matter. Now I will show that in addition to this, introducing axion field with non-minimal coupling, we can also solve the problem of dark energy. So inflation plus axion may give you dark energy. Not necessary, but it may give. Or at least if you have the realistic theory of modified gravity, which describes unification of inflation with dark energy through intermediate eras like radiation and meta dominance, then with the term of that sort, we may correct the dark energy era so that it would be most consistent with observational bound. So we introduce some notation for gravitational sector, including non-minimal coupling of axion with gravitational sector. We write the standard gravitational equation, and we write the equation of motion for scalar field. And now we talk about the choice of FR gravity. In principle, any model of FR gravity which gives consistent with Planck inflation is okay. I'll take the simplest one, which describes Starobinsky inflation, so R square gravity, just as an example. And now let me explain you which approximation should we take so that axion field did not break the inflation, but could be relevant for description of dark energy error. So this function we assume to be proportional to inverse of scalar field. So this function appears here as non-minimal function. Then this function of curvature we consider as some power of curvature. Okay. Again, I remind that that is gravitational sector. That is this function. Now, this parameter we take in some specific interval. Let's go to unified description of inflation with first dark matter and then with dark energy. So first, several words about axion field. In fact, we use two mechanisms for axion scalar field, which were developed in the literature. And that is primordial broken Pechet-Quinn-like symmetry, and the fact that axion field is responsible for reheating when it oscillates. Okay, so that is kind of one of very well developed axion dark matter models, and I'll go on its description very briefly because it's for the people who know this scenario. There is no big difference with standard this misalignment scenario for or misalignment model for axion field. I only describe additional assumption which appears due to the fact that we have non-minimal coupling of axion with gravity. So we consider this non-minimal coupling, and we put the following conditions: that during inflationary era and all subsequent cosmological era, there is the condition which relates somehow non-equality, which relate potential with this function, gravitational non-minimal gravitational coupling. So we can rewrite this in the following form and do integration over a scalar field, and we have this inequality. Now we will use this inequality, and the point will be the following. The importance of this inequality is twofold. From one side, using this inequality, we achieve that axion field does not influence inflation, even when this non-minimal coupling is included. From another point, this condition makes sure that after inflation, this non-minimal sector doesn't influence the preheating scenario based on this misalignment axion model. Okay, so let's go to the detail. We consider inflationary era, and in inflationary era, the axion scalar potential has the following form in terms of scalar field and axion mass. We assume that axion field is overdamped during inflation, and we take the following initial condition for the values of axion and its derivative. Okay, so this condition in fact introduce for us axion decay constant and the initial misalignment angle, where this time is the cosmic time during the inflationary period. Okay, Now we select again, that is the repetition of the works on misalignment axion evolution. So I don't go deeply in the detail. We select following to these works, we select this axion decay constant and the axion angle in the following form in terms of electron volts as it was proposed in these papers. And we start to study how the universe evolves after we have mass of axion approximately equal to our Hubble rate. So axion oscillations, they start when we have this mass proportional to Hubble rate. So we can study scalar equation of motion. We write it approximately in the following form because we drop non-minimal term based on our above inequality. We find some slowly varying oscillating solution with some time constant, and solving the equation for this this equation for this function, we can explicitly get that this function is proportional to scale factor in this power. Then axion energy density is proportional to this form. We write it explicitly, substituting here the corresponding values for axion and its derivatives. And we come finally to the fact that axion energy density is indeed dark matter energy density, and it's proportional of scale factor, inverse proportional in the power 3. Okay, so that is an important fact which shows that axion dynamics after frozen state during inflation is just called dark matter. And it doesn't matter what was Hubble rate background. I showed it on the example of R square inflation. However, we may consider any other cosmological evolution, any other inflation. Now, let's study background evolution during inflationary era. So we consider Friedman equation for R square gravity, which, as I told, we wrote, and then in this expression, we see that this term and this term, thanks to our inequality, so thanks to our bound to this term, becomes irrelevant. So we may forget about these two terms, non-minimal terms during inflation, and we are back to usual inflation in FR gravity. So studying inflation in this FR gravity, R square gravity was the example here. We just come to standard quasi-de Sitter evolution, which gives inflationary parameters. So primordial perturbation in tensor to scalar ratio consistent with Planck data up to very high accuracy, what is rather well known. Now important new element. Let's consider now dark energy epoch. So we consider the dark energy epoch, universe expands, axion fields oscillates, and dynamics is changing. So axion field is not frozen anymore. So now we can study dynamical evolution with account of axion energy density and with non-minimal coupling. So we write the correspondent Friedman-Robertson-Walker equations. They have the same form as that was before when we studied inflation. However, in this case, we have completely different situation. And the situation is the following, that in the left-hand side, this non-minimal terms is dominant because it contains the term which is inverse proportional to curvature. Okay, so it contains negative powers of curvature, and curvature we know in current universe is very small. On the right-hand side, the dominant term is Z term. Again, that is related with non-minimal term, and it's quite dominant again for small curvature. Potential term, so this term, is proportional to R square, and kinetic terms depends on some combination of this function A and its derivative. Okay. So approximately at late time, Friedman equations take the following form, and it can be rewritten as the following, and we get explicitly some approximate solution for Friedman for Hubble rate, and that Hubble rate describes quasi de Sitter universe again. So approximately it is constant. We can calculate deceleration parameter for Hubble rate, which takes the following form, and we also can calculate effective equation of parameter of the effective fluid of the universe at that period, and it's equal to -1 with something. As we know, according to observational bound, that is precisely what we need to describe the universal late time acceleration. Now, playing with the parameters which appear here, we can achieve completely the fact that this effective equation of state parameter lies within the observational bounds for which comes from astrophysical observations. Okay, so we show that coupling of axion with FR gravity, we are able to induce effectively dark energy epoch thanks to the coupling. Of course, we may go in another way. For instance, we can consider as a version of modified gravity, so not only R squared term, but also some power law term in curvature, and adding similar axion field, we see that within such theory, we know that there is a possibility to unify inflation with dark energy. Then axion field plays the role of cold dark matter. And in such theory, we have complete unification of all three dark forces. So inflation, dark energy, and dark matter. Moreover, if we have problems in dark energy sector, we can add here some non-minimal term of the sort I described above, and we can change slightly the behavior of dark energy Hubble rate so that to get a realistic dark energy epoch description. So the main lesson of that first part is the following, that within modified gravity, we can easily achieve unification of dark energy with inflation, including dark matter. And the easiest possibility for dark matter in such case is axion dark matter. Now let me go to second part, which is how fundamental is entropy. So when we have been students, at least most of us, we have been taught during the courses of classical thermodynamics that entropy is unique, universal, and fundamental quantity, which is eventually the most important quantity in physics. However, time goes, and with the development of quantum physics, quantum gravity, non-extensive thermodynamics, information theory, etc., we realized that entropy is not unique and it's not fundamental. Furthermore, in relation with quantum field theory and quantum gravity, we realized that entropy may have even quantum corrections. Now, we in different description of classical and quantum systems, different entropy concepts were introduced, which started from different points of view. I will concentrate now on black holes as an example. So, in 1970, it was realized that black holes are not cold objects. They have entropy and temperature. However, Bekenstein proposal to calculate entropy for black hole so that it should be proportional to black hole horizon area was not considered seriously. And the reason was the fact that there was no sum consistently checked. However, when Hawking discovered that Schwarzschild black hole and then any other black hole radiate quantum of fields, particle of fields emitting a black body spectrum of Hawking temperature, where m is black hole mass, then this discovery of Hawking made sense of Bekenstein proposal for black hole entropy calculation. And that was the beginning of golden era for black hole thermodynamics. However, the puzzling feature of Bekenstein-Hawking entropy was that from its very beginning, it was not proportional to black hole volume as in classical thermodynamics, but it was proportional to black hole area and black hole mass. Okay, so now it's important that when we, in classical thermodynamics, when we consider black hole entropy, we use somehow the fact that this theory has horizons. Last years, in relation with the fact that we have many different modified theories, which may be consistent with solar system tests, there were many attempts to introduce other entropies, not only Bekenstein-Hawking entropy, but Renard, Tsallis, non-extensive entropy, etc., etc. So it was a rather naive application of such different different entropies for black hole without completely clear understanding why it leads to some say incorrect description. Moreover, we know that horizons appear not only in black holes, but also in cosmology. Then, also in cosmology, we may use different horizon thermodynamics. Again, using different thermodynamics, we may somehow apply a thermodynamical approach to gravity theory. We may use different entropies, and we may come to different Friedman equations. Of course, all these different Friedman equations, they have equivalent description in terms of modified gravities. And then we have many different possibilities, still consistent with observational bounds to describe also such entropy universe. So let me give you just several hints. So Bekenstein-Hawking entropy is proportional to area law. And in this description, we have horizon radius. And as I told, this proposal is not unique. So naively, we can use different entropies to describe black holes thermodynamics. So, for instance, Tsallis entropy, which appeared as non-extensive statistics for systems with long interaction, in which partition function diverges. So, in that case, this entropy is the following function. So it's slightly different from Bekenstein-Hawking entropy, so that we have this expression. Now the next is Renai entropy. Again, that is entropy which appears as index specifying the amount of information, so not even in physics. And this entropy is logarithm of Bekenstein-Hawking entropy. There is Sharma-Mittal entropy. Okay, this Sharma-Mittal entropy is the function which is similar to this Tsallis entropy, where we have three parameters for this R and delta. So this Sharma-Mittal entropy may be seen as combination of Renai and Tsallis. There is also Barrow entropy, which is similar to Tsallis non-extensive entropy, but it was introduced as entropy to describe the quantum gravitational space-time form. So physically, it's different. Finally, there is a Kaniadakis entropy, which is sinus hyperbolic of Bekenstein-Hawking entropy. And we also, in non-extensive statistical mechanics in loop quantum gravity, may introduce the corresponding entropy. Okay, so for this entropic index Q quantifies the probability of frequent equants enhanced relatively to infrequent ones. Okay, so that is some parameter here. So we have number of entropies, and we have the following properties which all these entropies share. And the properties are the following. These all entropies vanish when Bekenstein-Hawking entropy vanishes. So in the third law of standard thermodynamics, this quantity exponent of entropy express the number of states. So entropy vanish when the temperature vanish. However, for Bekenstein-Hawking entropy, it diverges when entropy vanishes. Okay, so it goes to zero at infinite temperature. So it's inverse. Nevertheless, we require that any generalized entropy vanish when Bekenstein-Hawking entropy vanishes. All these entropies are monotonically increasing functions of Bekenstein-Hawking entropy. Next, all these entropy are positive quantities like Bekenstein-Hawking entropy. So that is quite natural. And finally, all above entropies, they reduce to the Bekenstein-Hawking entropy in appropriate limit. Then quite standard proposal, maybe, or conjecture, quite interesting conjecture is can we introduce some most general entropy or class general entropies which generalize all above entropies and maybe even more entropies? So I give the proposal of such entropy here. So we consider this entropy construct, as I should say, of course, it's not based on some physical properties. So we don't know which physical system such entropy may describe. So we introduce some function which depends on 6 parameters, and this function looks as the following. So we have these 6 parameters. So
you have about 10 minutes.
Yeah. I see. I control. So we can check one by one that the limits, corresponding limits of this general function, they give above several proposals for entropy. For instance, in the limit when these 2 parameters turns to 0 and the choice of these parameters gamma are equal, we come to from our generalized entropy, we come to the entropy in the power gamma. So choosing this gamma to be equal to delta or 1 plus delta over 2, we get Tsallis entropy or Barabasi entropy. With further choice, so for example, taking this parameter equal to 0 and playing a little bit more with parameters, we obtain Sharma metal entropy. In the same way, we obtain in some choosing parameters from above entropy, Renai entropy, and so on. So one by one, we obtain all these entropies. So from these 6 parameters entropy, we get all these entropies which were so far used for black hole physics. Furthermore, this entropy satisfies to generalized third law, and it turns to 0 when Bekenstein-Hawking entropy turns to 0. It's also monotonically increasing function. Okay, positivity is also satisfied in this function. So also there is a limit of this general entropy construct to Bekenstein-Hawking entropy because it reduced to all these several different entropy proposals from different points of view. We may consider even 3-parameter dependent entropy. For this 3-parameter dependent entropy, we get again, we can show that all above entropy properties are satisfied for such theory, and that in different limits, this entropy reduced to all above entropies. Okay, so I don't go to details of this rather simple mathematical exercise, and I just go to the explanation why this generalized entropy are not useful in the description of black hole thermodynamics or useful in very restricted cases. So consider Schwarzschild black hole. Okay, so for Schwarzschild black hole, we have black hole mass, we have its description, line element, we have black hole horizon, which is located on Schwarzschild radius. So the point is the following. Of course, formally, considering this black hole as some thermodynamical object, we can apply any of above entropies, not only Bekenstein-Hawking, as was done many times during last 50 years, but any thermodynamic. However, there is inconsistency, and I will show this inconsistency. The inconsistency comes from the fact that applying different thermodynamics, different entropy to such a black hole, we cannot get, for instance, Hawking temperature out of this black hole. So, for example, if we identify mass with thermodynamical energy density and consider thermodynamical equation, we define generalized temperature in the standard way. Okay. Now we work with our entropy. So in this case, our entropy depends on 3 parameters. So we do calculation of this generalized temperature from our 3-dimensional generalized entropy, and we come to the point that our temperature is not Hawking temperature. So whatever calculation we do for presented entropy, we cannot get Hawking temperature. Equivalently, we can do the inverse procedure. So we can identify, say, temperature which comes from generalized entropy or any specific entropy like Renai entropy or Barabasi entropy with Hawking temperature, and we calculate black hole mass or black hole energy. And again, we will not get consistency. So the corresponding expression is calculation is given here, and that shows again the inconsistency of that sort. So the conclusion of that section is the following: that we can propose different generalization of entropies, okay, and we can propose eventually some function which is most general entropy we can imagine, but nevertheless we cannot use any entropy apart of Bekenstein-Hawking entropy for the description of black hole thermodynamics. That is in contrast to the number of recent claims where black hole thermodynamics was described in terms of different entropies. So in the last couple minutes, I say several words about holographic cosmology. So in fact, when we study the universe, we know that the universe also may have horizon. And on the horizon, we may have the density of the holographic dark energy, which is proportional to inverse holographic cutoff. And then we can write Friedmann-Robertson-Walker equations. We can derive these Friedmann-Robertson-Walker equations from thermodynamical perspective, but using all these above entropies. So using just standard Bekenstein-Hawking entropy, we come to standard Friedmann-Robertson-Walker equation. So the derivation is given here. From thermodynamical point of view, we come to the standard Friedmann-Robertson-Walker equation. Okay. Now, if we repeat the same procedure, we come to different equations. So they differ from that equation, and the difference depends from the entropy you use. Effectively, instead of energy density here, we get energy density which is due to the corresponding entropy. For instance, for say for explicit example for Renai entropy, Tsallis entropy, we get this equation, okay, and we can study this. If we consider some other entropy and rederive, for example, Renai entropy, we can rederive Friedmann equation, and we get explicitly the correspondent energy density. The same for our generalized entropy construct. The important point and why it's related with modified gravity is that any such modified Friedmann-Robertson-Walker equation we can rederive from some specific modified gravity. So there appears very interesting relation between different modified gravities and different entropy proposals. Then for some of such entropy proposals, we may come to explicit description of the universe, which permits the unification of inflation with dark energy epoch, because it's also permitted in modified gravity theory. So in order to finish, I will not go to the detail of this. In order to finish, I want just to say that the lesson of all this discussion is the following. We have different entropy concepts, and in fact, they appeared entropy constructs which generalize all known entropy proposals which were given so far. However, despite the fact that they may be quite successfully used in cosmology, it's hard to use all these entropy proposals in black hole physics. Nevertheless, in cosmology, we get a consistent description of the universe, realistic description, including inflation, dark energy, within such generalized entropy proposal. So let me stop on this point.
Thank you very much for this interesting talk. Any questions from the co-hosts? Yes, Professor Demir.
Thank you for the talk. I am just curious. I mean, every physical system has its own entropy and has its own other thermodynamical variables. So why do I need this parametric generalization of entropy? And this parametric generalization seems to involve only surface. Why doesn't it involve also volume if it is a general entropic construct, so to say? Thank you.
Okay, so actually you answered to the title of my talk. So you say explicitly that entropy is not fundamental because it's different in different physical systems.
Mm-hmm.
And then do we need to use it if it's not fundamental? In the course of thermodynamics, we were taught that it's fundamental, universal, unique. Now we know that it's not so. Okay, then forget the entropy completely and let's invent some other quantity which will be fundamental and apply to any physical system because there should be something.
But is this parametric generalization a fundamental definition to your idea?
No, it's just proposal, conjecture.
I mean, it's a parametric generalization. I cannot just see how it could be fundamental in that sense. Thank you.
Exactly, I agree with you.
Okay, thank you.
Okay, there are a couple of questions in the chat box from Shema. About the first part of your talk, is it the axion that drives the inflation?
No, in the first part of my talk, the inflation was due to modified gravity, and axion was non-essential during the inflationary epoch.
Okay, and also how about the perturbations? How do the perturbations work for modified gravity theories? And for example, are there predictions one can compare with the CMB data?
Yes, of course. You can do perturbation for different modified gravity theories, and you can get quite good consistency in the same way as standard lambda CDM, for example, without any problem.
Any other questions?
That is understandable because you have equations which are similar effectively.
Any other questions? Okay, I have one sort of general question and another one kind of related to Professor Demir's question. Well, my general question is now because well, when we discovered the accelerating expansion of the universe, we realized that Einstein general relativity with matter domination doesn't work. So we have to modify something. So why do you prefer modifying the left-hand side of the Einstein equation rather than the right-hand side? This is my general question.
I replied to this question in the first sentence of my talk. You believe to quantum field theory. Quantum field theory works in your room now. Our computers, electricity, quantum electrodynamics. So when we do calculation, for example, in quantum electrodynamics, in curved space-time, so considering that universe is realistic, so it's not in Minkowski space-time, but in curved space-time, then we get vacuum polarization terms. And that vacuum polarization terms are terms of the sort R square. For example, conformal anomaly-like terms. Then can be even non-local terms if we talk about quantum gravity. So even if you believer of general relativity, at the early universe, general relativity is destroyed by these terms. So you have corrections, high derivative corrections to these general relativity due to quantum effect. That's all.
Okay, quantum. All right. My other question is, let me see if I have time. If you give up the Bekenstein-Hawking entropy and use one of the other entropy concepts, why do you expect to get the Hawking temperature? I mean, why do you still use Hawking temperature as a baseline?
No. Hawking temperature is a kind of verification of Bekenstein-Hawking entropy.
Okay.
It's verification, and you get it explicitly only when you do calculation following to Bekenstein proposal. But
yes,
if you do calculation following to any other proposal,
you get another temperature.
It's another temperature which is not equal to Bekenstein-Hawking. That's all.
So I thought you were complaining about the getting another temperature.
No. It's inconsistent. Okay. Become inconsistent.
Okay. Thank you. Okay. If there are no other questions, we thank our speaker for this interesting and enlightening talk. Another question came actually.
I think there is one question.
Yes, one more question has come at the last minute, but yeah. It says you talked about oscillations and also entropies. Why don't you think about topological entropy, which is about exponential complexity that can be used in the evolution of the universe?
You can add any other entropy, and you can, in the same way, you can generalize, include such entropy to the class of the entropies I was studying. So there is no any problem. I just listed some of entropies, not all.
All right, thank you. So Mithat, please take over.
Okay, so I'm going to chair this session. Essentially, it has been a very successful and productive conference. Actually, I would like to thank to the organizer, first of all, Ekrem Aydıner and his colleagues. And it's an honor for me to announce Professor Edward Wheaton, who is the American mathematical physicist at the Institute for Advanced Study, School of Natural Science in Princeton, USA. Dr. Wheaton earned his bachelor's in physics in 1971 from Brandeis University. And he did his doctoral work at Princeton and get graduated in 1976. Actually, his research areas mainly sparse string theory. Actually, he's the pioneer of the sparse string theory and is well known for his M theory. Other research areas are the quantum gravity, supersymmetric quantum field theories, and other areas of the mathematical physics. His work has also significantly impacted pure mathematics. And he has actually many awards and honors that I cannot count all of them here, but I can just pronounce several of them. So basically, I mean, he was the first physicist who was awarded the Fields Medal at the International Congress of the Mathematicians in 1990. And he has other medals, like Einstein Medal by the Einstein Society of Bern in Switzerland, 1985. And he also received the Druck Medal from International Center for Theoretical Physics, Klein Medal, Stockholm University, Newton Medal of Institute of Physics, Medal for Exceptional Achievements in Research, American Physical Society, again, the Einstein Medal, World Culture Council in 2016. So there are many more actually that I can't, but just the several of them. And he has the author of more than 300 scientific papers, more of them on string theory. And his research on strings has yielded numerous major theories in the field, including the M theory, which combines the 5 separate strings theories into one master equation. And there are several papers. I mean, the most cited papers are the anti-de Sitter space and holography, superstring theory, quantum field theory and Dion's polynomial, string theory and non-commutative geometry, dynamical breaking of supersymmetry, cosmic separation of phases, and more, of course. So he's going to present today the entropies and algebras in black hole theory and this stir space. Welcome, Dr. Edward Witten. We are very happy to have you here with us today, and we will be happy to hear your new presentation and theories today.
Well, thanks so much for the kind invitation and for the introduction. So, as was just explained, my title is going to be about algebras and entropies for a black hole and de Sitter space. And hopefully you'll see my slides in a second. Not quite sure what Zoom is doing. Oh, sorry. Now you can see it.
Okay, we see it.
So I'm going to start with a general introduction, and then I'll talk about this paper I've indicated, as well as work that's forthcoming with Chandrasekharan and Pennington. And because time is limited, I'll mostly explain the general ideas rather than technical details. Black hole entropy, actually, as you were reminded in the last talk, started with the work of Jacob Bekenstein. Bekenstein was inspired by questions from his advisor, John Wheeler, and he asked what the second law of thermodynamics means in the presence of a black hole. The second law says that for an ordinary system, entropy can only increase. However, if we toss a cup of tea into a black hole, the entropy seems to disappear. Bekenstein wanted to generalize the concept of entropy, so the second law would hold even in the presence of a black hole. So for this, he wanted to assign an entropy to the black hole. Well, so he wanted a property of the black hole that only increases. It's not true that the mass of a black hole always increases. If you have a spinning black hole, like the ones that are believed to exist in centers of galaxies, when its spin slows down, the mass goes down also. You can make the spin and mass of a spinning black hole go down. But at this time, Hawking had just proved the area theorem, that the area of the horizon of a black hole can only go up. And so it was fairly natural for Bekenstein to propose that the area of the black hole horizon is the contribution to the entropy. So he defined a generalized entropy of a black hole, which was a multiple of the horizon area. The 4gh bar is needed for dimensional reasons, plus the ordinary entropy outside the black hole. So Bekenstein's generalized entropy is the ordinary entropy of matter and radiation outside the hole, plus a multiple of the area of the hole. And the generalized second law was supposed to say that the generalized entropy always increases. Supposedly, Stephen Hawking was skeptical of Bekenstein's idea and set out to disprove it by studying the behavior of a quantum field interacting with a black hole. What I've drawn here is the Penrose diagram for a star that collapses to make a black hole. And then there's a physicist at future infinity at late times making observations and studying the experience of an observer far outside the black hole in the far future. Hawking discovered that the black hole actually radiates at a temperature proportional to h bar, and ended up proving that Bekenstein was right. Not long afterwards, Gibbons and Hawking considered another situation with horizons. This was in cosmology rather than black hole physics, and was also mentioned in the last talk. And they proposed that also the area of a cosmological horizon is a kind of entropy. More specifically, they considered de Sitter space, which is the simplest model of a cosmology with cosmological horizons. And they assigned a temperature and an entropy to the region of de Sitter space accessible to an observer. So de Sitter space may be a good approximation to our universe in about 10 to the 11 years. It's the maximally symmetric solution of Einstein's equations with a positive cosmological constant. Here's the formula. It undergoes exponential expansion when t goes to plus or minus infinity. It's the t going to plus infinity part that may be a good approximation to the future of our universe. Because of exponential expansion, other galaxies in the real world will be out of sight within roughly 10 to the 11 years, unless they're gravitationally bound to the Milky Way. They'll be behind the cosmological horizon. So here's a Penrose diagram that illustrates the idea. So the square is the Penrose diagram of de Sitter space. Future infinity is at the top, past infinity is at the bottom. On the left is the world line of an observer. In green is the region causally accessible to the observer. It's called a static patch. It's the region to which the observer can send signals and also receive information from. Usually, to do an experiment, you have to do something that disturbs something and then see what happens. So for example, you shine an electron beam and see what bounces back. Thereby you can do an experiment on whatever is inside the green region. So the green region is the region accessible to the observer, and it's the region that's not behind the future or past horizon, past cosmological horizon. So Gibbons and Hawking attributed to the cosmological horizon an entropy, which was its area over 4G, I said h bar to 1, and a corresponding temperature, which actually had been defined earlier. The meaning of de Sitter entropy has been something of a mystery ever since. So Hawking gave a clear meaning to black hole entropy by discovering that black holes radiate, and the temperature of the outgoing radiation is the black hole temperature, and then the expression, the formula dE equals TdS, the first law, lets you to infer the black hole entropy. We can't give such a meaning to the de Sitter entropy, so it's been something of a mystery ever since exactly what the de Sitter entropy means. Now, many researchers have thought that somehow the entropy A over 4G means that the black hole or the horizon of cosmological horizon can be described by some sort of degrees of freedom that live as its horizon with 1 bit or qubit for every 4G of area. So for example, in a famous article in 1992, John Wheeler illustrated that idea with this picture. As I say, the article was published in 1992. I tend to believe that Wheeler had been drawing the picture for 2 decades by that time. Now, black hole, there's a lot of mystery still today about what black hole entropy really means, but modern understanding revolves around defining entropy in quantum mechanics at a more fundamental level. So classically, you could consider n particles in a box with positions x and momentum p. As a classical physicist, Boltzmann assumed that at a given time, x and p have definite values, even if we don't know them. You can describe the state of what you know by a probability distribution function, rho of p and x, that encodes your knowledge. And eventually, Boltzmann and his successor Gibbs defined the entropy as a phase space integral of minus rho log rho. So in classical physics, entropy depends upon your limited knowledge of the system. The quantum analog of the probability distribution function rho is the density matrix of a quantum system, also often called rho. So the quantum version of the Gibbs formula for entropy is the von Neumann entropy of the density matrix, minus the trace of rho log rho. In the classical limit, von Neumann entropy goes over to the classical entropy, and it fixes an additive constant that's poorly defined in the classical expression. But there's a basic difference between the classical case and the quantum case. Classically, you believe x and p have definite values, and you use a probability distribution function because of limited knowledge. So the entropy too reflects lack of knowledge. Quantum mechanically, if a system is entangled with something else, a mixed state density matrix, rho, is the most precise description that quantum mechanics allows. And therefore, there's an irreducible fine-grained entropy, even if we know the state of the system as precisely as possible. That has no classical analog. So this fine-grained entropy is often called entanglement entropy, because it arises from the entanglement of a system with another system. So the combined system may have a pure state density matrix, but a subsystem would still have a mixed state density matrix and a von Neumann entropy. The idea that Bekenstein-Hawking entropy of a black hole should be understood as entanglement entropy was apparently first put forward by Raphael Sorkin in 1983 in a paper that initially attracted only modest attention. The idea was the following. In a quantum field theory, divide space into two regions, A and B. Now, in Sorkin's application, B was the region behind the black hole horizon, and A is the region outside. But for the moment, you could consider any division of space into two regions, A and B. Let psi be a state of the whole system, and let rho A be the reduced density matrix of the state psi for measurements only in the region A. So in the jargon, you trace out degrees of freedom in region B to get a reduced density matrix in region A. Then you can try to calculate the fine-grained or entanglement entropy minus the trace of rho A log rho A. One finds, or Sorkin found, that it's ultraviolet divergent regardless of psi. And moreover, the coefficient of the leading divergence is proportional to the area A of the boundary between regions A and B. In modern language, Sorkin's idea was that somehow gravity cuts off this divergence, leaving an entanglement entropy in the vacuum that would be the Bekenstein-Hawking entropy A over 4G, where A is the area of the boundary between them. That makes a lot of sense as it matches two ideas. One, A over 4G is the irreducible entropy of the system for someone who has access only to the region outside the horizon. Two, the divergence in the entanglement entropy is proportional to the area of the surface because it comes from short wavelength modes near the surface, which for Sorkin's application would be the horizon. As if after cutting off the divergence, the density of quantum degrees of freedom on the horizon per unit area is 4G, as in Wheeler's picture. Sorry. So anyway, this was Sorkin's idea. And the next major improvement was made a decade later by Susskind and Uglum, who made a simple observation that strongly supports the idea of interpreting S out, the entropy outside the black hole, as entanglement entropy. When Bekenstein talked about the generalized entropy, his S out, he said, was the ordinary entropy outside a black hole. And he imagined that as thermodynamic entropy. But thermodynamics isn't valid for an arbitrary state of a system. Entanglement entropy is universally defined. And Susskind and Uglum suggested that you could get a more precise and also more general version of Bekenstein's idea by interpreting S out as entanglement entropy. If we interpret S out this way, Susskind and Uglum made the simple but wonderful observation that the generalized entropy is better defined than either term on the right-hand side is separately. The second term has an ultraviolet divergence that Sorkin had noted. But Susskind and Uglum pointed out that the first term also has an ultraviolet divergence because there's an ultraviolet divergence in the relation between the bare Newton constant G0 and the physical observed Newton constant G. When Hawking did his famous calculation of black body radiation from a black hole, the G that appeared in his discussion was the bare Newton constant G0, because he was not including graviton loops or any loops that would normalize Newton's constant. So Hawking's derivation involved G0, but when we imagine the generalized entropy in the real world, we imagine the physical Newton's constant G appearing in the formula. But the relation between G and G0 has an ultraviolet divergence, which at one loop order takes this form, where lambda is an ultraviolet cutoff and C is a constant, which at one loop level is independent of H bar. So S out has a divergence independent of H bar. And Susskind and Uglum pointed out that A over G times H bar also has a divergence proportion that's a constant, just because 1 over G times H bar has an ultraviolet divergence. Soskine and Uglum showed that in leading order, the ultraviolet divergences in S out cancel those in 1 over G. And this was refined and better understood by later authors. So 21st century developments have strongly supported this interpretation that the generalized entropy has something to do with entanglement entropy, but it's left us with plenty of mysteries. I'm just going to talk about one aspect of the story because time is limited. Why is it that entanglement entropy is ill-defined in quantum field theory, so that S out has the quadratic divergence that Sorkin discovered, but entanglement entropy is well-defined once gravity is included, where we follow Sorkin, interpret this term as a sort of short distance contribution to the entanglement entropy. So then the whole thing is entanglement entropy with gravity. The question is, why is it that gravity makes entanglement entropy better defined than it is in ordinary quantum field theory? So explaining that one point will be the goal of the rest of the talk, and I'll give a slightly abstract explanation. First of all, in ordinary quantum mechanics, when one considers the entanglement between two systems A and B, one normally assumes at the start that each system has its own Hilbert space, HA or HP. The combined system then has a tensor product Hilbert space, HA tensor HP. A state psi AB in the combined Hilbert space might be a simple tensor product of state psi A and psi B. If that's the situation, then systems A and B separately can be described by pure states, namely psi A and psi B, and there's no entanglement entropy. But a more typical state is not a tensor product, rather it's a sum of tensor products, in which case we say that systems A and B are entangled. In that case, system A, for instance, has a density matrix of the form I've written that you get after summing over the unobserved states of system B, or unobserved if you're only going to measure system A. And then it has an entropy minus trace rho A log rho A, which can be expressed in terms of the coefficients Pi in this formula. Here I've assumed that psi AI and psi BI are likewise orthonormal for different I and J. The point is that in ordinary quantum mechanics, whether or not a state has non-zero entanglement and entanglement entropy is a property of the state. That's not so for entanglement entropy between different regions in quantum field theory. Let's go back to Sorkin's picture. The divergence Sorkin found was an ultraviolet divergence, so it doesn't depend on the state. Every state looks like the vacuum at short distances. So unlike ordinary quantum mechanics, where a state might or might not be entangled, in quantum field theory, every state has the same divergent entanglement between regions A and region B. The root of the problem is that in quantum field theory, it's not true that there are separate Hilbert spaces HA and HB for the inside and outside regions. There's only a combined Hilbert space H for the whole system. What the separate regions A and B have are not Hilbert spaces HA and HB, but only algebras of observables A and B, curly A and curly B. These algebras act on H, so you can regard them as von Neumann algebras. That's just a fancy name for an algebra of operators on a Hilbert space that's closed under a natural type of limit. So we have to get used to the idea that in region A and B, you have not a Hilbert space, but only a von Neumann algebra that acts on the big Hilbert space of the combined system. So now we're going to need a few facts about von Neumann algebras, which I'll first state, and then I'll explain a little bit by giving examples. So broadly, there are three types of von Neumann algebra. A type 1 algebra is the algebra that we usually take for granted in ordinary quantum mechanics, the algebra of all operators on a Hilbert space. In ordinary quantum mechanics, when we discuss a system A, it has a Hilbert space of H sub A, and the algebra of observables in this system is the algebra of all operators on that Hilbert space. And by definition, that's a type 1 algebra. So that's the algebra, type of algebra that we normally take for granted. If a system is described by type 1 algebra, it can have quantum mechanical pure states, namely states in the Hilbert space, on which A is the algebra of observables. And a pure state would have no von Neumann entropy. You can also define density matrices and entropies for a system that has such an algebra of observables. The other types of von Neumann algebra are less familiar. I'll just state a couple of facts and then give examples. A type 2 algebra does not have pure states, but it is possible to define density matrices and entropies for a system in which the algebra of observables is of type 2. A type 3 algebra is the worst type. A system whose observables form a type 3 algebra does not have pure states and also does not have density matrices or entropies. By now, you might anticipate the bad news. In quantum field theory, the algebra of observables of a region of spacetime is always of type 3. So to a region, one can never associate a pure state or a density matrix or entropy. The type 3 nature of the algebra is the reason for the universal ultraviolet divergence of the entanglement entropy. However, it turns out that including gravity, even semi-classically, changes the picture. At least in the case of the black hole or de Sitter space, including gravity at a semi-classical level changes the algebra of the region outside the horizon from type 3 to type 2. I don't know what would happen if you could include gravity exactly. I also don't know for sure whether there's a similar answer in more general spacetimes with horizons. All I know is that for the black hole and de Sitter space, gravity turns the algebra from type 3 to type 2. So when gravity is turned on even semi-classically, the region outside the black hole or de Sitter horizon is described by an algebra in which the notion of entropy is well defined, though there's no notion of a quantum microstate. We can interpret this as a somewhat abstract answer to the question of why gravity suddenly enabled us to convert the ill-defined divergent S out into the better defined generalized entropy. But to understand how this works, we need to understand something about von Neumann algebras of type 2 and 3. They can be most simply described as algebras that act on certain thermal systems. So remember first that a finite thermal system A with Hamiltonian H and inverse temperature beta has a density matrix, as written here, where Z is such that the trace of the density matrix is 1. Now, what's the thermofield double state? Roughly speaking, the thermofield double state is a pure state of a larger system that has this density matrix. That's not so precise for an infinite system, but it is precise for a finite system. In the case of a finite system, you literally introduce a second copy. Then you consider this pure state of the combined system, which I've called psi TFD for thermofield double. And psi TFD has been chosen because it purifies the thermal density matrix in the sense that for any operator A on system A, capital A, the expectation value of A in the state is the trace of A times the thermal density matrix. Now, this formula for the thermofield double state is usually not well defined for an infinite system, since Z is infinity and the sum doesn't converge. But it turns out that psi TFD does, in an appropriate sense, have a thermodynamic limit. By the way, the one-sided Hilbert space of the black hole does not have a thermodynamic limit or of a thermodynamic system. but the thermofield double state, or the two-sided state of the black hole, does have a thermodynamic, or in that, for the black hole, large N limit. Although the thermofield double state has a thermodynamic limit, funny things happen to the algebra of the observables when you take that limit. That's where algebras of type 2 and type 3 come in. Well, let's do this for the simplest case of all, which is the case that the Hamiltonian is 0. We do know how to diagonalize that Hamiltonian. For a system A of n qubits with Hamiltonian 0, the partition function is 2 to the n, and the thermofield double is just a completely entangled state of system A with a second system B that also consists of n qubits. So the nth qubit of the first system is completely entangled with the nth qubit of the second. Now let A and B be operators that act. Last time I gave this talk, the terminology caused trouble. Let A and A prime be operators that only act on the first k spins of system capital A for some little k. Define a function f of A as the expectation value of A in this thermofield double state psi. You can see that f of 1 is 1 because the state was normalized. And less obviously, you can see that if A and A prime are any two operators on system A, then f of A prime is equal to f of A prime A. The operators A and A prime don't commute, but they nevertheless satisfy this relation, which depends upon the special nature of this completely entangled state. And moreover, the function f of A has a thermodynamic limit in the sense that f of A is independent of n as long as n is at least equal to k. A was an operator that acts on the first k qubits. As long as you include all the first k qubits in the description of the system, it doesn't matter how many more you include, because the state is such that if an operator A doesn't act on extra qubits, the existence of the extra qubits doesn't affect the expectation value of the operator. Finally, f is positive in the sense that if A is non-zero, then f of A dagger A is positive. So far, we've defined the function f in the whole algebra A naught of all operators that act on only finite many qubits in system A. But you can take the closure of A naught in the von Neumann sense. That means you allow certain operators that act on any number of qubits, but with matrix elements that decay rapidly for large K. So then you can complete A naught to a von Neumann algebra A, still with a function f of A that has the same properties I stated. Since f of A prime equals f of A prime A, this function is usually called a trace. And I'll write it that way, I'll call it trace A. But it's not the trace of A in any Hilbert space representation. It's more like a renormalized trace with an infinite factor removed. Well, there's a more elementary example you all know of infinite dimensional algebra with a trace. That's the type 1 algebra B of all operators on an infinite dimensional Hilbert space curly H. In this example, however, while we can define a trace on elements of B, it's not defined for all elements, only for those that are trace class. For example, the identity element of B does not have a trace, unless you want to allow infinity as a possible value of the trace. By contrast, from the infinite set of qubits, we constructed an algebra A in which every element has a trace. So clearly, it's an essentially new type of algebra. In fact, it's the simplest type 2 algebra. It's said to be of type 2-1. It was first constructed by Murray and von Neumann. If A is this type 2-1 algebra and B is the type 1 algebra of all operators on an infinite dimensional Hilbert space, then we can make a third type of algebra by just taking their tensor product. It still has a trace because each factor does, but it's not defined for all elements because of the factor of B. In fact, C is a new kind of algebra said to be of type 2 infinity. It turns out that A and C are the important types of type 2 algebras for our applications. C is related to the black hole. A is related to de Sitter space. The thermofield double of almost any non-zero Hamiltonian leads to an algebra of type 3 in the thermodynamic limit. The simplest case, well, you could take almost any Hamiltonian. It can even be a sum of simple single qubit operators, like this one. Take this operator in a single qubit. The sum over that of infinitely many qubits will lead to a type 3 algebra. At inverse temperature beta, this is the thermofield double state. We can still define a thermofield double state by entangling each qubit pair in this state. We can define the function f of a, and as before, it has a thermodynamic limit. The important difference is that f of a prime is not equal to f of a prime a. For n going to infinity, you can define an algebra a naught of operators that act on any finite set of qubits, and its completion is a von Neumann algebra of type 3. So this is perhaps the simplest construction due to Powers, Rocky, and Wood of type 3 algebras. Algebras of type 2 or type 3 do not have an irreducible representation in a Hilbert space. Whenever such an algebra acts on a Hilbert space H, it always commutes with another algebra of the same type. For example, we constructed our type 2 and type 3 algebras as algebras of operators on the A part of a bipartite system AB. So in that construction, they commute with an identical algebra that acts on system B. The difference between a type 2 algebra and a type 3 algebra is that a type 2 algebra has a trace and a type 3 algebra does not. Moreover, in a type 2 algebra, the trace is non-degenerate in the sense that the function AA prime equal to trace of AA prime is a non-degenerate and positive definite bilinear form on the algebra. So if f of a is any linear function on the algebra, then f of a is the trace of a times a prime for some unique a prime in the algebra. Now let's go back to the situation considered by Sorkin. B is the region behind the horizon, A is the region outside the horizon. We consider some state psi of the whole universe. Suppose it were true that physics in region A is described by a type 2 algebra, curly A. Then the linear function that takes A to its excitation value in the state psi would be equal to the trace of A times rho A for some rho A in the algebra. If the algebra were of type 1, we would use this condition to define the density matrix rho A of the state psi for measurements in region A. So it makes sense to call rho A the density matrix also in the type 2 situation. Once we have density matrices, we can define entropies. The entropy of region A would be minus the trace of rho A log rho A. So if the region outside the horizon is described by a type 2 algebra, then we can define an entropy for this region. As I've already explained in ordinary quantum field theory, the algebras of regions are of type 3. But it turns out that when we include gravity, things are different. Gravitational effects, even for very weak coupling, convert the type 3 algebras into type 2 algebras. The mathematical mechanisms that lead to this are quite simple and have long been known by operator theorists. What's new is only that these mechanisms are actually implemented by perturbative gravity in the field of a black hole or de Sitter space. The details are different in the two cases, and I only have time for very brief explanations. So here's a Penrose diagram of the maximally extended Schwarzschild black hole in asymptotically flat spacetimes. As discovered by Kruskal, Sakaras, and others, there actually are two asymptotically flat regions. So there are two regions at spatial infinity. And the diamonds labeled A and B are the regions causally accessible to an observer at spatial infinity. So our two regions, A and B, are simply the regions outside the horizon on the right or the left. The black hole is a wormhole that connects two asymptotically flat universes, the two systems A and B. In low energy effective field theory, we would construct a Hilbert space curly H that describes fields in the black hole spacetime. It's acted on by algebras curly A and curly B of operators in the right region and the left region, respectively. Two important operators are the ADM energies HR and HL measured on the right or left sides. Another important operator is the bulk operator H that generates the killing vector field of this spacetime, the time translation symmetry, which moves time forward on the right and backward on the left. These operators are related by the fact that curly H is beta times the right Hamiltonian minus the left Hamiltonian, where beta is the inverse of the Hawking temperature. There is a subtlety, however, about constructing the Hilbert space curly H of gravitational fluctuations. If we only look at gravitational fluctuations that can be measured locally, we get a Hilbert space H naught of graviton modes that's similar to any usual QFT Hilbert space. An algebra AR0 of observables to the right of the horizon acts on H0. So little r is because these are operators on the right, and 0 is because these are operators that act on the part of the Hilbert space that parameterizes modes that can be measured locally. This is a type 3 algebra as if gravity were any other quantum field. But there's one more mode of the gravitational field that isn't locally measurable and that isn't included in H naught. It's a relative time shift between the left and right-hand sides of the black hole. When you construct a Hilbert space, you consider all initial data on a space-like hypersurface S, modulo diffeomorphisms of the space-time associated to that data that vanish at infinity. The equivalence relation involves only diffeomorphisms that vanish at infinity. So it's possible to have a perturbation, which would be the equivalent if you allow diffeomorphisms that don't vanish at infinity, but is physically non-trivial because you only impose equivalence under diffeomorphisms that vanish or trivial at infinity. So the Hilbert space of gravitational fluctuations in the black hole background is not the one H naught of only locally measurable perturbations. There's one more possible type of fluctuation that's not locally measurable. There's a relative time shift delta between the left and right-hand sides of the black hole. Because you might have initial data which are standard at infinity, and by a diffeomorphism that shifts the time at infinity on one side by an amount delta with the equivalent to standard initial data. But that delta is physically meaningful. You can't remove it by diffeomorphism that's trivial at infinity. So the Hilbert space is really the naive one tensored with L2 of R, where R consists of functions of the time shift. Using the time translation symmetry of the black hole background, you can reduce to the case that the time measured on the right side is 0, and the time measured on the left side is delta. So compared to the ordinary quantum field theory in the black hole background, gravity in the black hole background has a slightly bigger Hilbert space, where you add this little thing. Likewise, in gravity, there's one operator measurable by an observer on the right that doesn't have an analog for ordinary QFT. That's the ADM mass HR measured at infinity. So this formula that little h is beta times HR minus HL, well, we can solve it for HR. HR is 1 over beta times little h plus HL. That formula is now key. This is the one extra operator that you wouldn't have in ordinary quantum field theory in the black hole background. The operator HL shifts acts by shifts of the time shift variable. Up to a unitary transformation, we can assume that's all it does, because if it does anything else, where XL acts on the big part of the Hilbert space, we could remove XL by a unitary transformation. So up to a unitary transformation, HL only acts on the extra bit of the Hilbert space. So now consider this formula. On the right, H over beta only acts on the big part of the Hilbert space. HL acts only on the little part of the Hilbert space. To use a fancy language, H is what's called the modular Hamiltonian of the Hartle-Hawking state in H0. And as was first explained by Sewell 30 years ago, following previous authors, this is a fancy way to describe the fact that the black hole has a Hawking temperature 1/beta. I use the fancy language because I'm about to make contact with what people in operator algebras say, and they use this fancy language. See, what's the algebra of observables to the right of the black hole? It's generated by the ones you'd have if gravity was an ordinary quantum field. But there's one more operator, which is this 1/beta times the modular Hamiltonian plus something that acts on the extra bit of the Hilbert space. What we've just rediscovered is what's called mathematically the cross product of the algebra AR0 by its modular automorphism group. This construction was introduced half a century ago by Takasaki and Kahn, who discovered that if you start with the type 3 algebra, this construction gives a type 2 algebra. From their point of view, they wanted to study type 3 algebras. This was difficult. Type 3 algebras are harder to study than type 2 algebras. This way of constructing a type 2 algebra from a type 3 algebra gave a powerful way to study type 3 algebras. So that's what they did with it. From our point of view, the cross product construction isn't something we introduced by hand because we want to study type 3 algebras. It's something that's spontaneously generated by gravity. The Kahn-Takasaki results can be reinterpreted to state that the algebra of observables outside the black hole horizon, taking gravity into account, is really of type 2, in fact, type 2 infinity. This gives a somewhat abstract explanation of why entropy is better defined in gravity than in ordinary quantum field theory, at least for the black hole, because there's a natural notion of density matrix and entropy for a state of a type 2 algebra. One can also show that up to an undefined additive constant, independent of the state, you can show that for any semi-classical state of quantum fields in the black hole background, the entropy computed using the type 2 definition agrees with the Bekenstein proposal A over 4G plus S out. Something rather similar happens in de Sitter space. So again, I've drawn the Penrose diagram for de Sitter space. The left boundary is the world line of an observer to whom the green region, the so-called static patch, is the causally accessible region. And the Gibbons and Hawking de Sitter entropy has been interpreted as the entropy that's appropriate to the observations made by an observer who can only see the green region. So we want to, in some sense, define an entropy associated to the green region. There's a killing vector field of time translations that's future-directed time-like in the static patch. It's past-directed time-like in this complementary static patch over here. Let H be the generator of time translations. In ordinary quantum field theory, we'd associate a Hilbert space H0 to a de Sitter space and a type 3 algebra A0 of operators in the static patch that acts on it. However, in a closed universe, the isometries have to be treated as constraints. Here we have a closed universe because a spatial section of de Sitter space is compact. It's a sphere. That means we should replace A0 by A0 super H, the invariant subalgebra of A0. Or at least the most naive idea is to replace A0 by A0H, the invariant subalgebra of A0, consisting of the H invariant operators. But that doesn't work. The modular automorphism group acts ergodically in the language of operator theorists, and A0H is trivial. The only way to get a reasonable answer is to include the observer in the analysis. As a minimal model of the observer, we consider a clock with a Hamiltonian that I'll call X. It's physically reasonable to assume the observer's energy is bounded below by 0, so I assume X is non-negative. Thus, the effect of including the observer is to modify the naive Hilbert space by replacing what it was before with what it was before tensored with L2 of R plus. R plus is the half line of non-negative X. So in this stripped down model of what it is to have an observer, including the observer means that we replace the naive Hilbert space by the naive Hilbert space tensored with L2 of R plus. Likewise, the algebra is extended from A0 to what I'll call A1. A1 is A0 tensored with all operators on L2 of R plus. I'm assuming that the observer can manipulate the clock in an arbitrary fashion, and therefore I'm assuming that the algebra of observables that act on the clock is the algebra of all operators on L2 of R plus. Finally, the constraint becomes the total Hamiltonian of quantum fields plus the observer. So the constraint operator is now H plus H of the observer. The correct algebra of observables, taking into account the presence of the observer, as well as the fact that we're in a closed universe, so time translations are constraints. The correct algebra of observables is this one, the H hat invariant part of A1, where this was A1. Essentially, by Takasaki duality, this algebra is of type 2-1, which means there's a notion of density matrix and entropy. And because the algebra is now of type 2-1 rather than type 2 infinity that we got for the black hole, there's a state of maximum entropy. The state of maximum entropy is the natural de Sitter state, sometimes called the Bunch-Davies state. The density matrix of the maximum entropy state is rho equals 1. This state has a flat entanglement entropy as first predicted based on the Euclidean path integral by Don Silverstein and Terova, though related ideas in a different formulation go back to Banks, Susskind, and others. Again, facts known from gravity can be recovered from the algebra. So if you assume the presence of matter in the static patch, that reduces, then you have to consider the generalized entropy, the entropy of the horizon plus the entropy of the matter. And the claim is that the existence of matter in the static patch always reduces the generalized entropy. And it reduces it by an amount that can be computed using the type 2-1 algebra. And when you do that, you get a formula that you can also interpret in terms of gravity. I should stress something I haven't had time to properly explain today. Entropy defined this way is really defined up to an overall additive constant independent of the state. That's because the trace in a type 2 algebra is really of a normalized trace with an infinite factor removed. And removing that infinite factor from the definition of the trace has the effect of adding a constant to all entropies. This is analogous to entropy in classical physics, which is defined up to an additive constant by formulas like dE equals TdS minus PdV. That formula enables us to define entropy up to an additive constant, but no better than that. And in classical physics, you can't do better. For example, in classical physics, you can't say that the entropy goes to 0 at 0 temperature, because it actually usually goes to minus infinity. To conclude, we learned that at the level of semi-classical gravity, it's possible to define an algebra A such that the generalized entropy, A over 4G plus the entropy outside, in the presence of a black hole or cosmological horizon, is the entropy of a state of the algebra. This algebra doesn't have pure states, so at this level there is, for example, no notion of a black hole microstate. Thank you very much for your attention.
Thank you, Dr. Witten. Thanks for finishing on time as well. So we can have some questions. Let me see. Okay, Robert Mann, please go ahead and ask your question, Dr. Robert.
Yes, thank you. Quite an interesting talk. one thing, your construction seems to depend in the case of the black hole, that it's an eternal black hole. So how would this work for a black hole formed from collapsing matter?
That hasn't been studied carefully, but I expect that there's an analog. You would define an algebra. First of all, let's see. I'm not good at it, but I'm trying to draw the Penrose diagram. The red part is the collapsing star. Then we would define an algebra for a late time observer who's making observations after a certain time. And you see, if we allowed all possible observations at all times, we would get a type 1 algebra and there would be nothing to say. Then there'd be a black hole pure state. Instead, we take a late time. I'm telling you what I think should happen, but this has not been worked out carefully. We would take a late time observer who only is allowed to make observations after a certain time. That would be a type 3 algebra. I should say that in the anti-de Sitter context, something like this was done by Leuthäuser and Liu. I should have mentioned their work because it was my inspiration, actually. Another person I should have mentioned was Aaron Wall, because well, his work is important background for some things I didn't really have time to explain. Going back here, we would define a type 3 algebra if you were doing ordinary quantum field theory in the black hole background. I believe with gravity, it will turn out to be of type 2 for similar reasons to what I said for the eternal black hole. But I don't have a proper argument to give right now. I'm only expressing what I think the answer should eventually be.
Okay, and if I can ask one other follow-up question, not a follow-up, I guess. There's no notion of pure state in this concept. So you say there's no black hole microstates. So you didn't say it, but would you say then that the search for black hole microstates is a fruitless task? There's no point in doing it, or could you comment further?
I'll tell you the most extreme possibility along those lines, which might be too strong a statement, but I'll make it anyway. I could imagine the following might be true. There might be a clash between having black hole microstates and having a notion of causality. To be able to say, when you say something is a black hole, that's a statement about the causal structure. That statement is precise classically, and it's precise in quantum perturbation theory around the classical limit. Actually, what I'm saying is clearest in the ADS-CFT correspondence if we had negative cosmological constant, where we understand more precise statements. So let me switch to the case of negative cosmological constant. Sorry. So here I've tried to draw the Penrose diagram. For finite n, we have microstates. We even understand what they are in principle. For infinite n, or asymptotic in 1 over n, we have causality. For infinite n, we have the classical Penrose diagram, and we can give a precise meaning to the statement that there's a black hole. If you head inward, you never reemerge. And that's also valid order by order in 1 over n. I think it's conceivable that for finite n, you can't give a precise meaning to the statement that the system is a black hole. And asymptotically in 1 over n, you can't give a precise meaning to black hole microstates. So I think there might be a kind of complementarity where you cannot simultaneously say in a precise fashion that something is a black hole and that it has microstates. That might be too strong, but that's the strongest statement I can imagine that might be true.
Okay, thank you.
Okay. Next, Durmush hocam. You can ask your question.
Can I have a question concerning the reduction from type 3 algebra to, change from type 3 to type 2 algebra? Is it because of the loss of time translation invariance, or loss of vacuum state due to the inclusion of gravity, or am I getting it wrong? Thank you.
It's related to the fact that time translation became a gauge symmetry.
Oh, I
So
see.
in de Sitter space, the crucial fact was that we have to interpret time translation invariance as a constraint, a gauge symmetry. And that happened because it was a closed universe.
I see. Closed universe and gauge symmetry.
For the black hole, something different happened, but it again happened because time translations were a gauge symmetry. Because time translations are a gauge symmetry, you can shift the right side forward in time relative to the left side. And that is the time shift mode.
It is
In
your
fact, maybe I
relative
shouldn't
time
explain
shift,
it that
huh?
way.
It is the relative time shift you are speaking. Okay.
Yes.
Okay.
So the relative time shift exists because time translations are a gauge symmetry. So for both the black hole and de Sitter space, the crucial difference from ordinary quantum field theory was that time translation invariance was a gauge symmetry.
I see. Thank you.
I'm suspecting that in general, an observer who is interacting with black hole and cosmological horizons, that the experience of such an observer can always be described by type 2 algebra. I mean, again, hoping might be a better word than expecting. That's the strongest statement of its type that might be true. But it goes well beyond what's been justified.
Can I ask a little bit more? If time translation is a gauge symmetry, then there is a gauge charge, so to say. Do you mean that the time at the right-hand side is different than the time at the left-hand side by this shift, essentially?
It can be, because there are separate Hamiltonians, H right and H left on the two sides.
I see. I see. Okay, thank you much. Thank you.
Okay, Dr. Constantino, you can ask your question.
Yes. Is it thinkable that type 2 algebras can be reconciled with classical thermodynamics by using non-additive entropies, which would contain von Neumann entropy as a particular case, non-additive entropies such as the Q entropy that has proved to be interesting in many physical contexts?
I doubt it, to be honest, but I think it might be. I think there might be something interesting to say about a classical limit of the type 2 algebra. I haven't been able to think of anything sensible, but a vague idea is that with deformation quantization, you would deform the algebra of classical observables into a quantum deformed algebra and smoothly go over from entropy, classical entropy that's only defined up to a constant, to type 2 algebra in the quantum theory. Okay, that's a pipe dream. Technically, I don't have any idea why anything like that is true or whether it's true, but I've imagined it.
Thank you.
Okay, there is one more question from the chat, Martin Rayner. Martin, do you want to ask your question, or I can read it from here? Okay, I think I can read it from here. It says, if QG degrees of freedom are finite indeed, cannot we have all consistent with type 1 only? Or what's the decisive argument for type 2 rather than type 1? Do I miss the essential?
Well, we were close to that in one of the previous questions. So, for example, in the context of ADS-CFT for finite n, we have an ordinary Hilbert space, there are black hole microstates, and there's a type 1 algebra for sure. If you ask, if you ask whether we are restricted in the black hole, if you ask why we're getting type 2 algebras, it might be because we don't know how to do the exact theory. But I believe it, as I said in answer to one of the other questions, that it might be that getting a type 2 algebra is inherent in having a description of the causal structure, where you can say in a precise fashion that you have a black hole. There might be a description like you suggest that manifestly has finite entropy in type 1 algebras, but in that description, there might be no clear space-time causal structure.
causal structure.
I don't know for sure, of course. Many of these questions are making me, are forcing me to make suggestions on things where I don't really know the answer.
Okay, are there more questions? I don't see anything on the chat. Okay, I think we have enough. So we are also in time to give a break. Thank you again, Dr. Wheaton. We are very happy to listen you here. Thank you. And now we are going to give a break for 1 hour and then continue the next section. Is there any announcement, Ekrem Hocam, or we just go to break?
I have no any announcement. I would like to thank Professor Erik Tarhan, Sergey Odinstov, and Professor Wheaton for their excellent talks. Program will continue. Thank you again.
Thank you. See you in a 1 hour. Bye-bye.
Yes. Okay, now you see me. Okay, finally. Okay. So
Okay.
if I put up can I put up my slides now?
Yes.
Yeah, let's see what's going to happen.
Alvin?
Can you see that? Does that work okay?
Alvin?
Yes, hocam. I sent you a message from the chat. Jem will join us soon.
I didn't see Jem.
Sorry?
I didn't see.
He's not here yet.
Join in a minute.
Yes.
But
are you able to see my slides?
Okay. No.
Not right now, no.
Please share again.
Can you see my slides?
No.
No.
Why?
I don't know. So you are sharing the screen, but they don't show up. Okay.
Okay.
I don't know.
I'm sorry. I can't share the screen. Oh, I should share the screen. Okay.
Yes.
Fine.
Yes. Screen or just where the slides is.
Got it. Okay.
Yeah.
I understand. So now the question
you are
is
a
which one
co-host, so yeah, you have the privilege.
I see. Okay. Let me see if this one works.
Yes.
Okay. 1 second.
Yes.
Does this work?
Yeah. We are seeing it now, but I think you can make it to full screen because we are not seeing you. I don't know what you intend to do. We are seeing your view where the slides are small.
You're saying at the presenter view, you mean?
Yeah.
Okay. Tell me if this works.
No, this is what we are supposed to see. Thanks.
Okay, good. So you just see the single slide, right?
Yeah.
Great.
If you move just one forward so that we can check that. Yeah, it works fine. You can go back. Thanks.
Okay, very good.
We can start, Fethi. You can introduce Paul.
Okay, sure. Maybe I thought we could wait for a minute, but we can just start. We are very happy to have Professor Paul Steinhardt from Princeton University. Professor Steinhardt got his PhD from Harvard, and then after a few positions, he joined Princeton University over 20 years ago. And he was there when I was there, a PhD student. Now I could go on to, I go and tell you about how many papers he published, how many citations he got, but he doesn't really need that kind of praise. If you studied cosmology at all, you know Professor Steinhardt. He was at the center of ideas about early cosmology, back many decades ago about inflation, and then he got some other ideas. And if you actually follow the current developments in the field, you would always see his name on different sides of the arguments. And even more surprisingly, which is not very common today, it was common 100 years ago, but cosmology isn't the only field he works on. He's also pretty well known for his work with quasicrystals, which is not something directly related to cosmology. So he's a person of many interests. We are very privileged to have him. I won't speak any longer. Welcome, Professor Steinhardt.
Well, thanks. Thanks very much for the kind introduction. It's good to see you again. Yeah, so my goal today is going to be to point out a number of basic common misconceptions in cosmology that are pervasive today. You can find them in papers. They're published in textbooks. We teach them to our students. By recognizing these misconceptions, my hope is that you can detect some of the flaws in our current thinking in cosmology, and also recognize that there are opportunities to find new ways to explain the observed properties of the universe. Now, because we're going to be talking about very basic principles, this talk is going to be, in some sense, remarkably simple. I'm hardly going to need an equation to make my basic points. At the same time, I think most of you will find some surprises in what I'm going to say. So let's begin with the basic framework that underlies all of cosmological thinking today, namely the Big Bang Theory. So if we're going to be talking about rethinking cosmology, what about the Big Bang Theory? Well, we have to be careful because there's an abundant amount of empirical evidence for the Big Bang Theory. Most cosmologists would agree, including myself, that this is the case. However, it's also important to recognize that there's not a shred of empirical evidence for the Big Bang. So it's kind of a strange situation where there's lots of evidence for the Big Bang Theory, but not for the Big Bang. How can that be? Well, it's because the Big Bang Theory really combines two different ideas, which are merged together into one. But the two ideas are in very different standing in terms of empirical evidence. The first idea is that the observable universe was once smaller, hotter, denser, and has been expanding and cooling for the last 13.8 billion years. For this, there is lots of evidence, beginning from Hubble's observation of the expansion of the universe, to the discovery of the microwave background, to studies of cosmic nucleosynthesis. And these allow us to trace the evolution of the universe back in time from the present to when it was much smaller and much hotter than it is today. In fact, back to a time that is roughly 1 second after the beginning of expansion, when the temperature of the universe was about equal to that of at the core of the sun, hot enough to fuse together protons and neutrons into nuclei. And in fact, we can stretch our empirical evidence back even further than this, using the tools of particle accelerators to simulate some of the conditions in the early universe. But even that only allows us to stretch back a little bit further. If we want to get to the Big Bang, we have to extrapolate back much further than this. So that's the second idea. The second idea we associate with the Big Bang Theory is the idea that the universe began with the Big Bang. But that takes us to temperatures which are more than 15 orders of magnitude higher than anything we can test empirically, or to densities that are 60 orders of magnitude higher. So really way beyond what we actually can test experimentally. And in getting to the Big Bang, we have to take for granted that there's no fundamental changes in the laws of physics, in particular, the laws of gravity, even as we extrapolate to extraordinarily high densities and temperatures, way beyond anything we can test today. So that's why it's possible that there can be lots of proof for the Big Bang Theory, but none for the Big Bang. In fact, probably the first time you came across the Big Bang, you already had the first impression that it's a sketchy idea. We're so trained to think about it since childhood that maybe it's just become ingrained in us, but it is a kind of sketchy idea, the idea that there's some event, there's some physical event which has an after but not a before. It's a very strange idea. We know really of no other phenomenon like it. Of course, mathematically, it's a singularity. it's actually a sign that the equations that we're extrapolating back in time have broken down in some way and need to be improved in some way. There have been lots of speculations about what that really means. A common view is that we should be able to follow the evolution of the universe back in time far enough that the density reaches the Planck density, where quantum gravity effects become important. Everything in the universe that couples to gravity, which is everything, is strongly coupled to strongly coupled to themselves and to each other, producing wild quantum fluctuations in space and time and matter and energy distribution. Now, exactly what this phase is like is a subject of some debate. There are various terms or various ideas that people have introduced. They go under names like quantum foam, emergent space-time, tunneling from nothing, the no boundary proposal. I think it's fair to say there's no accepted theory. If we hold to the general idea that this initial state is some sort of quantum entangled state, we don't even have a firm idea of how we can undergo a transition from this quantum state, this quantum universe, to the classical universe described by Einstein equations, as we need to describe the rest of the history of the universe. Now, my goal today is not to debate which one of these pictures of the Big Bang is correct, but rather to make a more general argument that a Big Bang followed by expansion can't explain the most apparent salient features of our universe. So the Big Bang itself is a problem for cosmology in a deeper sense, not just that it's a singularity, but that it actually prevents us from explaining things. What I have in mind when I say the salient features of the universe, I mean the most apparent features that we observe. For example, when we look at an image of the cosmic microwave background radiation, a snapshot of the conditions in the universe, roughly 400,000 years after the beginning of expansion. We're familiar with this kind of plot from the Planck satellite and similar earlier ones that we obtained from earlier satellites, which show the distribution in temperature, the tiny variations in temperature across the universe, across the entire observable universe, back at a time when the universe was about 13.8 billion years younger than it is today. Now, the picture is meant to emphasize tiny variations in temperature compared to average. For the purposes of this discussion, I'm more interested in the average. I'm not interested in the small variations. And what's most apparent when we remove those small variations is that we have a universe which is remarkably homogeneous. We have a universe which is simple geometry, a spatially flat or Euclidean geometry where the sums of angles of triangles is 180 degrees. We have a universe which has a remarkably small entropy, a very low entropy compared to the total entropy available to it, exponentially smaller than the total available to it. And that entropy is strangely partitioned. There's hardly any entropy in the space-time or gravitational degrees of freedom. On the other hand, the matter and radiation is in thermal equilibrium, which means that it is at maximal entropy or near maximal entropy. So how is it we have this strange partitioning, almost none in the gravitational, lots in the matter radiation? And of course, this phase is well described by classical physics with small quantum corrections. And if you think about these 5 properties, they're everything the Big Bang is not. The Big Bang is inhomogeneous, curvy, high entropy, all degrees of freedom are excited, there's no partitioning, and it's inherently quantum. And so the question is, how do we get from this beginning to what we see in the microwave background? Now, this problem has long been recognized, and it's led to the idea of trying to amend the Big Bang picture by introducing a kind of band-aid that we call inflation, a rapid period of rapid accelerated expansion that lies between the Big Bang and the cosmic microwave background radiation, the part of the universe, the stages of the universe that we can test empirically. The question we want to ask today is, questions I should say we want to ask today are, does this Band-Aid do the job? And are there other possibilities worth exploring that might do the job better? So I want to go over carefully the various principles that underlie our thinking of inflation and how it works, and talk about alternatives. So let's first of all think about the flatness problem. Let's for the moment assume we have a homogeneous universe, and we're asked to explain how inflation flattens the universe. So ask yourself, how do you explain this to yourself, or how do you explain this to a student, or how do you explain this to a colleague who has never heard about inflation? I would bet for most of you, you bring up the kinds of figures I'm showing you here. You think about an inflating balloon. It even has the word inflating in it. And as I inflate the balloon, the radius of curvature of the balloon becomes larger and larger, or the curvature on the surface becomes smaller and smaller, or closer and closer to flat. This is what we often teach our students, and maybe we even teach ourselves or convince ourselves that this is the correct picture. The problem with this explanation, though, is that it's wrong in a very fundamental sense, as I'll explain. And it's not only wrong, but it misleads you into believing that expansion is essential to flatten the universe. And that's just not true. So let me explain. To do so, I have to introduce a tiny bit of general relativity, in fact, in simplified form, in the form of the Friedmann equations. So there we have a scale factor, A of t, which describes the amount of expansion, or characterizes the expansion as a function of time. It's a coefficient of the space in the Friedmann-Robertson-Walker metric with conventional space and time coordinate choices. It represents, it's a coefficient of, A squared is the coefficient of the spatial part of the metric. And substituting the Friedmann metric into the Einstein equations, we get the Friedmann equation, which I've shown you on the second line on the left. On the left-hand side, we have the Hubble parameter squared. On the right-hand side, we have a sum of different contributions to the energy density of the universe, each of which depends on different powers of the scale factor, or more precisely as inverse powers of the scale factor. The power is 2 epsilon I, where epsilon sub I is equal to 3/2 times the quantity 1 plus the pressure over the energy density of that component. So here we're treating the universe, as we commonly do, as if it contains separate components, each of which has its own epsilon, or its own equation of state. And then we can also have a curvature term, which goes like the k over a squared. Now, I'm going to be talking about expanding universes and also contracting universes. Let me emphasize that Einstein's equations don't know anything about whether the universe is expanding or contracting. The same equations apply equally well in either case. Whether or not the universe is expanding or contracting is something we, when we produce models, set as an initial condition. I can start with it contracting, or I can start with it expanding and study what goes forward. But the important thing is the same equation applies. When we talk about the evolution of the universe goes through different stages where one or more terms on the right-hand side end up dominating. For example, there might be a phase when radiation dominates. Radiation has epsilon equal to 2, or matter dominates, which has epsilon equal to 3/2, or dark energy dominates, which has epsilon equal to close to 0. So we can think of the universe as going through different periods, in which one or more components, one component dominates over the others for a period, depending upon the particular powers and the particular ratios of densities we have to begin with. In particular, if we think about one particular term dominating, let me just I may not say which one for the moment. Let's just suppose it has some density rho and some equation of state epsilon. We can rewrite or simplify or break down the Friedmann equation to this very simple relation, a relationship between H inverse, A, and epsilon. In other words, it tells us something, this relation tells us something about the geometry that's encompassed in the scale factor A, something about the composition of the universe that's encompassed in the exponent epsilon, and on the left-hand side, how that affects the expansion of the universe, or what I've written in this combination, the speed of light times h inverse, that tells us something we call the Hubble radius, essentially the scale over which causal interactions or dynamical interactions can take place. And this very simple relation is actually all we need to understand an awful lot about the issues, the fundamental basic issues and misconceptions about the universe, because it's telling us a relationship between the Hubble radius and the scale factor. To understand the universe, we have the evolution of the universe, both the puzzles and the solutions. This will be the key relation that one has to keep your eyes on. So now let's return to this picture over here. Okay, given what I just told you about the Friedmann equations, you can see what the problem is. This picture is only telling us about the geometry of the universe. It says nothing about what the universe is composed of, how fast it's expanding. Any kind of expansion would seem to do the trick. And what's in particular, what's missing is general relativity. What this balloon picture is telling us is a kind of naive Newtonian picture of flattening of the universe. Now, not how it really works in cosmology. Because in fact, in cosmology, we're really not interested in, or we can't even determine what is the true ultimate geometry of the universe. We can only measure the geometry of the universe within our Hubble radius. So what we are really interested in when we talk about the flatness problem is not the absolute flatness of the universe, something we can't determine, but its apparent flatness, its cosmological flatness, how flat it appears to be given the limited amount of it that we can observe. So consider, for example, an expanding universe. Here we see different snapshots from an expanding universe in which, let's say, we're matter dominated or radiation dominated. That corresponds to epsilon equals to 3/2 or 2. Important thing being, it's epsilon bigger than 1. Now let's consider the relationship we just described between the Hubble radius, roughly speaking, how far we can interact with or see, compared to the scale factor. If epsilon is bigger than 1, then what this is saying is that the Hubble radius is growing faster than the scale factor. Every time the scale factor doubles, the Hubble radius more than doubles. So for example, if originally we see only a section of the universe, a Hubble radius, which is given by this spherical cap, then the next picture, the universe has grown by a certain factor, the Hubble radius has grown by more than that factor. And if we repeat this again, it's grown by even more of than that factor. So it's true that geometrically, if we just think about the sphere itself, it's becoming less and less curved. To an observer who's able to observe within their Hubble radius, its curvature is becoming more and more apparent because the observer can see more and more of it and can, for example, more easily identify triangles, the sum of whose angles is greater than 180 degrees. This is why we have a flatness problem if the universe only went through phases since the Big Bang with epsilon bigger than 1, because by now, such a long time after the Big Bang, it should be very apparent whether that the universe is curved, and yet we don't observe any curvature at all. What happens with inflation? With inflation, the key thing is that epsilon is less than 1. This reverses the relationship between the Hubble radius and the scale factor. Now the Hubble radius is growing more slowly than the scale factor. For example, let's suppose epsilon is close to 0, which is the case as you get closer and closer to a cosmological constant or de Sitter phase. Okay, then the Hubble radius is actually hardly growing at all, while the scale factor grows a lot. So in terms of our picture, the Hubble radius hardly grows at all, while the universe is being stretched or is being expanded. And now we can see that within the Hubble radius, the universe appears flatter and flatter because we're seeing less and less of it. It's harder and harder to identify triangles, the sum of whose angles is greater than 180 degrees. This is what the flatness problem is about. And once you understand that the flatness problem is expressed in this way as a relationship between the Hubble radius and the scale factor, you realize there's now another way to flatten the universe. So as it's often said, inflation is the only way of flattening the universe, that's simply not true. Here's another way of flattening the universe that we call slow contraction. Slowly contracting universe is one whose pressure is much greater than the energy density, or whose epsilon is much greater than 3. In this case, when we look at our relationship, now we have the universe contracting. So you see our sphere is contracting. And so naively, you'd say its curvature is growing. But that's true geometric curvature. What we're interested in is its apparent or cosmological curvature. So because we have a situation in which the Hubble radius is shrinking faster than the scale factor, then in the next scene, the Hubble radius could be very tiny compared to the radius of the bubble, such that the universe appears to be, once again, flat to an observer inside the Hubble radius. And that is sufficient to solve the flatness problem. However, there's a difference, whereas that's worth noting, which is that the epsilon here can be quite large. And in fact, as I'll point out in a moment, it could be 50 or 100 or 1,000 very easily, which means that the amount by which the Hubble radius shrinks and every time the universe, let's say, shrinks by a factor of 2 in scale factor can be enormous. So it's a very rapid form of transformation from an apparently flat universe to one that is from apparently curved universe to one that is apparently flat. Now, you might be wondering, how do we get these funny equations of state about epsilon? In both cases, whether we're talking about inflation or slow contraction, we're talking about, in the simplest models, a universe which is dominated by a scalar field interacting through some potential via phi, in which there's an equation of motion which describes its evolution, which I've given on the second line, which is, if we think of phi as representing, say, the position of a ball on a hill, where the hill has a shape equal to v, it's describing the motion of that ball down the hill given by the shape of the potential. The middle term is an effect due to gravity known as Hubble friction. So that's all the ball or the field is subject to a gravitational friction force if the universe is expanding. Then H is positive, the universe is expanding. So that's the case, for example, that we have in the case of inflation. So here's a canonical example or sketch example of the case of inflation. We have some potential. We arrange it so that the potential has some rather flat plateau. We arrange it so that the field is slowly rolling. A field rolling down a potential, if it's homogeneous, which we're taking for granted for the moment, has a value of epsilon, which is equal to the expression I show in the slide. It's 3 times the kinetic energy of the field over its total. If we want that to be much less than 1, like we do for inflation, in order to explain the flatness problem, we want a field which is rolling slowly with small, as to say, we want a field with small kinetic energy. The closer it is to 0, the closer epsilon is to 0. And then inflation, the solution of the equations of motion, if in the limit that epsilon is slowly varying or constant, is that A grows as t to the power 1 upon epsilon, where epsilon is small, much less than 1. So it's growing very rapidly. That's a very high power of time. Now, what do we do for slow? What if we, instead of rapid or accelerated expansion, we want slow contraction? Well, of course, we're going to begin contracting rather than expanding. And in terms of potential, essentially the same potential could be used, except now we've changed the 0 point. Because in order to have slow contraction, we want to have epsilon much greater than 3. And in order to do that, you need the potential to be negative. You need to have some be rolling down some potential where it's negative. The moment it's negative, though, epsilon is definitely bigger than 3. You automatically, without doing anything else further, have a condition of slow contraction. And in the limit that the epsilon is slowly changing or nearly constant, we get a similar expression for A of t. Now we'll define our time coordinate. Instead of going from 0 going forward in time like we do for expansion, we have it go from negative to approaching 0, in which case it goes like the absolute value of t to the 1 upon epsilon. But the basic point is it doesn't take any more different physics for inflation than ingredients than inflation than it does for slow contraction, we just simply have to, we can use very similar ideas. Now, sometimes I'm asked, if we're going to have a condition of slow contraction where pressure is much greater than energy density, doesn't that mean we have to have some kind of superluminality? That's actually a myth. Slow contraction does not require CS squared greater than 1 any more than inflation requires CS squared to be imaginary. The idea that P over rho is related to CS squared comes from what one often calls in cosmology thinking about perfect fluids. A scalar field is not a perfect fluid. In a perfect fluid, CS squared, which is dP d rho, is equal to P over rho. But scalar fields are not really perfect fluids. They have some aspects in the homogeneous limit that remind you of them, but in particular, they do not have this relationship between the speed of sound and the pressure and energy density. For either inflation or for slow contraction, the speed of perturbations in the field are equal to 1. And having P negative, P over rho negative, or P over rho much bigger than 1 doesn't cause any physical problems whatsoever. Okay, so slow contraction is possible using similar ingredients. Here's another interesting little feature about slow contraction, is that in a certain sense I will describe, it is much more faster than inflation. So here I'm comparing two examples, inflation and slow contraction. In inflation, I'm expanding, I've taken my sphere and I've multiplied it by a factor of 2. In the case of slow contraction, I'm contracting, I've divided it by a factor of 2. In the case of inflation, as I go from the first picture to the second picture, the Hubble radius is hardly expanding at all. So this is what it would look like in the second picture. If I want to ask how much I flatten the universe, well, I can think of that as being determined by the ratio of the area of the spherical cap to the area of the sphere. So the spherical cap has not changed area at all. The surface area of the sphere has changed by a factor of 2 squared. So I flattened the universe by the amount of cap to surface area. I flattened it by a factor of 4. Now that's not enough flattening to flatten the universe. We need to flatten it by at least 60 eFols. So that's why you need to, so in fact, we need to repeat this many times over to have sufficient flattening for inflation. On the other hand, for slow contraction, I mentioned that epsilon can be quite large. Depending upon how steep the potential is, the steeper the potential, or it turns out that, the bigger the epsilon, and it's not difficult to get values of epsilon, which are 50 or 100 or 1,000. And let's just take the 50, for example. That would mean from the first image, the second image, the Hubble radius has shrunk, by the area of the Hubble radius has shrunk by a factor of, well, 2 to the 100th power. And the surface area is only shrunk by a factor of 4. So roughly speaking, the cap to surface area has been reduced by a factor of, well, 2 to the 96, but let's just round it to 2 to the 100. The point is some fantastically large amount. And so large, in fact, it's already enough to produce the flattening we need. So if the universe were to bounce at this point from the contraction to expansion, it would already be flat enough after a bounce to explain the flatness of the universe we observe today. That's what I mean by being much faster than inflation by this measure. So that's a curiosity, an interesting curiosity. Now, so far, though, we've just been assuming without any explanation that the universe was homogeneous. Now let's turn to the second big problem of cosmology. How do we explain the smoothness or homogeneity of the universe? We know it's a puzzle because when we look at the microwave background, assuming the standard Big Bang model without inflation, we have a picture in which the universe looks very homogeneous at the 400,000 year mark, at a time when the Hubble radius is tiny, about a degree apart on the sky. How do we achieve smoothness on scales much larger than the Hubble radius, sometimes called the Hubble horizon? We call it, in fact, the horizon problem. And the strategy of inflation, well, the strategy of inflation is to imagine that actually there was an earlier time when the universe we observe, the oval that I'm showing in the large, was actually smaller than the Hubble radius. Inflation begins with the observable universe smaller than the Hubble radius. It is presumed. because that would allow the possibility that there was causal interaction that would smooth the universe over that sub-Hubble scale. And then inflation comes along, and as long as we're sufficiently smooth, it will stretch the universe at an accelerated rate, much like stretching a rubber sheet. That's how we normally explain it to our students. That would smooth out the wrinkles and flatten the universe. Now, there's already a bit of a problem with that explanation about the stretching part of it, because often when we're thinking about the universe in that way, we're employing a metaphor in which we think about the expansion of the universe like stretching a rubber sheet. So you imagine a wrinkly rubber sheet, and then you stretch it, you can imagine it flattening out. But wrinkles in a rubber sheet, first of all, are fixed, can't get down to arbitrarily small scales. They're fixed by it's limited by the thickness of the rubber sheet. And furthermore, when you try to stretch it, as long as there are these loose wrinkles there, it doesn't resist the expansion, the stretching of the sheet. The wrinkles we're talking about in the universe are wrinkles in the distribution of energy, and they can occur in arbitrarily small scales, and they do resist the expansion or inflation of the universe because they correspond to gradient contributions to the energy density, which compete with the potential. So the actual, this picture is very naive picture, and it doesn't capture the right physics. And in fact, the problem with this explanation more generally is that, well, it's wrong. I've already given you a hint of that it's wrong. It leads you into believing that you need expansion in order to smooth the universe, that it's essential. It teaches that a region must be in causal contact within the Hubble radius first in order to hope to ever be able to smooth the universe on a large scale. And that's just not true. None of those things are true, not necessary. Now, in the case of inflation and expansion, we have the problem that we need to get, in particular, we need to get inflation to begin. That is to start. And the Big Bang poses a blockade for that in the sense that it produces a tremendous amount of inhomogeneity in the universe and a tremendous amount of entropy in the universe. And inflation, in order to start, needs a universe, a patch of universe, which is nearly smooth and has extraordinarily low entropy. So that's not going to be a typical region. If we're thinking about different patches of the universe coming out of the Big Bang, it's not going to be a typical patch. It's going to be a very rare patch of the universe, which is going to be sufficiently smooth for inflation to begin, sufficiently smooth within its Hubble radius for inflation to begin. So problem number one, inflation has a starting problem. It can only start in rare, nearly smooth patches. Now, some extremely rare patches will be so smooth to begin with that they can not only have inflation begin, but they can sustain it for 60 e-folds or more, what we need to explain observations. But for every one of those extremely rare patches, there will be rare but somewhat less rare patches which don't have quite good enough conditions. We will not end up with producing the amount of inflation or the conditions that we need to explain what we observe. But there'll be many more of them, exponentially more of them. And the same so for even less rare patches, which produce even less inflation and even less, take us further from the conditions we observe. So in this first problem we have is the part of the universe that matches up with what we observe is extremely rare. It will only occur can only have a chance of occurring in extremely rare regions. Then there's a second problem. Even if we focus only on those regions which are so smooth that they can give us more than 60 e-folds of inflation, there's not just there's a quantum effect, a quantum runaway effect that is well known, which leads to eternal inflation caused by that, created in that patch, and an uncontrollable patchy multiverse of outcomes, where literally anything that can happen will happen and will happen an infinite number of times. That means an infinite number of regions which are not as flat and not as smooth, they do not have the microwave background we observe, all those things will occur. And it's uncontrollable in the sense that once inflation kicks in, you'll inevitably get this runaway and this multiverse, leading to a situation where regions like what we observe, which are as remarkably smooth and flat as we observe, will not be typical. In fact, that's the bottom line. Smoothness and flatness in this kind of scenario is not the typical outcome. Something else, anything else, the sum of everything else is more typical. So it's not really explaining why the universe is what it is. It's saying it's possible, but it's not typical. That's a very strange kind of explanation, a scientific explanation for what is a very important, essential phenomenon in explaining the properties of the universe we observe today, the properties we observe in the cosmic microwave background. Now, since we've been talking about contraction, we might ask, what about the analogous problem in contraction? At first, you might think contraction is going to be much worse because we often naively think of contraction of the universe as being a lot like gravitational collapse. It's going to produce black holes. It's going to produce large gradients. It's going to produce a mess. But actually, that's a misconception. That whether or not the universe does that or does not do that depends on the composition of the universe. And generally, it's not generic that it will form anything that's like what you think of as gravitational collapse. This has been known since the 1960s, well, maybe even earlier than that, from the foundational work of Lifshitz and then Belinsky, Kalatnikov, and Lifshitz through the 70s. So, in fact, what happens depends upon whether you're fast contracting or slow contracting. Let's talk about the case of slow contraction. To analyze what's going to happen now, we have a challenge. What we really want to ask is, suppose we begin with a universe which is not at all smooth. It's very far from Friedman-Robertson-Walker. Is it going to evolve to be smooth and flat or not? For this purpose, we can't use the usual tools that cosmologists have been using up until recently. We can't use cosmological perturbation theory to answer the question, because that already assumes the universe is nearly Friedman-Robertson-Walker to begin with. Instead, we have to use the full power of general relativity. 10 nasty coupled partial differential equations for the gravitational part, plus additional equations for the, let's say, the scalar field and any additional forms of matter energy you have. And that's not something that can be analyzed. This kind of nonlinear coupled equations is not something that can be analyzed with pencil and paper. But fortunately, we can adopt the tools that were developed to study collisions of black holes, mergers of black holes, several decades ago. We can adapt that technology of numerical relativity to study what happens in a wildly inhomogeneous, anisotropic, highly sheared universe, as I'll show you briefly in the simulations here. This foundational work of transforming the techniques of numerical relativity to cosmology was pioneered by Anna Iosh and appears in a series of papers that have been published in the last few years. I'm just going to show you a few excerpts from it. In this case, I'm going to be focusing on a certain slice through space-time, okay, as a function of time, in which we begin initially with a distribution of shear or anisotropy, which when we normalize compared to the total energy density, its spatial distribution is given by that upper sheet that you're seeing. I hope it appears in greenish. So the universe is dominated by shear. It's far from FRW, highly nonlinear. There's also curvature. That's the red surface, how that's distributed. There's also what I called matter here, but which is actually let's see, one second. There's also what we call matter here, which really means the scalar field in this case. And by evolving these equations forward, Anna was able to study what happens to the relative distribution of these components as the universe evolves, even though it begins as far from FRW, very, very far from Friedman-Robertson-Walker. We have a time grid on the bottom. That's measuring how much contraction has taken place as measured by how much the Hubble radius has shrunk. Beginning from today, if the universe were if we're beginning from the size of the universe today to a microscopic size, the universe might contract, let's say, by 100 or 100 more than 100 e-folds. The time here is measured in e-folds of contraction. So we want to see, does it ever smooth out, and how long does it take? Okay, it takes about 2 years to set up all the mathematics as well as the physics for this. The simulation, though, will run in just a few seconds. And Anna likes to describe it as the most difficult and boring simulation that you're likely to see, for reasons you'll see in a moment. Keep your eyes fixed. Here it goes. That's essentially the end of the action here. What's happened is we started off with shear dominating and curvature dominating in some sections, but already after just a few instants, it seems like the universe has worked its way back to a condition. Yeah, 1 second. That's what I want to try to do.
Professor, we have 10 minutes, just as a warning.
Yeah. So let me show it again. Oh, sorry. Here we go again. Watch closely, and you'll see that it takes hardly any time before the blue sheet has risen up and taken over. There it is. The universe is flat, and we've only gone a small fraction of the total amount of smoothing that can occur. What we see is that this is a remarkably fast and powerful smoother. And if I'd used, and here we're using a rather modest value of epsilon, if we'd used the value of epsilon equals 50, you wouldn't have even captured a frame of this. It would have been smoothed only after the first frame. And you might say, well, maybe that was a special example. Well, by now we've run literally thousands of examples with different initial conditions, some even wilder than what I just showed you. And even in this case, boom, the universe smooths. Now, what's interesting is not only that it smooths rapidly, but how it smooths. Because we had this idea going back to inflation that in order to smooth, you must begin with regions which are first within the Hubble radius, smooth them out, and then spread it out. But what's happening here is something quite remarkably different. What you're observing is that the universe is actually smoothing everywhere, even on scale, even stretched over scales way beyond the Hubble radius. The Hubble radius is small compared to the size of the box I'm showing you. This is possible in contraction. It's a feature of contraction that does not happen related to contraction, does not happen in expansion. As Belinsky, Kalatnikov, and Lifshitz showed, what happens when you're contracting is that instead of having a going normal gravitational collapse where gradients are becoming large, the opposite is happening. Gradients become irrelevant. Physics becomes ultra-local. The couple of partial differential equations, in the couple of partial differential equations, all the gradients terms become irrelevant, and every point operates according to the same local equations of motion. What happens depends upon whether you're fast contracting or slow contracting. Mikhail only studied the slow contraction phase, assuming matter and radiation were the only components. And in that case, what they found is a mess. The shear components drives the universe into what we call chaotic mixed master behavior. And so what one ends up is a universal mess, something we don't want. But it turns out if you make epsilon greater than 3, it's like a phase transition. Behavior is entirely different, as you saw. And what you see is that every point eventually comes attracted to the same Friedman-Robertson-Walker universe. What you're seeing here is the first example of true universal smoothing. That unless you have some region which is going to locally form a black hole, which will form a set of, in volume-wise, of negligible measure, what you end up over here is a universe which is smooth everywhere, which is, if you want to explain why the universe should be smooth, this is an explanation of why it is so. Let me also mention another problem associated with the Big Bang, which I've already touched on, which is the double entropy problem. That coming out of the Big Bang, what we expect is all degrees of freedom, gravitational matter radiation, to be excited, but we don't expect, and so we expect to have high entropy, and we don't expect to have the strange partitioning that I mentioned earlier. And inflation requires the same thing as the cosmic microwave background. It requires the only important degree of freedom to be excited to be that of the inflaton. So also a state of low entropy and strangely partitioned entropy. This double entropy problem is going to be characteristic of any theory that includes a Big Bang. It's going to have to contend with this Big Bang double entropy production problem. So to summarize, what we've learned is that a universe that begins with a bang has, first of all, a double entropy problem. Explaining why we don't have very large, what happened to the very large entropy you'd expect to be produced at the beginning, and how it got how has it managed to get strangely partitioned? And inflation can't resolve it. Inflation needs it solved before it can start. So something has to happen before inflation, if inflation's ever going to begin. The Big Bang also produces a smoothness problem, and inflation can't resolve it for the reasons we discussed. It also has a flatness problem, leads to a flatness problem. There's no reason why the universe should be flat after coming out of the Big Bang. And inflation can't resolve that unless the universe is already smooth, and we can't yet explain the smoothness. In fact, the best we can do coming out of the Big Bang is produce a patchy multiverse in which our universe, the properties we observe, is actually unlikely to occur. A very strange kind of theory. And these are regions why it's time to rethink cosmology. And how you rethink it, I can imagine various directions it can go. But one obvious thing you might think about is getting rid of the Big Bang and replacing it with something else, something that avoids the quantum problems and the classical problems associated with the Big Bang. And the simplest example of that would be what we call a gentle bounce, a transformation from a universe that is first contracting, and before you reach the Planck density, transformed smoothly to a universe that is expanding, preserving the smooth and flat conditions that you produce during the slow contraction. So, putting the ideas together that we've heard about, slow contraction, that phase will produce a universe that universally and rapidly resolves the smoothness and flatness problems, and does not produce a multiverse because it doesn't involve any inflation. We need to connect it to the later universe, which we have empirical data for. To do that, we'll want to introduce a smooth transition, replacing the Big Bang, which would mess up everything, with a gentle bounce. A smooth transition occurs at temperatures and densities well below the Planck density. And that will resolve or get rid of this problem of high entropy production and the problem of having to have some sort of quantum to classical transition. And when the energy density that's driving the slow contraction finally decays into matter radiation and the universe so-called reheats, analogous to inflation, then we'll end up with a universe which is smooth and flat like we see in the microwave background, but has high entropy in the matter radiation, just like we observe in the cosmic microwave background. All this has observational implications. It first of all explains for the first time in a universal way the homogeneity and flatness we observe. It's not an accident of our region in the multiverse. It's a generic feature of the universe. It similarly explains the entropy problem, both parts of the entropy problem, the low entropy overall and why it's partitioned in the peculiar way we observe it to be. It also makes a prediction. Unlike the case of inflation, it doesn't produce detectable B-mode polarization. So key tests that are being performed right now in the Atacama Desert and elsewhere in the world are setting up to produce tighter limits on the B-mode polarization, and thus far, no detection has been found, consistent with what this picture would suggest. And if the bounce doesn't occur once, but occurs many times, both in our past and our future, that would mean the dark energy density of the universe cannot be a cosmological constant. It must be time varying. And furthermore, it cannot last forever. The acceleration error would have to come to an end. For example, in the cyclic type universe, it would have to come to an end, leading to a new bounce and a new period of expansion. And all this is just the tip of a very large iceberg. There are many other implications of these ideas, but let me stop here and ask for questions.
Thank you, Professor, for the talk. So you can raise your hand if you have a question. Okay, I'm looking at it. So Selim İlday, Selim Hoca.
I didn't have a question. I just I was applauding.
Oh, sorry.
Thank you very much for a crash course to cosmology and what's ahead. Thank you.
Thank you. Thank you.
Professor Mann?
Yes, hi, thank you. It was a very interesting talk, and it's nice to see a competitor to inflation, especially given the promotion we saw a couple of days ago with Andrei Linde's talk. So I'm just trying to understand the basic idea. I gather that the slow contraction phase, if you go backwards into the past, eventually reaches a maximum and is a previous universe. And so we've got sort of a perpetually bouncing universe. Is that right?
You have various options. The way I think about it is first to focus on what happened 13.8 billion years ago. Was that a bounce or was it not a bounce? Right now, it's perfectly consistent with the idea that it was a bounce. And as long as we don't see the B modes, it remains consistent that way. Now you want to go further back. You'd like to say what happened before then. Okay, and one possibility would be that the universe really is a single bounce universe. So it began very close to Minkowski, very nearly empty, with an arbitrarily large, infinitely large Hubble radius, shrunk down, bounced, and now we're going forward in time. But another logical possibility, which I find more compelling and more interesting, is the idea that you cited, which is that actually the bounce isn't a one-time event, but occurred repeatedly. And then it's, as you say, the universe would go through regular cycles of expansion, slow contraction, bounce, more expansion, slow contraction, bounce, etc. An interesting difference, though, is that unlike cyclic models of the past, where you imagine that the scale factor is going up and down in a periodic way, that's not what's happening here. It can't happen here because the contraction is so slow. What happens is we have the usual amounts of expansion, but then we have contraction. But I showed you that takes very little contraction to solve our problems. In the meantime, the Hubble radius has shrunk a lot. And we want to bounce the universe before the Hubble radius reaches the Planck scale. So after very little contraction, but a lot of space itself, but a lot of contraction of the Hubble radius, the scale factor bounces and begins to grow again. So over time, we go through a lot of expansion, a little contraction, bounce, a lot more expansion, a little contraction, bounce, going forward in time. So in terms of the scale factor, the universe is growing, whereas in terms of the Hubble radius, which determines the density and the temperatures and everything we actually measure and observe, that's behaving periodically. So it's a new kind of cyclic universe, which makes you rethink the traditional problems we associate with cyclic universes of the past. Those problems like the Tolman entropy problem or the crunching of black holes together to form a mess, none of that stuff occurs in this kind of scenario because of this slow contraction rather than what I called rapid contraction that was considered previously.
Okay.
Does that answer your question? Yeah.
Yeah, it does somewhat. Yeah. So, I mean, rather than think maybe of my own critiques, I'd say I thought it was a great talk, but with all due respect, cosmologists tend to be a bit like used car salesmen. They tell you all the good things about the model, but tend to hide the not good things. So what are the biggest problems this model faces? Or this approach faces, I should say.
You mean the physical problems, aside from the problems of trying to convince people to consider it.
Yeah, that's right. What are the challenges this model faces to get it to be better than it is?
Well, I'll tell you what is missing from both inflation and this picture, which would, to me, make a better model. So I mean, the way I view model building is we learn some things from each models, but we also learn what we're missing. What no model presently explains is, number one, the amplitude of the perturbations, and two, the tilt of the perturbations. It's often said, because the reason why I'm saying that is those are input into the model. When you build your model, you decide those things based on observations. They're not derived from the model. Now, it's often said that inflation produces a nearly scale invariant spectrum. So I know exactly where that idea traces from because I'm one of the co-authors of that paper. And what the paper said is you can design it to make it nearly scale invariant, but it doesn't force it to be nearly scale invariant because the deviation from scale invariance is determined by epsilon, and inflation only requires epsilon less than 1. The data is forcing us to epsilon to be like, I forget the current value, 0.002 or something like that, extremely small compared to what is required just to have your inflation. And in a similar way, we don't have a firm idea why the nearness to scale invariance in this case has to be so close to scale invariant as we observe. So that's a puzzle for me. An improved theory should explain that. And the amplitude of the perturbation is, of course, crucially important to the whole story. We wouldn't exist if the amplitude were too small, and the universe would be entirely different if it were much bigger. So it's a very important number to understand, but we put it in by hand in both cases. So there are definite things to improve in our model as they are, and the same issues apply to inflation. It's just that, so far as I'm concerned, we've learned enough about inflation now that its problems, it has more problems that we don't see here.
Okay, thank you.
Okay, thank you. Thanks for the question.
Hamza, you had a question?
Yes, thank you. Do you hear me? Yeah.
Yes.
Amazing talk. Thank you very much. A question about, you have mentioned the so-called apparent curvature when you were comparing the Hubble radius with the scale factor. Apparent curvature, is there a precise definition for that, or just you mean the measured, the one we can measure from the CMB?
Well, a way that might be more familiar to you if you're a cosmologist is what we call omega curvature. So omega curvature is the curvature k over a squared divided by h squared. But if you think about that combination, it involves an h and an a. So it depends on the relationship between h and a, the same one I showed you. So you can rewrite omega k in terms of a to a power 1 minus epsilon. Epsilon minus one, sorry. So if the universe is, and then you can rederive everything I said in terms of that omega k. So it's something we measure. We constrain omega k from the microwave background and combined with other measurements. But you can think of it as a ratio of the Hubble radius, but its growth with time, it reduces to it can be expressed as a ratio of the Hubble radius to the scale factor. And so how it changes with time, whether it grows or shrinks with time, depends upon whether epsilon is greater than 1 or less than 1, and whether the universe is expanding or contracting, which combination works.
So it's the same way we address the flatness problem in inflation.
Exactly. Yeah. So inflation, that ratio, so the ratio goes like a to the epsilon minus 1. So during inflation, you want omega k to be decreasing. So a is growing, so you want epsilon to be less than 1. There's that condition for inflation, okay? Now, if I'm contracting and I have a goes to epsilon minus 1, I instead want epsilon to be greater than 1. So it's the opposite of inflation. So in terms of the flatness problem, assuming homogeneity, there's an exact dual relationship between the two. It's just that if I'm, depending upon whether I'm contracting, expanding, I need epsilon to be greater than 1 or less than 1.
I see. Thank you very much. Thank you.
You're welcome.
We thank Professor Steiner again. Let me applaud him
Thank
for
you.
everyone. Now we are going on to the talk of. We are going on to the talk of Professor Capoziello. Could you share your screen, please?
Okay. May you see me?
No. Okay, Professor Steinhardt, could you stop sharing your screen?
Yeah, I'm getting there.
Okay, good. Thanks.
Okay.
We don't see your screen yet.
You can now?
No, we see just you.
Just me. Okay.
Yeah.
So now?
Okay. Yes.
Perfect.
Now we see your screen.
Perfect.
So let's test the.
May you see it?
Yes. Now we see it the way
also,
we are supposed to see
if I'm moving, is okay?
Yeah, it's going forward. Yeah, it's going forward.
Perfect.
So you can...
Perfect. Thank you so much.
Thank you. So let me introduce Professor Capoziello from University of Napoli. Professor Capoziello also works on gravity and related topics like cosmology and astrophysics, and especially today he will talk about the special interest of his, actually kind of an intersection of interest of his, cosmology and kind of alternative theories of gravity together. So we'll be talking about non-local gravity in cosmology. Professor Capoziello.
Thank you very much. Thank you very much for the invitation and for this really amazing Congress. My best congratulations. Okay, so what I'm going to discuss with you, I would like to discuss with you the fact that non-locality could have a very nice, a very important role in cosmology and in astrophysics, and essentially it could play an important role in order to match together the ultraviolet behavior of the universe, for example, the inflationary behavior from one side, and from the other side, the large scale structure, because the non-locality could in some sense lead the evolution of the universe at early time and at late time. Okay, so this is the outline of my talk. I would like to discuss a little bit what does it mean locality and non-locality in physics, and why from some years up to now non-local theory of gravity are gaining a lot of interest in the community. And in particular, I would like also discuss with you an approach, the so-called Noether-symmetry approach, by which it is possible to select some suitable model related with the fact that the symmetries and then the conserved quantities from one side give rise to the possibility to integrate the model, and from the other side they are connected with some realistic model. And then I would like just to present you some results in this perspective, where non-local gravity is leading cosmology from one side. We can have also some feature related with non-local gravity, considering the galactic center, and in particular the black hole, the Sagittarius A star. And then non-locality could be important in order to shape the form of the cluster of galaxies. And furthermore, I would like to finish this talk considering the fact that non-local gravity could have some interesting feature also in the gravitational wave physics. Okay, so very simply, what does it mean locality and non-locality? Locality means in some sense kinematics. It refers to the states. When you are considering the states, when you are considering some point in a given dynamics, in particular in classical theory, you are considering local structure. In particular, classical mechanics and classical field theory are strictly, and in particular also general relativity, are strictly local theory. On the other hand, as soon as you are considering at fundamental level dynamics, you need interaction, and then the interaction bring with them the non-locality. In particular, the Born interpretation of psi and the Heisenberg uncertainty principle give rise to the possibility to deal with non-locality into the dynamics. In particular, from a technical point of view, we have to compare local action versus non-local action. And when you are considering local action from a technical point of view, you are considering a functional of only local fields. And in this case, these fields run into the action as an algebraic function, for example, and their derivatives, for example, the classical mechanical Lagrangian or something like this. On the other side, the non-local action means that you have a functional with a non-local field that has to be at least one, and they are essentially related with some transcendental function and their derivatives. In this paradigm, in particular, you have to compare at certain point classical and quantum. So just to have a paradigm, classical means local and quantum means non-local. Then the problem, GR is a theory where you have a local definition, the observer, for example, or the event in the space-time, and quantum field theory needs, for example, the possibility to have to take into account non-local action. Okay, so in this perspective, what does it mean non-locality in physics? It means something very concrete. It means something, for example, related with the fact that you have a quantum entanglement, you have the uncertainty principle. So there is there is no possibility to localize the system during its evolution. So there is no unicity of the path when you are considering the initial condition. So non-locality is very, very present in physics. And in particular, from a dynamical point of view, you need, for example, that quantum field theory has to be formulated according to the prescription that, for example, at one loop level, non-locality comes out very, very straightforward. In this paper by Barbinsky, there is a very, very nice review paper in which there are all these aspects which are pointed out and discussed in detail. Coming to the details, non-locality in physics comes out also for very, very standard interaction, for example, the electromagnetic interaction. And in particular, if you consider the Euler-Heisenberg-Lagrangian, also in this case, as soon as you are considering the propagation of the fields, immediately you run into the non-locality. More technically, if you consider the Yukawa-Lagrangian and the related effective action, you cannot avoid the non-local operator, and this non-local operator has this form, which it appears as the inverse of the standard Klein-Gordon operator. So as soon as you are considering this kind of interaction, you need non-locality. In particular, the Euler-Heisenberg-Lagrangian and the Yukawa-Lagrangian are two very important cases where you can put in evidence the presence of non-locality. But non-locality could help also in addressing some shortcomings related with general relativity. Why? Because no theory up to now is capable of solving this problem, all this problem that I summarized here at once. For example, we have the universe accelerated expansion, we have the inflation, we have the galaxy rotation curve, we have the dark side, we have the fine tuning of cosmological parameters, we have the tensions in cosmological parameters at a large scale. At small scale, at ultraviolet scale, you need renormalizability, you have that GR cannot be quantized, and so on. So these are very, very deep problems and issues that should be, in some sense, enclosed into a comprehensive picture. And in particular, the fact that you cannot change your model starting from quantum scale up to very large scale. This is the main, from a conceptual point of view, the very, very important issues related with the non-locality. In particular, people is taking into account, for example, the fact that some assumption of GR can be relaxed. For example, the equivalence principle, the Lorentz invariance, the fact that the theory is strictly formulated with at second order in the field equation. And so there is a plethora of proposal, but the main point is that all these proposals has to recover, in some sense, the good results of general relativity that continuously is challenged, but in any case, it seems very strong to be completely ruled out. So, despite the fact that there are several shortcomings, general relativity remain a solid theory. And for example, the observation of the black hole, the two modes related with the gravitational waves and so on, says that in any case, general relativity has to be considered in any extension or modification of theories. In particular, I like to deal with the extended theory of gravity. Extended means that at certain point, you have to recover, or in some weak limit, or with a particular choice of the parameters, the general relativity. And in particular, there are a good trend in literature in which people are dealing with post-Einsteinian theories. Post-Einsteinian theories means that post-Einsteinian limit means that at a certain point you have to recover the standard picture that you have in general relativity, but it seems that this picture is not working at any scale. And in particular, here you have some theories where, from a local point of view, you can take into account extensions for general relativity. But in particular, you have to take into account non-local extended theory of gravity. And according to the literature, you can consider two main families. One family is the so-called infinite derivative theories of gravity from one side. From the other side, you have the integral kernel theories of gravity. And the definition is essentially related with the fact that one can use the box operator or the inverse of the box operator according to the IDG or the IKG theories. And you have to take into account some geometric invariant. In particular, you can consider curvature, torsion, Gauss-Bonnet invariants, and so on. So as you see, there is a huge amount of possibilities in order to construct some non-local theory which is related with the extension of general relativity. In particular, for example, if you take into account an infinite derivative theory of gravity, what is the paradigm? The paradigm is taking into account this prototype of non-locality. You have a general operator depending on the distance, which is this one. So as soon as you are considering an operator depending on the distance, you are taking into account some non-local theory. So the recipe is you have to take into account a Fourier transformation, you can get a reparametrization, and at certain point you get the theories that we have discussed before, the infinite derivative theories of gravity. From one side. For example, there is a very nice theory of gravity, which is this one, proposed in this paper by Bisbas, Gerwig, Koivisto, and Mazumdar, in which you have the most general gravitational action in 4 dimensions, where you can take into account the quadratic curvature and the ghost-free. And then, as you can see here, as soon as you are defining these terms, you are putting some length scale or some mass scale, and you can consider this transcendental and analytic function. Why you have to take into account this kind of situation? Because you can get two very, very interesting features. For example, you can get some super renormalizable and unitary theory. You can admit regular black hole solution. You can get, for example, the maximal UV complexion, for example, for the Starobinsky model. As you know, the Starobinsky model is very good tested according to the Planck data, and to the it seems a very good proposal for inflation. And in this case, taking into account this kind of correction, the Starobinsky model can be completed toward the ultraviolet scale. Okay, so at certain point, we need the possible classification, because as you see, there is a plethora of possibilities in order to take into account this kind of correction. And our proposal is very straightforward. If exists some Noether symmetry, this Noether symmetry can select physical models. Why this? Because the existence of symmetry is, in some sense, is a sort of paradigm that is working in any field of theory. And the interesting issue is that, according to this, let us try to see if it is possible to find out some model in which quantum correction from one side can also address the infrared behavior. So the purpose are to reconstruct a reliable cosmography and then compare with the dark energy, to get some physically motivated cosmological model, and then in particular, or for example, producing some non-local gravity black hole solution, and so on. So, what is the method that we are going to propose? Starting from the approach by this nice girl, Eminator, we can construct a one-parameter group of point transformation. When we can take into account an infinitesimal group generator. These are technical points, but I would like just to show you that according to this approach, it is possible to get really a lot of reliable model. And then, according to the Nether theorem, it is possible to fix some integral of motion and eventually to integrate the dynamics in order to see if such a dynamics is reliable or not, or is physically suitable in order to address the problems that we have seen before. So the recipe, if you want to summarize this Nether symmetry approach, we have to consider a class of point-like Lagrangian. Point-like because we need to construct some cosmological Lagrangian or some spherically symmetric Lagrangian, and we will see that these are sufficient in order to fix a lot of problems in cosmology and astrophysics. We have to write the ansatz for this Nether vector, and you can ask for the existence of the symmetry, and this is the condition for the existence of the symmetry. Apart from the mathematics that sometimes is quite cumbersome, the important results, the important point of this approach is twofold. From one side, it allows, as we will see in a moment, to fix some form of the Lagrangian. So the Lagrangian strictly depends on the presence of the Nether symmetry. And from the other side, it is possible to solve the dynamic and find out some interesting cosmological, for example, or black hole solution and so on. So with this recipe in mind, starting with this approach, let us try to see if it is possible to construct some non-local gravity cosmology. Some of the results presented here are taken by these two papers. So details, you can find out the details in these two papers. So there is an important case before. The important case is the so-called Deser and Woodard model. Deser and Woodard in 2007 proposed the possibility that by non-local cosmology, is it possible to solve the problem of accelerated expansion and then the dark energy issue. So they proposed a very minimal model in which you have general relativity corrected with some non-local term, and they noticed that the non-local term give rise to a sort of a retarded green function. So the retarded green function is capable to match in a very nice way the decelerated expansion with the accelerated expansion. And then, in some sense, it is possible to get a sort of radiation matter transition that end up with the current cosmic acceleration. So the paradigm seems very realistic. Why? Because non-locality, as we have seen before, comes out from quantum correction. If you remember, the action giving rise to the super renormalizability it is strictly related with the effective field theory, which can work in quantum gravity. But from the other side, according with this approach, it is possible to consider the fact that this retarded green function are capable of giving rise to this nice expansion mechanism. But starting from this, let us see from a very practical point of view how it is possible to work with this kind of model. And in particular, one of the approach proposed by Nogiri and Odintsov some years ago is extremely interesting in this perspective, because you need a sort of localization of the non-local degrees of freedom, and they pointed out that this localization gives rise to a farther scalar field. In some sense, we get the same approach that you have in inflation, or that you have with the quintessence, in which you get at certain point some extended theory of gravity where you have to take into account some further degrees of freedom which are related with the scalar field. But the nice news, the nice information in this is that we know the origin of this scalar field, which is strictly related with the non-locality and then with some quantum mechanism working in ultraviolet epoch. And in particular, what we have done, we have considered not only the Deser and Woodard model, which in some sense can be a very, very special model in which you take into account the general relativity and you just consider a term giving rise to non-locality. But we consider a sort of extension of f of r where you have this box minus r term, which is which give rise to the non-locality. So taking into account this formal localization, the good news is that at the end of the day, we get a theory, a scalar tensor theory, nothing more than a scalar tensor theory, where a particular role is played by this further scalar field, this new scalar field, which has the meaning of a sort of Lagrange multiplier acting into the action. According to this, you have a sort of mini superspace where the cosmological Lagrangian can be dealt with AT, which is the standard scale factor, R, which is the Ricci curvature scalar, and then these two fields where one is the Lagrange multiplier and the other one is the scalar fields coming from the localization procedure that we have constructed. However, after solving the dynamics, the main point is reversing the problem and then to take into account the inverse approach in order to recover the non-local behavior. So, coming to some technical point, we can construct the Noether vector. This is the Noether vector. I would like just to give you some hints because the calculation are a little bit cumbersome, but in the paper there are all the details. You get at the end some generator, and finally at the end of all this calculation, the presence of Noether symmetry is capable of fixing these two forms of Lagrangian. Why they are interesting? The first is interesting because it is nothing else but, for example, the Starobinsky model, if n is equal to 2 in particular, corrected with the non-local term, with this logarithmic correction, which is very useful in order to regularize the theory. While the other case is interesting because it is exactly the one used for the super normalizability of the theory. And then, in some sense, they have some physical meaning. So you can take into account, for example, the first case. You have a possible choice, which is this one, and finally the function became this one. So for n equal to 2, we get that the non-local extension of Starobinsky model is recovered by Noether symmetry. So you can reverse the statement, then the non-local Starobinsky model is working in a so nice way because the Noether symmetry are fixing this kind of theory. So it seems that the Noether symmetry can have a very, very nice role into this kind of approach. Then it is quite standard to take into account the dynamical system related with this kind of Lagrangian. You can work out the cosmological equation, and eventually it is possible to get some exact solution. And in particular, you have these two exact solutions. But the interesting point is that, for example, you can get, for example, radiation solution. And then immediately you have that the Deser-Woodard case is easily recovered. So what is the message? The message is that Noether symmetry fix the class of theories which are compatible with symmetries and then with conservation laws, and give rise to the possibility to work out the model and then eventually to solve. The same situation is possible also with the other model. With the other model, in some sense, we have that according with this M, we have several. In particular, we have all the Einstein-Friedman solution can be recovered according with this. As pointed out in these papers that I mentioned before, this case is interesting because it reproduces the above super renormalizable model, and then it seems that the super renormalizable model is compatible with the dark energy models. So, in some sense, also if we have to work a lot in order to really fix this statement, it seems that we have a good indication that from UV behavior up to the infrared behavior, we can adopt in the same model. And what is going on now? We started to compare this kind of behavior with the observation. And also in this case, we have some good news. In particular, in this paper, we consider the non-local teleparallel cosmology. In particular, we worked out this kind of theory where we used the teleparallelism, the fact that we are considering the so-called teleparallel equivalent theories of gravity. This is just a particular case, but it works also in metric theories. And in particular, you can see that there are good agreement between the observed data and at various redshift, and we are in a compatibility region also with the Q. Q here is the deceleration parameters, which is ruling the late cosmological expansion. So the perspective now is taking into account this non-local gravity model, try to see if they are capable of fixing constraints with respect to the data. Okay, but this is not the end of the story, because we can consider, for example, also astrophysical tests. And in particular, we have at hand some very, very interesting astrophysical tests which can be connected with the galactic center. And the recent picture of the galactic center, in some sense, could be really a treasure in order to give us a lot of possibility to get information from this very, very peculiar object. And in particular, what we have done. We have considered the same non-local action, but in this case in spherical symmetry, and we tried to model out dynamics around the Sagittarius A, considering, for example, the free parameter and constraining the free parameter by the S2 star orbiting around the Sagittarius A. 2 days ago, Professor Genzel gave us a very, very nice talk on this structure, and let us try to see if it can be really useful in order to select theories of gravity. In particular, we have pointed out that you can estimate a reduced chi-squared, and then emerges that we have a characteristic length which are related with the non-local gravity. So according to this length, it is possible to fix, in some sense, the theory. So what we have done? We have reproduced nothing else but the same scheme that we have seen before, but in this case, instead of taking into account a cosmological Lagrangian, we consider a spherically symmetric space-time, and we applied this nether symmetry approach to a generalized Desert and Woodard model in the same fashion that we have seen before. After some calculation, what you get is that the point-like Lagrangian, in this case depending on lambda and ni, reduce to this one. And the epsilon, it is the Lagrange multiplier that we discussed before, but now in spherical symmetry. So the solution. Also in this case, the Noether symmetry is capable to select a form of Noether vector and a form of theory. And in particular, this theory and this theory are selected by the presence of Noether symmetry. In particular, we restricted to a subclass of space-time, which are in some sense Schwarzschild-like space-time, and consider the feature coming that come out from the in the post-Newtonian limit. And this is the situation. The situation is that, for example, you have correction to this potential coming from the fact that non-locality introduce correction to the Newtonian potential. This is a quite obvious result, but it is interesting that this situation can be strictly related with the presence of non-locality. You can work out all this structure, and in particular, you can get the order of the potential up to the 6th order. And as you can see here, it is a quite complicated expansion, but it's not so complicated because you can see that at 2nd order, you recover the standard Newtonian potential, while at 4th and at 6th order, you get 2 corrections, and these corrections are related with some particular length, and we will see that this kind of length can be tested in some sense into the Newtonian, into the galactic environment. In particular, these 2 lengths are these R epsilon and R phi, and we have seen that we have simulated the orbits coming from this kind of length, and we have seen the Keplerian orbit, and we have seen that we have a good approximation from the standard Keplerian orbits, the GR orbits from one side, and from corrected non-local orbits. In particular, this is the good news according to us, is that these are, according to the simulation and to the data, this is important, you see that if you minimize the chi-squared, you get that the 2 lengths are of the order of the 1.2 and 1.1 astronomic units. And according to the people working in Event Horizon Telescope, they can be reached by their sensitivity. So this is nothing else but an indication. There is no final statement, but into the measurement that people in Event Horizon Telescope are performing, very likely there is room in order to get constraint from non-locality. It is interesting that this constraint can be immediately, as you can see in the second picture here, can be immediately compared with the GR measurement. Okay, so you can continue to develop this approach, and you can see if non-local gravity can work, for example, also for cluster of galaxies. In this case, we are to another scale larger than the galactic one. And also in this case, it seems that new corrections can be related with this kind of length that emerge from non-locality. In particular, we adopted exactly the same scheme that we have seen before. And also in this case, we take into account the correction related to the Newtonian potential. So the approach is exactly the same. And in particular, what we have used here, we have used the Clash survey. The Clash survey is the cluster lensing and supernova survey with Hubble. And in particular, we have fixed the non-local gravity parameters, taking into account the measurements of clusters reported by the Clash collaboration. And these are the results. We have considered, for example, the Lansing convergence, which is given by this formula. But in the Lansing convergence, we put the two potentials that I mentioned before, phi, which is the potential related with the Newtonian one, and the correction coming from the non-local terms, and we have estimated the order of magnitude for each contribution. So it seems that the length, the corrections strictly depends on the structure that we are taking into account. Just to give you an example, it seems that like the Schwarzschild radius is related with the mass of a given object, here the non-local radius is related also with the mass and the interaction that you are taking into account. So it seems that the non-local radius is a new feature emerging in this non-local lengths, which is not just one, but in this case are two, are related with the new with this length that can be fixed by the data. In this case, we consider the Navarro-Ferencke-White profile for the cluster, the standard one, and we analyzed how it is possible to fix the constraint for the non-local gravity in this feature. So these are just a technical slide in which I try to give you an hint of the methodology. We have used nothing else than the Monte Carlo chain, and in this Monte Carlo chain with a lot of iteration, we produce some mock data, and we take this mock data from this Markov chain and compared this with the real data. In order to fix these parameters. The parameters are essentially the concentration C200, the mass of the cluster, and the two lengths that we are taking into account. So it is nothing else but a standard analysis by which the theoretical Lansing convergence is taken into account. And this is the interesting feature. The interesting feature is the fact that the Navarro-Ferencke-White parameters can be essentially compared with these two lengths. And in particular, it seems that you have a sort of shift in the standard GR. And as you see, the shift is in some sense compatible with the observation. So in some sense, it seems that we are capable to reproduce GR, but with some error bars, and these error bars is strictly related with is not excluding. This is the right word. Is not excluding the non-local corrections. Okay, so finally, we can fix some bounds for this particular length scales, and in particular, these are the two bounds that we have fixed. As you see, we are improving a lot the length that we used for the galaxy. Why? Because the length are running with the scale. So since the scale is different for cluster, you have to expect that the scalar fields, the localized scalar fields, give rise to new length, new correction, essentially. And this is the statistic of some typical cluster that we take into account. So the message, it seems that gravity is not scale invariant, but the various scale can be ruled by the presence of these non-local terms, which give rise to structure at the galactic, large scale structure, and finally to the cosmological scale. And in particular here, you have how this new potential can be in some sense tested by the gravitational lensing. In the papers there is a detailed discussion of this. In particular, here you can see two particular clusters that we used into the analysis. Okay, since my time is going to finish, I would like just to present you a final check for this non-local gravity, which could be connected with the possibility that there are some polarization, some further gravitational modes, which is obviously related with the non-local gravity. And in these two papers, we described this feature. In particular, also in this case, we take into account a model related with matter symmetries, and according to this model, we can get a minimal model, and such a minimal model is nothing else but the Deser and Woodard model. And also in this case, we worked out the weak field limit, but in this case, the post-Newtonian limit, because we are taking into account gravitational waves. And finally, we get the field equations also in this case. And as you can see here, we have some further feature, which is related with the fact that the non-locality gives rise to some further modes. In particular, what you have seen is that beside the two standard modes related with the general relativity, we have this part of the dynamics, which can be in some sense modeled out as some further polarization. So in some sense, we have some massive modes which are related with the non-locality. This is obvious because these massive modes are related with a characteristic length coming out from non-locality. And in particular, we have seen that it seems that non-locality yields three additional polarization of this form. So it is just nothing else but a technical detail. But at the end, if you do all the calculation, it is possible to demonstrate that two of these further polarization can be absorbed into just one polarization. And at the end of the dynamics, what you have the two polarization related with the GR plus a scalar polarization, and this polarization strictly depends on the feature of the theory. In particular, if you remember, strictly depends on this A1 parameter. If you remember, the A1 parameter is the parameter which gives rise to the coupling with the non-local term. So the strength of this A1 parameter can be in some sense connected with the further polarization that you are obtaining in this new perspective. So since I think that my time is going to finish, finally, what is the main result? The main result is that non-local gravity exhibits a massive scalar gravitational mode in addition to the standard ones, the two standard ones. These additional gravitational mode comes from a straightforward extension of a general relativity, and this could be extremely interesting in order to test this kind of theory at fundamental level, because if a web of interferometers, which are going to be constructed, the LIGO, the Virgo, the Cagra, the Indo-LIGO, and so on, are connected and synchronized together, if they detect a further mode, and this further mode is a scalar mode, this could be, in my opinion, a very interesting hint in order to fix the non-locality terms. However, also in this case, we can enlarge and we can extend the approach and we can consider some more general model. So, concluding this discussion and summing up, non-local gravity, in principle, could reproduce ultraviolet and infrared cosmic evolution. Nether symmetries are nothing else but a tool in order to work out models. Is nothing else but a sort of trial and errors in order to see if you have some physically relevant models or not. But the good news is that some of these models, some of this selected model by the nether symmetry can track naturally the dark energy, and in particular the solutions can be matched with the experimental observation, and they are not ruled out by the observation. So the suggestion that let us try to see if also non-local models are interesting to be probed with observation, in particular with the forthcoming Euclid or with the other observations that are running right now. These are at a very, very large scale, while at scales which are nearby us, in particular at galactic scale, if you take into account, for example, S2 star orbits, this could be a very, very good tool in order to fix the potential, in order to fix the various features of the non-local gravity. In particular, we pointed out that at any scale, this characteristic length strictly related with the structure of this non-local terms comes out. It is interesting to see that these lengths are not universal, but they behave in some sense in analogy like the Schwarzschild length, in the sense that the Schwarzschild length strictly depends on the mass, and this strictly depends on the strength of the non-local terms. Finally, since non-local gravity provides, gravitational waves provide a further polarization, you can try to see if this could be a feature that can test the model at fundamental level. It could be, in some sense, a sort of prova regina of the approach, because if after some detection you have further polarization, this further polarization could be a good hint in order to suggest that non-local gravity could work. So perspective. From the perspective, we have several perspectives from a theoretical point of view and from the observational point of view. From a theoretical point of view, we can search for cosmological solutions which are consistent with the cosmic history, with the whole cosmic history. We can study renormalizability and the unitarity of the non-local gravity at fundamental level. We can search for some realistic black hole solution, which could be in some sense related with the non-local gravity, and in particular, this non-local gravity could be also developed in terms of quantum cosmology. From the observational point of view, in particular, if you improve the data set, the observational data set with supernovae, with the baryonic acoustic oscillation, and with the observational Hubble constant and so on, you can in some sense better fix the structure of this non-local model. Furthermore, you can constrain local scale using Keplerian physics in some sense, and one can refine the analysis of clusters, taking into account, for example, also dust, hot gas, Sunyaev-Zeldovich effect, and not just lensing as we have done in this preliminary paper. And in particular, the main point, it could be that a possible detection of further gravitational modes could be really an important hint in this perspective. Thank you for your attention.
Prepare flutter for everyone. So if you have a question, you can raise your hand and I can unmute you, ask to unmute you. Meanwhile, I can ask a question. So is the quadruple formula for the energy loss in gravitational waves the same for this theory? Because if it's not, then right, we already the pulsars which can test this theory directly without gravitational observations.
We are doing this. We are doing this. Yes, this is a very important point. So it seems just a general relativity, but corrected, nothing more. So this is the message that we have.
Okay. So there is another question from Behnam Hassan on the chat. Is it possible to extract from non-local gravity the quantum corrections of the black hole thermodynamics? For example, logarithmic correction on the black hole entropy.
Yes, yes. Benham is very expert of this. Yes, sure. In particular, we have also some common paper on this. The important point. Thank you, Benham, for this question. It is interesting that several of these models give rise to logarithmic correction. So logarithmic correction for people working in quantum field theory is a good feature because it is very good in order to regularize and finally renormalize the theory. So the fact that it emerges in most of these terms is good in order to set up some theory which is good at ultraviolet and at infrared scales.
Okay. Okay. He thanks you. Let me ask another question since there isn't another one I see here. So as far as I know, non-local theories, if you are not careful with them, even classically, can give you instabilities, Ostrogradski kind of instabilities. What is the magic here that prevents that kind of instability? I assume these theories are checked for it already.
So we have already checked this. It seems that non-locality, there are several papers on this. Some of them are by Sergei Odintsov, by Vasilis Economou, and they fixed this. And in some sense, we have several, not all, but several of these models are stable with respect to the Ostrogradski instability. So it seems that non-locality seems to, in some sense, to cure the Ostrogradski instability, as for example in the case of F of R. But if you consider F of R, which are avoiding F of R models, which are avoiding Ostrogradski instability, then the non-local counterpart are also avoiding the Ostrogradski instability.
Okay, thank you again. So if we don't have any other questions, then we are going to have a small break and we are going to meet at 21 Istanbul time. Everyone, you can stay on here. Have a good night. Thanks again, Professor.
Thank you very much. Thank you very much.
beyond the standard model of cosmology. He has very influential papers on the subject, especially if you want to learn, what is there more than lambda CDM out there. Is the paper he co-authored as a review of this area is a very good place to start. So it would be nice if you have a look at it. Without further ado, I just leave the screen to him. So you can share your screen and unmute yourself.
Sorry, I'm having a problem, but I think I fixed it. 1 second. How's that? That, you can hear me?
Yes.
Great. Well, thank you very much for inviting me. It's a pleasure to be at this conference. It looks like a terrific meeting, and I wish I'd been able to spend more time listening to other people's talks. I'm sure they've been great. I'm going to talk about an idea called early dark energy today. It's not my idea, as I'll discuss, but we have been working in a variety of ways to try to give the idea a more concrete home within a sort of well-behaved particle physics setting, field theoretical setting, as you'll see. So I'll talk a little bit about the reason we're interested in this idea, namely the Hubble tension in cosmology and its possible solutions. And then I'll focus on early dark energy and explain to you what it is, and in particular, tell you about some of the issues with implementing it in a sensible way. And in particular, I'll focus on its own coincidence problem, which is different to the coincidence problem that you'll have heard of in dark energy in general. And so then I'll focus in on possible solutions to this, which is what I really want to talk about. And I'll try to explain how coupling to matter species, for which the epoch of matter radiation equality is a special or important epoch, can provide you a way to ameliorate the problems that early dark energy has and to try to provide a more sort of compelling model for this new physics. Depending on how time works out, I will talk about neutrino-assisted early dark energy and chameleon early dark energy, which are two different implementations of the broad idea. So before I get going, I should say I've been working with quite remarkable people over the last decade on various aspects of this problem, and particularly in recent years with all the people on this slide. So I won't dwell on this slide, but I did want to at least show the faces of the young people in particular that I've been lucky enough to work with in the last few years. So what's the problem I want to talk about? Well, it's the Hubble problem. The standard cosmological problem explains most observations, but we know that there's been several anomalies and tensions that have been found comparing different cosmological and astrophysical data sets. And of course, from the point of view of someone like me, and I expect most of you, the interesting thing about this is that it might point to the presence of new physics. So the most discussed of these problems is really between measurements of the Hubble parameter. And by that, I really mean the Hubble constant, the value of the Hubble parameter today, but measured using data primarily from very different epochs in the universe. So there are what are called local measurements, and I'll describe this in more detail in a moment, obtained by observing Cepheid variables, a sort of very old way of doing this in a way, but of course done by modern masters of the field. And this gives you a value of the Hubble parameter that is around 74 or so. This number changes a little bit year to year. I haven't bothered to update it too much because it doesn't change that much. And then there is estimates of the Hubble parameter you can get by taking the Planck microwave background anisotropy measurements and fitting those to our best current simplest model of cosmology, namely lambda CDM with 3 light neutrinos, very light in this case, and then you infer a Hubble constant that is markedly different, okay? There's a tension of about 5.5 sigma or so, and it doesn't seem to be going away. Often, those of us who have worked in particle physics and cosmology long enough, you see anomalies come along, and sometimes they drift above 3 sigma, and sometimes they approach 4 sigma, but often they come and they go away rather quickly. This has been very, very persistent, and each time we get new data, often that data makes the problem worse. And so it's been a fascinating few years for this reason. Now, it is one of a set of other moderate tensions in the Lambda CDM model. This is the one I just talked about. There's a measurements of the Hubble parameter compared to, publication year. That's not a very useful axis to have, but I just wanted to show you the scatter really in a plot like this, depending on different measurements and also different ways of measuring. There are other examples. There is a discrepancy between the way in which matter clustering is biased in the standard model of cosmology, the sigma 8 tension between different measurements. And there's also, just to give another example, the issue of the unexpected lack of power in the angular microwave background power spectrum above around 60 degrees. Okay, often you will see that described as a low multipole lack of power in the K-space description or L-space description of the microwave background. It is true that you see it there, but in the real space correlation function, it's very dramatic. It just drops to 0, as you can see in this dotted line on this plot. And that's just another example of something we don't understand in cosmology. So let me be a little more specific about what's going on here. One way to measure the Hubble constant is locally, really just to do essentially what Hubble did. A little bit more sophisticated version of that, but the same thing. Measure the distance to galaxies. Use Cepheid variables within those galaxies. Measure the slope of the redshift distance graph, and then plug that slope into the expression we have within the standard cosmological model for the luminosity distance to different galaxies. So this expression here. So this is taken from general relativity, of course, and it has the Hubble parameter in red, and you just read off the value of the Hubble parameter that way. Okay. Now, another way to do it is to use a microwave background. Microwave background provides a specific length scale or angular scale on the sky. So if you look at the power spectrum, the position of the first peak in particular gives you a standard size on the sky. And you can compare that physical length to the angular separation that it subtends on the sky. And that gives you this sort of sound horizon distance that I've written as an integral here over the history of the expansion of the universe. And you calculate that using our standard cosmological model, and you measure the position of that angular peak, and you use the fact that the distance, the angular distance to fluctuations in the microwave background is related to these two quantities in this way, and that allows you to write down another integral. And that integral contains the Hubble parameter again in a different way. So now you just get to compare these two, and it's by doing this that you get the different values that I mentioned. So what could be the resolution here? What can be causing this? Well, of course, it could be that one or more of the measurements have unknown systematics. There could be a calibration issue in the Planck data. There could be unknown distance ladder systematics in the Cepheid data. And many, many people have tried to understand this. Many people who are certainly far more qualified than I am to understand the intricacies of how these observations are done have tried to explain that. And there are efforts to improve this ongoing. And every time someone makes an effort to improve these systematics, this tension seems to get worse, which is interesting. The other possibility is that it's our statistics we don't understand, okay? Maybe the tension is not as bad as we think. Maybe we don't have the right statistical measure of the tension, or maybe by making different cuts or priors in our data, well, the tension will not be as bad as we think. And many other people, again, far more qualified than I, have tried to understand this. This is all fascinating to a certain subset of the community, but of course, for people like me, what I really care about is, could it be new physics? And that's what we're going to focus on for the rest of this talk. So this is one possible way to address the problem. The idea is called early dark energy. It's not a particularly great name, by the way. It's not particularly early. We tend to think of early universe as very early. This is not very early. It actually is around the time of matter radiation equality. And it's not really dark energy, although we do need it to have a few things in common with dark energy. We don't need this to cause the universe to accelerate. We don't need it to behave like dark energy. We do need it to be subdominant before, very subdominant before the epoch of matter radiation equality, and then to become a little bit important around that epoch, and then to go away again. So in that sense, it has some commonalities with dark energy. So the goal here is to take this example that I gave you earlier of measuring the angular distance on the sky in the microwave background, writing down the sound horizon in the way that I've written it here. And you'll notice that in the way I've written it here, I've got this ellipsis, dot, dot, dot, that allows you, if you change the matter energy content of the universe, to change the value of RS. So the whole goal of early dark energy is to add some new stuff into the Friedmann equation in such a way that it alters RS at the right epoch and then goes away again later on. And by doing that, one can tweak the value of the Hubble parameter that's inferred from the microwave background and bring it in line with the number that we measure from local measurements. Okay. So this is a nice idea. It's attractive to those of us who are interested in looking for new physics, but it turns out to be quite hard to implement. You cannot always get what you want in early dark energy. There are some positives of this idea. It does appear to resolve the Hubble tension. It improves the fit to cosmological data relative to lambda CDM. And there are a number of theoretical scenarios, as I'll mention a little bit in a while, that can give rise to this kind of physics. In particular, and let me not shock you, guess what? It's cosmology. A simple scalar field seems to be one thing that can do the job. So we always invoke a scalar field. This has not been a surprise that that's what came along here. We're not very creative at the end of the day. Now, there are negatives here, okay? I mentioned at the beginning, one of the other tensions is this large-scale structure tension, the sigma-8 tension. And it turns out that although that is not as serious a tension as the Hubble tension, the idea of early dark energy seems to make that tension worse. And so there's a tension here between those two tensions. You need to include some local values of the Hubble parameter while fitting, and that you might worry that you're including information you should be predicting. And then there's a sort of theoretical issue. For reasons that I'll come back to, simple potentials don't work for this to make this happen. And so potentials that are very flat are needed to do this, very flat around the origin. And the potentials that people have thought about that give the best fit are potentials that look like this. So potentials that look a lot like you would have for example, a pseudo-Amber-Goldstone boson, but to some ridiculous power, which we have no real reason to think about being true. On top of all that, as I'll also mention, the solution is very fine-tuned in theoretical parameters. And so it's something else that we flag as theorists. So without dwelling on the details here, it's really not that easy to make this idea work, certainly from a theoretical point of view. When you change the sound horizon, it comes with other effects. For example, it changes the damping scale of perturbations, and that can conflict with other observations if you're not careful. So it's a nice theoretical idea, but comes with some baggage. Nevertheless, it can help with the Hubble tension. What you need is a pre-recombination energy injection close to matter radiation equality. What happens is that reduces the pre-recombination expansion rate, therefore reduces the sound horizon. And then, crucially, if you want this to work, right after this has done its job, right after it has come in and changed the expansion rate and reduced the sound horizon, it has to go away rapidly. It has to dilute away rapidly so that the late universe is unchanged. And as I said, I'm just highlighting again, there is this tension with the large-scale structure tension. There are some other problems of early dark energy that I mentioned on the last slide and I want to focus on. What creates this phenomenological behavior? Why should some physics come in just at that time and then go away? Why does it appear at matter radiation equality? And in particular, could we conceive of a model that doesn't worsen the large-scale structure tension? So these are questions that led us to start thinking about this problem. I'll just mention in passing, since I've been trying to give you bad news about early dark energy, that maybe it's not that great and it has these problems, that in a couple of relatively recent papers, this one in particular, I won't require you to read all this, I just want to So this is just part of an abstract of this paper from Hill et al. At the end of last year, that you combining data from ACT in particular, they find that early dark energy is favored over lambda CDM at about 3 sigma by ACT data alone. And then, but then of course, when you include the full Planck data, you again don't find evidence for early dark energy, as you might expect, because Planck pushes you back in that other direction. And also an even more recent paper from February, just a few months ago, from Smith et al., where they look at Planck, SPT, and ACT, and they find a moderate preference for early dark energy by combining those 3 data sets. I don't have a horse in this race, but I just want to point out that a lot of smart people who know a lot about the way this data sets are supposed to be encouraged are finding this intriguing, but the dust has not settled around the data yet. Okay, so let's focus on one of these actual problems and talk a little bit about how we might solve it. So early dark energy does have another coincidence problem. We have a coincidence problem already in dark energy. Why now? Why did the universe begin accelerating today? And in early dark energy, there's another type of coincidence problem. Why is it that this new contribution to the mass energy density of the universe just happens to kick in around matter radiation equality? So it's irrelevant before, it's relevant then, and irrelevant afterwards. Why is that a special epoch? And that is unexplained in typical models of early dark energy. One way you can make it work, which is how early dark energy works, is in the standard way we all learn when we're dealing with scalar fields in cosmology. Namely, if you tune the mass of your scalar field to be at the value of the Hubble parameter at the time that you want it to be important, then you can arrange for a field to be friction dominated due to the Hubble expansion and stuck on its potential until the Hubble expansion rate decreases below its mass. So if you tune the mass, you can make this work. So you just write down the simple field equation for a scalar field, and you just ask, what is the value of the Hubble parameter at radiation equality, matter radiation equality? And the answer is 10 to the minus 29 electron volts. It's very low. And so if you want to build a model with that mass, it's very finely tuned indeed. It's very hard to build models. As I said, you could imagine trying to build a model. I mean, whenever we're faced with a very low mass in cosmology, one way to address that is to say, well, maybe it's a pseudo-Nambu-Goldstone boson. Okay, so it has a very light mass. The problem is that if you do that in a model like this, so you arrange for it to have a very light mass around this point, then if it has a very light mass around the origin, at the end of the day, the field will oscillate around the origin and it will make a contribution to the matter density of the universe. When it does that, it will ruin the agreement with data. So I made a statement here without writing down a potential. I should have written down the potential, but what I wanted to say is, when you normally have a potential for a Nambu-Goldstone boson, the way that that happens is, to a first approximation, the potential is flat, and then instanton contributions raise the potential and give you this 1 minus cosine phi behavior. That's very nice in general in cosmology, but I told you in this case, if you want early dark energy to work, it has to be 1 minus cos phi some power. Particle physics model. So just to reiterate, at the risk of being pedantic, you can write down models that do this. They are very finely tuned. And when you try to write down models that are theoretically protect the small numbers involved, you end up having to still ignore contributions that you've no real right to ignore. So here's an idea about how to deal with that, a broad idea and a couple of examples, okay? We want to find another mechanism to trigger the onset of early dark energy that does not have the fine tuning of the example I just gave you. So the idea we will exploit is that instead of balancing the scalar mass against the Hubble parameter at equality, we'll exploit the fact that early dark energy must become important at that time and look for other physics that is also important at that exact epoch. And we'll try to couple these two things together so that some known physics that is important at that epoch triggers the onset of this early dark energy. Very simple idea. And there are a couple of well-known examples of this. One is the coincidence between the energy scale of matter radiation equality and the upper limit on the sum of neutrino masses. Now, when I start to describe this model in detail, you're going to see this is really hard for us to make work because we need neutrino masses are a little bit heavier than you would love. But for now, I'll just keep to this line and point out that the upper limit on the sum of neutrino masses suggests a coupling to neutrinos might help you in this regard. And so I'll present this model in a moment, and we call this neutrino-assisted early dark energy. Second example is, well, there is something we certainly know happens at matter radiation equality, namely matter was irrelevant before, roughly speaking, and becomes relevant afterwards. And so perhaps a coupling to matter itself might be a natural trigger. And in general, coupling to matter is a very hard thing to make consistent with all our precision measurements in physics. And so what I'll really do is couple only to dark matter in this example. And this is, for perhaps obvious reasons, to some of you, this will be a model we call chameleon early dark energy. So let me talk about the first example first. This is presented in a couple of recent papers, a PRL with my former postdoc, Jeremy Saxton, and a longer paper in which we partnered with my student, Chuyo Liang, and my former student, Mariana Carrillo Gonzalez, to look at a much more detailed analysis. So the idea here is very simple. We take the idea of an early dark energy field, just some scalar field, and we couple it only to neutrinos. Obviously, it's coupled to everything else in the universe through gravity, through a minimal coupling, but it's coupled differently to neutrinos. In fact, we couple through a conformal coupling for reasons that I think will become clear. So here's the simplest example I could write down. Einstein gravity, scalar field, a potential, and then, this is the interesting part, you can imagine that the rest of the universe goes along for the ride here, but neutrinos do not fall along geodesics of the Einstein metric, G mu nu, they fall along geodesics of this conformally related metric, G mu nu tilde. Okay, G mu nu tilde contains the scalar field phi. Okay. If you don't like that, I mean, there's a reason I want to do it that way, but if you find that opaque, you can just expand out this action, okay? After all, to treat anything like this sensibly, it has to be a well-behaved effective field theory, as I'll come back to, so I can truncate it. And then you'll see that what happens is I just have neutrinos with a non-trivial contribution to their mass that comes from phi, the early dark energy field. There are other things you might worry about here, like back reaction. I'll come back to talk about those later in some detail. So now the resulting equations of motion are the ones you would expect, except for the scalar field phi, which does not just have the normal equation of motion, but has a source term that depends on the trace of the energy momentum tensor of neutrinos. Okay. And so that energy momentum tensor of neutrinos I'm calling big capital theta mu nu. Okay. So we can just treat this as motion in an effective potential, and we can ask what happens. So there's the effective potential. It's the potential I wrote down, plus this coupling to the source term due to phi. And now, and of course, there is some complexity in here that I've been sort of ignoring, which is theta contains the entire Fermi-Dirac distribution. At the simplest level, we know how to deal with that. It's in every cosmology book, and in fact, every statistical mechanics book. You can just integrate over the Fermi-Dirac distribution, and you find the following object, which is the trace of the energy momentum tensor. It's T nu to the fourth, the temperature in neutrinos to the fourth, and then a function, tau of m over t, where the function tau is this integral that you've all found in every undergraduate physics course. Okay. And this integral is really the thing we care about in this model. This is why we created this model. Because the details are not overly important, although I will go into them in a while, but what matters is how this integral behaves. And here's the main property of this integral I care about. So on the x-axis here is redshift, on the y-axis is the value of this integral, just normalized by convenient factors of h and m Planck to explain what's going on in the Hubble, in the Friedmann equation. So small values, of course, because neutrinos are light and they don't contribute a huge amount of our energy density, but starts off small, gets a peak around the redshift of matter radiation equality. And I'm sorry, my pointer's not really working here. I'm trying to, I don't know if I can make it work, but I'll just keep saying words. Around the redshift of matter radiation equality, this thing becomes large, relatively speaking, and then goes away again at late times, okay? Roughly speaking, the trace is zero, the trace becomes important, everything redshifts away. That's roughly the way it goes. But this, of course, has a non-trivial effect in the Friedmann equation, okay? It has this forcing term. And so the temperature here is around the mass of the neutrinos, around of order EV or so. And so the simplistic argument is that what happens now is that the field, you can choose, you do not have to choose some ridiculously fine-tuned potential. There'll be some tuning for sure. The field can sit in its minimum if you like. Then this forcing term comes in at temperatures around the neutrino mass and pushes the field away in its potential. Then the forcing term goes away again. And then the field will drop back down. And that's early dark energy. And you can do a quick check, a simple analytic estimate of how far this field gets displaced, just by simplistically ignoring certain terms in the field equations. And you can get a value that the kick is around 0.03 times this parameter beta that was in my conformal coupling times M Planck. So some small amount the field moves by. It makes a contribution to the energy density of the universe. It changes the expansion rate, and then it just rolls down to its minimum and goes away again. And so this is doing exactly what early dark energy is supposed to do, but without having to tune the mass so carefully to keep the field hanging around on its potential at matter radiation equality. Lest you think those simple calculations might make a big mistake, you can just fully numerically solve these equations. So we take the Friedmann equation, we put in lambda CDM, actual lambda, plus a coupling, so matter, radiation, the scalar field, and we solve that self-consistently with the scalar field equation, or if you like, self-consistently with the acceleration equation. And this is what the early dark energy field does, and it's exactly as advertised, only here I'm plotting the actual change in phi, the field. So changes by, some number times 10 to the minus 9 M Planck at around the redshift of matter radiation equality and vanishes again down to zero very quickly. And the Hubble parameter, and it should be no surprise to you, I've chosen parameters carefully here, changes compared to the Hubble parameter in lambda CDM by about 8% at matter radiation equality. So I should point out here, for those of you who spend as much time as me thinking about these things, don't be alarmed by this plot. I'm not showing the Hubble parameter increasing. That would violate all kinds of energy conditions in cosmology. This is the Hubble parameter compared to the Hubble parameter in lambda CDM. So the expansion of the universe would agree with lambda CDM at early times and late times and change by about 8% around matter radiation equality. Exactly what you need to solve the Hubble tension. This is in some sense the key result of this set of models. Now, that model I just wrote down was very, very simple. And there are a number of reasons to worry about that model theoretically. So in our second paper, we came back and tried to write down a more complete model that makes us happier. So this is the same sort of model. I've done two things here. Firstly, I've written down a very generic potential, meaning mass squared phi to the fourth, nothing special about it. And I've allowed for a more general conformal coupling between phi and neutrinos. I've written that as a squared of phi rather than this exponential function I wrote down before. I won't specify the origin of neutrino mass here, but we could talk about that, or whether they're Dirac or Meron. I'll just write them down for now. And again, if you expand out this action and I do a redefinition of the neutrino field, just to make things look neat and canonical, you get the following action. Einstein gravity, simple scalar field, simple potential, and then a weird coupling to neutrinos. Okay. Now, The quartic potential, if I just wrote lambda phi to the fourth, it turns out that in contrast to the original early dark energy models, which had to be very finely tuned, it's an excellent fit to solving the Hubble tension. So that's nice. The fine tuning we had before at that level is not there. On the other hand, you know, effective field theory should guide the way we work here as particle physicists. And effective field theory would say, unless you have some symmetry that prevents it, you should also include a mass. And the mass, I told you, is very tightly constrained in these models by late time expansion. So just to be clear about that one more time, what happens is, however you get the field up there, either the regular early dark energy model or the way we do it, after the forcing term or the Hubble friction, whatever it is, goes away, the field starts to drop. When it starts to drop, if it gets near the minimum and oscillates around a mass term, those oscillations effectively contribute like a fluid with equation of state P equals 0. So they look like matter. They make an effective contribution to dark matter. And that ruins the agreement with large-scale structure data at late times. So you have to avoid that. So I'm flagging that now technically for you, and I'll show you in a moment that that's okay for us. Now, the other thing we've done here is to generalize this coupling function. And for that, we have a very important reason. And again, it comes down to the effective field theory. When we wrote down the exponential function as a coupling, you could show that that effective potential that I wrote down is minimized at this value of phi. And you see that this is related to the trace of the energy momentum tensor. The problem is this grows with redshift, because there's always a little bit of a contribution here from the mass of the neutrino. And so it grows and grows with redshift, and eventually it exits the validity of the effective field theory. I can't truncate this anymore. I can't really compute things. So if you want to make the effective field theory well behaved, it turns out you can do that by making one assumption about this function A that I included to replace the exponential. And that is, we're going to assume that when the series for A is resummed, that should say resummed, I apologize, it has a minimum at some value of phi. This happens, for example, in some strongly coupled string theory models. So what happens then is the effective potential looks like this. It would be very simple if A was the exponential, but I don't want A to be an exponential here. And here's the comparison between the two cases. So redshift on the bottom, phi over m Planck times beta, which is the relevant thing for computing quantum corrections to this theory and the effective field theory. The red curve is what happened in the original model with an exponential coupling. And as redshift increases, as you go to early times in the universe, you exit the regime in which you can trust your calculations. In particular, phi over m Planck becomes much bigger than 1. You don't know how to truncate anything. On the other hand, if I can get a minimum in A, I can actually keep things well behaved all the way out to high redshift. In particular, just to give you a very simple example, if my coupling function looks like this, A has some minimum, I've chosen this function so it has a minimum at a value phi bar, then you can remain completely ignorant about the UV completion of your theory and trust the cosmology up to high energies, high temperatures, as we would like. So this is an important outcome of trying to generalize this model. Now, I told you that there's another problem here in principle, which is the mass, and this is, I want to come back and ask about radiative stability. So the effective field theory forces a mass term, and that mass cannot be too large, as I said, otherwise we'll have a problem with large scale structure. So what I'm going to say here is, I'm allowed to include a mass term because an effective field theory forces me to include a mass term. But if I choose that mass term to be very small so I don't screw up large scale structure, can I make it be technically natural so that quantum corrections do not reintroduce a big mass? So this is just the normal question of radiative stability of my model. And the way to figure that out is to expand out the interactions in the model. And the expanded interactions look like this. Little phi here is the expanded value of phi around its minimum, around its current value, sorry. And phi is its minimum value. And so that's one interaction you have to worry about. There's also, you have to worry about cubic and quartic self-interactions of early dark energy. And together with this term I wrote above, these make a set of contributions, one loop contributions to the mass in that potential that I wrote down. And it's these contributions that tell you whether the mass I would like to choose is allowed or inconsistent with the effective field theory. So what you get when you compute these loop diagrams, when you estimate these loop diagrams, I should say, is that the contribution to the mass squared looks like this. And the good news here is that it's suppressed by the Planck mass. And so what you find is that if this inequality is satisfied, the mass term that you've chosen, m squared, is completely consistent with effective field theory. And I won't plug in all the numbers for you here. I'll just point out that this is very, very easy to attain. Sorry, I shouldn't have picked that. This is not a big constraint on the model. So unlike in regular early dark energy, where I had to choose the mass, the right value to get it to stick on the potential until matter radiation equality, here I can choose it to be very small. It's consistent with the effective field theory, which with radius stability, and I still get early dark energy kicking in at the right time because of the coupling to neutrinos. You can look at the cosmological evolution in significantly more detail. As I said, at high redshifts, the effective potential is minimized at phi bar, and that is nice because it provides you with robust initial conditions for your evolution. So the universe expands, the trace of the energy momentum tensor of neutrinos redshifts until the contribution from the actual potential, in particular its quartic term, is non-negligible. And then the minimum adiabatically evolves towards zero, and higher order terms become important. So this is a lot of words. I'm going to show you graphs on the next slide, but just to say, all of these words are supposed to say, it does exactly what I advertised to you. If I look at omega phi, there is a kick feature that leads to an onset of early dark energy behavior. The Hubble constant redshifts more slowly compared to the way it does in lambda CDM. The sound horizon lowers. The value of H0 inferred from the microwave background increases. And then this is a transient effect because the field rolls down to its minimum, and that eventually decreases to zero as the neutrino density redshifts away. So eventually the quartic term becomes negligible, the neutrinos are negligible, the mass term is the only thing, and I've chosen the mass term to be tiny. So this, in principle, does everything you want. So what does it look like? Well, you can just check that during the matter epoch, so after radiation, after this has happened, the early dark energy behavior, the phi field can become decomposed into two components, really. There's an adiabatic component that tracks the minimum, and that acts as a small contribution to actual dark energy, to the cosmological constant. And there's a rapidly varying component from oscillations around the minimum that acts like an additional dark matter component. It's very easy to check that the total energy density of dark energy, including the cosmological constant, is given by this. And for the masses that I've chosen in this model, this is an absolutely irrelevant contribution to the lambda mass m Planck squared part. So nothing to do with late time cosmic acceleration is affected by this physics, which is good. The dark matter contribution at late times is given by this. And this, as I said, provides a potential tension with the data. And that's why in other early dark energy models, you neglect the mass. So we have shown that in our models, you can include a mass large enough to be radiatively stable, but small enough so that we're not in tension with the data. And that's the check we did. So, oh, I have this slide twice. It's not deliberate. So we numerically solve the equations again, and it just looks like this. So just to be clear what I'm showing you, these are the two components. The left is the contribution of the oscillations to the overall energy density in phi, and you can see they're irrelevant. They're tiny. They're just a superposition on top of the overall behavior. And just to sort of lay that out in more detail, omega of delta phi, and it's just a small contribution to the overall dark matter density. So not something you need to worry about. Similarly, the equation of state of dark energy, actual dark energy, changes by an irrelevant amount, certainly within the bounds of current measurements. So late time behavior is just fine in this model, is the short answer.
Professor Troden, you got around 10 minutes.
That's fine. That's fine. I'm going to skip this slide anyway because I want to, and I think I'm going to skip this one too. I'll just go on and quickly sketch this, and then I'll be done. So let me just say that, of course, the right thing to do now is to make a comparison with large-scale structured data in detail, to do a Monte Carlo calculation. And we're on the way to doing that, but we haven't done it yet. So, and I'll mention at the end why that's so important. So to end, I just want to sketch this other idea that I mentioned, the possibility of not coupling to neutrinos, but coupling to chameleon-like coupling to dark matter. So this is work I did with my colleagues, Justin Khoury and Bhuvnesh Jain, and our postdocs, Tanvi Karwal and Marco Riveri. So here we do a very similar thing. I do exactly what I just showed you I did with neutrinos, but instead of conformally coupling to neutrinos, conformally couple to dark matter. Again, it's going to yield an energy injection around the time when matter starts to dominate the universe. And the goal will be that the dynamics are sufficiently different that we can allow more particle physics, natural particle physics potentials than this best fit model that's rather unnatural that I mentioned earlier. Okay, I'm going to ignore that. So again, simple model, scalar field, regular matter behaves in normal ways. Dark matter couples through some conformal metric with a conformal factor A squared of phi. Write down the background equations of motion. I'm not going to dwell on these too much because you've seen them. And again, you've got motion and effective potential. Okay, dark matter dilutes away in a slightly non-standard way. Let me keep going. So just to give you a very simple choice, I'll choose that exponential coupling again, and incredibly boring potential, lambda phi to the fourth. Again, effective field theory tells you that without a symmetry, we should include a mass term. So we're going to include an ultralight mass term so that we know that we are safe from dark matter behavior, 10 to the minus 28 EV. And radiative corrections from dark matter loops, just as in the last calculation, can be checked, and it yields this. All that tells us is the cutoff our effective field theory should be much bigger than the dark matter mass. And so if the dark matter mass is less than or around than EV, we'd be radiatively stable. So we write down what are the initial conditions in this model. Field rolls down its effective potential. There's a time varying amplitude. The dark matter interaction dominates. And then eventually the potential takes over when dark matter dilutes away. And of course, the critical epoch here is matter radiation equality. Okay, when matter, when the expansion of the universe qualitatively changes. Okay. Before that time, it's Hubble frozen. So I don't want to, I'm well concerned about time. I just want to show you what happens. Okay. So remember, this is just a scalar field coupled to dark matter. And what happens is the field is dominated by kinetic energy at early times, and then it moves on. So to show you what happens, here's the evolution of the scalar field and its effective potential. Okay. If it were just its regular potential, the regular potential is the black dotted line. And you can see that the field would just plummet down to the minimum of this potential. So we've chosen a nice, well-behaved potential. It couldn't behave like early dark energy. But because of this coupling to dark matter, the effective potential flattens out and gradually lowers the field down into its minimum. So just to emphasize that, this is what happens to the field. I'll show that one more time. So instead of just plummeting down, following the potential with the black dotted line, it's gently lowered into the minimum of its potential. And that is what does all the work in comparing with the Hubble parameter. So again, you can solve for the background behavior. Here I'm showing two different signs of the conformal coupling beta. The left side for different signs of beta is the energy densities in matter, radiation, a cosmological constant, and this new field. So the straight lines are, radiation and matter, and then you're seeing different incarnations for different values of beta of what happens with the dark energy. It comes in, it's subdominant, but it's becoming important. It becomes as important as it will be, and then drops away again. On the right-hand side, you can see that more explicitly as a fraction of the total energy density in early dark energy. It's irrelevant at high redshift, becomes important, and then you see these little oscillations as it goes away. And those oscillations are what you have to keep small in order not to screw up late time measurements. So let me summarize what I've told you. Early dark energy is, I think, a somewhat promising resolution to the Hubble tension, but it suffers from a coincidence problem. And that coincidence problem is, it needs to contribute slightly before matter radiation equality and end rapidly thereafter. What we've proposed are two new mechanisms to address this problem. Both involve coupling to different components of the energy budget of the universe. In the first one, coupled to neutrinos, and then the dark energy field gets an energy injection when the neutrinos become non-relativistic around matter radiation equality. If you had an EV neutrino mass, I'll come back to that in a second. That displaces the scalar. You get an onset of early dark energy behavior without a need to tune the scalar's mass. Here's the bad news, and the proposal is on the verge of being excluded by neutrino mass bounds. Neutrino mass bounds keep getting stronger. Planck lensing BAO puts masses, less than about 0.12 eV for lambda CDM. If you want to really understand if this proposal can work, the only way to do it is to do a full Monte Carlo of this system, including all these extra parameters I've included. That is a tricky thing to do, but it's possible then that the best fit would shift the neutrino mass bound slightly, and then this would be tantalizingly at the right scale to be correct. Right now, I would say it's either going to be ruled out when that's done, or it's going to be right on the edge and sort of tantalizingly have exactly the right numbers to work. So we'll see. If you couple the early dark energy scalar to dark matter, then the dominance of dark matter at matter radiation equality triggers the onset of a very brief, non-negligible contribution to the energy budget. And it also addresses this coincidence challenge that I mentioned. Also, again, alleviates these rather unnatural potentials that have been some of the benefits to the data. As I just said, for this case and the last case, a full Markov chain analysis is needed to understand the kind of fit our models have to the full joint data sets, and that's underway in both cases. In the case of chameleon early dark energy, we're actually close to completing it. That's because that's easier to do than the neutrino case, when you have to actually modify the Boltzmann code for the neutrinos to understand the back reaction. So I would say in general that, as with any suggestion of new physics, which early dark energy certainly is, we should expect that it doesn't exist in a vacuum. And I just see these as the first attempts to understand the consequences of how that new physics might couple to other matter, and how that might not just provide us a way to test it, but also a way to make it a more natural solution to the problems we have in cosmology. And I will end there, and thank you.
Thank you for this nice talk, Professor Troden. We can take some questions. You can write them in chat bot, or you can unmute yourself and ask those. Hamza Azri has a question. Can you unmute yourself, Hamza, or? Hang on.
Okay, can you hear me?
Yes.
Thank you. Thanks for the very nice talk. I have a question about the conformal coupling, the conformal metric you have introduced. This looks almost similar to some mechanisms in strong gravity regimes, and Fitchy is expert in this. And so I don't know if the motivation is coming from there or not, but my question is, do you have like instability in the solutions in the scalar field or not? Because you generate a mass, I think, effective mass, right?
So, okay, so two questions there. First of all, the motivation, I tried to show you in each case that when you expand out these theories, as you should for an effective field theory, they're not that mysterious. They're just particular couplings that are, that you would generate in the effective field theory. The reason I wanted to write it down initially as a conformal coupling was because then it's explicitly clear that the thing that you're coupling to is the trace of the energy momentum tensor. And we know for neutrinos for example, that the trace of the engineering tensor is the thing that becomes dominant and goes away again. So that was our motivation. The best of my knowledge, there are not instabilities. I did say that we should do a full Monte Carlo. That is true, and we are. We certainly have done a sort of simpler perturbative analysis of these equations, and there are not instabilities in these models that I know of. No, other than the obvious instabilities of, growth of structure in the universe and cosmology itself. There are no other instabilities.
I see. What about the radiative corrections? You mentioned the neutrino mass at the end. Okay, you said there is no issue, but what about the scalar itself?
Yeah, so in fact, the neutrino is an easy thing to compute, but we also, the calculations that I presented, I went through quite quickly. They were actually calculations of the scalar, both the neutrino contribution and the scalar self-interaction contributions. And so we check all of them. That's right. It's very important to make sure that you have radiative stability.
Thank you. Thank you very much. Thank you.
Sure.
There are some questions in the chat. I think we have some time to discuss them as well, so I'm going to read them. Jakub Hundur asks, how long does it take, or in which time epoch is it supposed to happen? But it is not. Please.
So I was trying to make it clear, but I apologize if I wasn't. That the way that early dark energy works, if it works at all, is that it has to happen at the epoch of matter radiation equality, essentially. So that's when it happens, okay? Redshifts of order 1,000 or so in the universe. And the energy has to get out of the way pretty quickly. So within, less than an E-fold, right? It just goes away. So it comes in, goes away. So I could quantify the last thing a little more if I had to, but the epoch is very clear. It's matter radiation equality. And then this question about mixings, I see.
Oh yeah, that was.
I don't know. We haven't studied a model with mixings. My guess is it doesn't matter because we don't actually care. The microphysics of the neutrinos is not as important here as just what are the mass eigenstates is important. So we just need to know the mass eigenstates, I think, and the mixing doesn't help us with this problem. If we had found that the interaction between the scalar and the neutrinos introduced enough self-interaction that we had to worry about it, then I think you might have to worry a lot about mixings, but you don't have to worry about it in this model, I think.
I have a quick question. So is there a natural motivation for just coupling to the neutrinos? There are lots of alternative theories that couple nominally to all matter. I've even seen theories that only couple to fermions for some reasons. I've never seen anything that couples to a specific kind of fermion.
Well, so everyone has their own taste of what this kind of naturalness means, as opposed to technical naturalness. I would say
any motivation for just coupling to neutrinos.
It's a good question. So people have certainly studied models like each of these for many, many years. Okay, so models of coupling regular dark energy to neutrinos were studied, I mean, more than 20 years ago now by people like Kaplan, Cohen, and people and Nelson, people like that. And coupling to just dark matter was studied extensively in the chameleon models of dark and regular dark energy. So these are well-known things to do. I have not answered your question about how well motivated they are. I just wanted to point out these things have been around for a while, these kinds of ideas. There are two answers to your question. There's the honest answer, which is, in models like this, you could have a very modest goal, which is write down a model that works and make sure it's radiatively stable. Okay, so in that sense, the thing you wrote down is fine as a physics theory, and that's what we've done. The real answer is, you can write down models in which you get this kind of behavior, but it's tricky. So one way to do this would be to appeal to an embedding within string theory, where different types of matter live on different branes in an extended extra dimension. And then the warp factor is different in each place where you are in the fifth dimension, and that causes a different coupling to a different conformal metric. And so that I'm not trying to tell you that that's my motivation and that I love those models, but if you forced me to give you a more, if you like, fundamental setting, that's the one I would give.
Okay, thanks. I'm pretty satisfied.
So if there are no other questions, we can thank Professor Troden for this nice talk again. And we can start with our next speaker and second to last speaker of today, Professor Xiaogang Wen.
Thank you.
So Professor Wen, can you try sharing your screen, please? Let me try and thank you. Okay, this looks good. So before you start your talk, let me give a quick introduction, make a quick introduction for you. So Professor Xiaogang Wen is a prominent figure in the condensed matter theory group in MIT. In particular, he is Cecil and Ida Green Professor of Physics, and he has many research interests, but some of it includes topological and quantum order, high temperature superconductors, and origin and unification of elementary particles. Today's talk will be about his last interest, I'm guessing, and it's called Unification of Elementary Particles and Fundamental Forces via Quantum Information. So screen is yours, Professor Wen.
Okay, can you hear me?
Yes.
Yeah. Also, can you see my cursor?
Yes.
Okay, thank you. Okay. I really like to thank the organizer for organizing such an interesting meeting. You know, many aspects of fundamental physics is touched in this meeting. And so today I'm going to talk about actually a topic in condensed matter physics, despite the title. So actually you'll see that even in condensed matter physics, which is viewed as applied physics, some fundamental physics question can be touched. Okay, so let's ask a question. How do we gain a deeper understanding of our world? You know, our world is very rich, have a lot of phenomena. How to gain this deeper understanding? It turns out that our understanding is deep understanding is obtained through the cycle of discovery and unification, and more discovery.
Do you remember how you got here?
So, so in the discovery phase, we just collect a lot of experimental facts. Then we are overwhelmed by those experimental facts. Then we want to have a theory to unify, to have an understanding of those experimental facts. And so through this cycle, we just gain a deeper and deeper understanding of our universe. And each big unification can be viewed as a revolution in physics. And for those deep revolution, actually, it turns out that we may have a new worldview. You know, many fundamental concepts are changed. Even the language is changed. Okay, and most time we also need to introduce new mathematics to describe the new world. So the first revolution is, we can say, is a mechanical revolution.
Do you remember how you got here?
Unify the falling apple on the earth.
You've lost your capacity to discern reality from fiction.
And the worldview at that time is that all matter are formed by collection of particles. And for each particle, their motion are governed by Newton's law. Okay. Then the second one, we can say that's an electromagnetic revolution. And where it's unified is a seemingly distinct phenomenon of electricity, magnetism, and the light. Okay. And I will say the new worldview in this revolution is that we discover a new form of matter. I call that wave-like matter. So this wave-like matter is an electromagnetic wave, which causes electromagnetic interaction. And this kind of wave-like matter satisfies very different law. So it's actually satisfies Newton's Maxwell's equation. Then the third revolution, I would say, is a relativity revolution, where unify the space-time and the gravity. And another way to view this revolution is that a second wave-like matter is found. So which is a deformation for space or gravitational wave. Okay. Again, this is second wave-like matter. Again, obeys a different equation, which is Einstein's equation. And it's taken 100 years to experimentally confirm this second form of wave-like matter. So it's quite an achievement. Actually, I would say the biggest revolution is the quantum revolution. It turns out the quantum revolution unified this particle and the wave. So this particle-like matter and wave-like matter are unified under quantum revolution. And so we have this weird form of matter, which is not particle, not wave, but it's both particle and both wave. And so it's kind of particle wave-like matter. So essence in quantum theory, the quantum theory is really a very fundamental revolution. So the one of essence is that the very notion of existence is changed. For example, we can say that spin up is existence, and spin down is also existence, which can be referred as a 0 or 1 bit in this qubit. However, the quantum physics tell us if spin up, spin down are existence, then their addition must also be an existence. So this up plus down is also exist. So this is really, really weird, but this is really a superposition principle, which kind of fundamentally change our notion of existence. Okay, and it is this superposition principle which gave rise to this particle wave duality. And the linear algebra describing this superposition became a mathematical foundation for quantum theory. Then as a consequence, maybe I want to emphasize there's another essence of quantum theory as an essence of, as a consequence of superposition. You know, we used to think the information and the matter are two very different things. So information is the attribute of the carried by a matter. But however, the quantum physics tell us that a frequency, which is a property of information, because frequency represents change. So anything change is a frequency. And so frequency actually is a property of information. But according to quantum physics, the frequency is related to energy. According to relativity, energy are related to the mass. Both energy and the mass are property of matter. So therefore, just like a Boltzmann constant, which connect temperature to energy, the Planck constant really connect frequency to the matter, to the energy. So it's really, so Planck constant really connect matter and information. It says that the matter and information are deeply related, or maybe the same thing, you know. So I would say this is probably a deep message from quantum theory. So we should view matter information as the same, or there's a unification between matter and information. But this sounds like a philosophy, you know, exactly how matter, like electron, proton, quarks, photon arise from a quantum information, how that works. Okay, one way for this to get work is to say that the space itself is a quantum information. Or another way to say that more precisely is that the space is a collection of qubits, or we can say the qubit ocean. So this is kind of like a picture of a space here. And so the dots are qubits. The white one is the qubit 0, and the black one is qubit 1. So in the qubit in two states. And this link represents the qubits may be interacting or entangled. So there's some sense of a neighborhood. Okay. So so in this picture, the space is a qubits, and the qubits is everything. So there's no such thing as what is between two qubits. Do we have anything between the qubits? No. Qubits is everything. It's all we have. So there's nothing between two qubits. Okay, and so in this picture, then we say that the elementary, the vacuum is like a ground state of the qubit ocean, and the elementary particle are the wave or excitation in this qubit ocean. So that is a picture to say that how everything coming from quantum information. So therefore, the origin of elementary particle, it became origin for wave because of particle wave duality. So we just need to find all kind of wave equation describe all kinds of particle. And this entanglement between qubits give us a sense of space. For example, whether space have 1 dimension, 2 dimension, 3 dimension or not, it really depends on the entanglement structure of qubits. Okay, so that is the basic assumption. And so actually this assumption sounds kind of maybe crazy, but actually it's not crazy at all because there's an experimental test. The space actually is a dynamical media. It's not just some empty state. That's really the Casimir effect. And the Casimir effect already tells us that the space itself is dynamical media. So it's kind of like this qubits ocean. It's compatible with the qubit ocean assumption. However, do we really believe that elementary particle and the fundamental force all come from the ocean of qubits? You know, qubits are really the simplest object in quantum mechanics. There's nothing simpler than that. If you say that the elementary particle have something originate from somewhere, then the qubits is the simplest thing it can originate from. But there's nothing simpler than qubits. But however, qubits are too simple. You know, our elementary particle and the fundamental force are described by a standard model, which is kind of rich and complex. For example, the standard model have those properties. You know, the standard model have some input. We have to have input to build the standard model. So why we have those input? Why those input are necessary? So I call those input to the standard model as a wonder or mystery of the universe. So certainly first we have this identical particle. But however, if identical particles are bosons, then it's easy to use qubits ocean to describe it. For example, we can assume this 0 qubits as a vacuum in the background. Then the 1 qubit is a boson moving around. So therefore, if a standard model only contains scalar bosons, then it's easy to see that the qubits ocean can give rise to standard model. But we know that the standard model contains much more than identical boson. It's also contains a photon, or another way to say that the wave that satisfies Maxwell equation. It's also contains wave that satisfies Yang-Mills equation, which is give rise to strong and weak interaction. And then we have a particle with a Fermi statistics, which is the standard model are described by anti-commuting field. You know, why we introduce anti-commuting field in standard model to describe our universe? You know, who ordered that? And those fermions also carry fractional angular momentum, which sounds also strange. And also we have a parity breaking. That is only maybe left-hand fermion or maybe right-hand fermion coupled to the Yang-Mills wave. And then we have very accurate Lorentz symmetry. We also have a spin 2 bosons, which have only 2 components. You know, spin 2 should have 5 components, but this spin 2 only have 2 components, which represent the gravitons. So those are kind of like a very basic properties, and which we don't explain where they come from or what is their origin. We just use this as input and to build our model. But now we are like to ask where those 8 wonder or the 8 mystery come from. Do they have an origin from can they come from quantum information? Can they come from qubits? So there's another way to rephrase what I just said, which I call the condensed matter view. So we know that a quantum magnet is a spins going up and down flip That's like a qubits go from 0 to 1. So therefore, the so quantum magnets is a qubit ocean. We can also view qubits ocean as a lattice boson gas. You know, the 0 qubits can be viewed empty side, and the 1 qubits can view the occupied side. So both lattice boson gas and the quantum magnets are something available in our quantum material. So therefore, we can ask, because this qubit motion basically is this quantum magnets or lattice boson gas. And so then we can ask whether we can use this quantum magnets or lattice boson gas to simulate a standard model. That's another way to put it. More precisely is that can we design interaction between those electron spins or the boson gas such that the low energy effective theory of this lattice model happen to be the standard model. Low energy effective theory happen to be standard model. At the beginning, it sounds impossible because for the boson gas qubits, we only have a scalar bosons. And with only scalar boson, how do you produce the fermions? How do you produce a gauge field and the Young-Mills field? That's possible. Okay, so that's really become a very fundamental question. It seems impossible. And so let's to see this what is the problem. So let's try some familiar condensed matter system. For example, let's consider superfluid. The superfluid is actually all kind of superposition of those particles. The ground state of superfluid is a superposition for all kind of a particle position. Okay, so that's the ground state. Then what is a wave? What is a collective excitation above this ground state, superfluid ground state? Well, very simple. It's just density wave. So some region have a more particle, other region have less particle. This density wave may propagate, and we get this standard density wave equation. And we quickly see that this density wave equation indeed gave us a massless particle, but it only gave us a massless spin 0 bosons. Okay, it's not a light. So therefore, therefore, this kind of condensed matter system cannot produce a wave that satisfies Maxwell equation. It can produce a wave, but satisfy a wrong equation. Okay, the light have a 2 transverse mode, not like a 1 longitudinal mode. Okay, so in our second try, we can assume, let's consider another qubits ocean where the qubits 0 is a background, but the qubits 1 form a crystal. Okay, so these black dots are position of qubits 1, you can see. Okay, and then in this case, this crystal have a 2 kind of wave. This is a longitudinal compression wave and the transverse shear wave. Okay, or transverse wave. Okay, so there's something closer. So this kind of wave satisfy elastic equation, which is describe a spinless spin 1 boson with elasticity 0 and ±1. It's almost there, but not quite. Photon is something very special. Photon is a spin 1 boson, but have elasticity only ±1. The elasticity 0 is missing, so we don't have a longitudinal mode. So therefore, this qubit ocean of crystal does not work. Okay, again, we get some wave, but a wrong wave equation. So actually, in condensed matter, people study all kind of order, this all kind of symmetry breaking, all kind of order. And it's really frustrating. And we find all kind of wave equation, but none of them are Maxwell equation. So we couldn't find the media which produce Maxwell equation. So in a sense, we try to find the ether. And we try to say whether certain condensed matter system or quantum spin system behave like an ether whose spin wave satisfy Maxwell equation, but we cannot. So in some sense, we kind of give up. We say that the light is fundamental, and we should not ask where they come from. But however, in 1980s, and we discovered many quantum material like a quantum Hall effect. Also, we discovered high-T superconductor. So that's a stimulated theorist to study spin liquid. Okay, and those studies reveal that there's a new kind of matter actually. We call it topological quantum matter. So, so you can see based on Landau theory, we used to think all different phase matter are classified by the symmetry breaking. But in the quantum Hall state and spin liquid states, we have a different state matter with the same symmetry. So symmetry breaking cannot really characterize them. So that's indicated there's a new kind of matter. So I call this this new kind of order called a topological order because it's not characterized by symmetry, but characterized by some kind of topological property. Okay, and in the previous search of a quantum matter which produce a Maxwell equation, it's a field search. We overlook this topological order. So maybe this the appearance of a new kind of matter, new kind of order, may give us some new hope. That's maybe the media which produce the Maxwell equation can be found in this new kind of material, new kind of order. So what is this topological order? It's just a name. It's taken quite a while for us to really understand what is the topological order. So microscopically, topological order actually is a pattern in the entanglement or many body entanglement. So we call this entanglement called the long range entanglement. So so one way to view long range entanglement is to view this particle have a global dance. You know, the quantum motion are highly correlated, have this global dance. You can see there's a quantum Hall dance like a waltz. Maybe so here I will basically talk about string dance. So those qubits like the qubits 1 or spin down, they line up, they form a string. Okay. And then the ground state is a superposition of a string formed by those qubits, formed by these down qubits. Okay. Okay. So this we call the string liquid. More generally, the string may branch, so we can get the string net liquid. So those kind of string liquid or string net liquid will have a long range entanglement and will carry a non-trivial topological order. So that represents a new phase of a matter. So in some sense, this string dance is like a microscopic mechanism to have a topological order. Okay, and so when you have this topological dance, what can we have? Actually, we immediately get photon. We get a wave that satisfies Maxwell equation. The idea is the following. So here our ground state is a superposition of strings, but those strings form loops. There's no end. String have no end, so they all loop, liquid of loops. Okay. So that's ground state is a superposition of all kind of loops, all size. The loop can be very big and wrap around the universe several times. You know, this kind of loop liquid, just like this. Okay. And then you say, what is the excitation? Just like the superfluid, where the collective excitation is the density of a particle. Here, the collective excitation is the density of strings. So some region will have a more string, other region have less strings. Okay. Then we immediately find that the string density wave is described by a vector field, because when in the region we have a more string, we also need to specify the string in which direction. There's a more string in which direction. So actually, string density is a vector field. Furthermore, this string density vector field is a divergenceless, because we already say that the string have a no end. Okay, so therefore, along the string density cannot change because string cannot end. You know, the string density can only change in the direction perpendicular to the string. Okay, so that kind of string density has satisfied this divergenceless condition. And then, so now probably I don't need to do too much. You probably can guess that the most natural and simplest wave equation for this divergenceless vector field is actually the Maxwell equation. Okay, And so actually, if you do this some mean field calculation, indeed, you will find the Maxwell equation describing the collective wave in a string liquid. Okay, so therefore, the string density wave is gave rise to electromagnetic interaction. And so this kind of string loop liquid is the ether. Actually, we are looking for that for 150 years. So now we can see we find ether, which is a string liquid. Okay, but for the strong and weak interaction, we have Yang-Mills equation. That described by different wave equation, not the Maxwell equation, but the Yang-Mills equation. And can we have that? The answer is yes. And what we need to do is that we have to assume a string can have different types. Like in this picture, we have kind of red, green, and the blue string. The 3 types of string. And this string can follow certain rules. Not every string can join. They have to join following certain rules. So that's called the fusion rule of a string. It turns out that the type and the fusion rule of string determine the gauge group. So in fact, actually, string type is a representation of the gauge group. And the fusion rule actually is a fusion rule satisfied by the representation of a group. Okay. And so therefore, this kind of string liquid have a collective mode described by the non-abelian gauge theory and satisfy the Yang-Mills equation. Okay. So this is so therefore, the string net density wave can give rise to a strong and weak interaction. But those are just interaction. How about the matter? So we have a lot of matter here. There's a quark and a lepton. We know that the matter actually carry gauge charges. So what is a gauge charge? What is those particle carry gauge charge? It turns out that the particle carry gauge charge is just an end of strings. Remember that the vacuum have a lot of loops. So when you have an open string, the middle part open string are mixed with a closed string background. So it's kind of invisible. Only the end of string are visible. So therefore, the open string do not behave like an extended object, but behave like 2-point object. Okay. And this 2-point object actually is a gauge charge. And they interact with a string density wave in the same way as a gauge charge interact with a gauge field. So therefore, these are really just a gauge charge. Okay. And this and the fusion rule of a string led to the fusion rule of a gauge charge, and the last led to the emergence of conservation law. We know that the charge conservation is actually a conservation of gauge charge, and this conservation is emergent conservation because in the string liquid we don't have a symmetry. And there's no symmetry, there's no U1 symmetry. And but we do have a string liquid, we do have this topological excitation appears end of string. And this end of string have a special fusion rule, and this special fusion rule gave rise to the conservation of gauge charge. Actually, now there's an opinion that also from superstring theory that quantum gravity have a no global symmetry. Okay, so all the global symmetry, or so-called global symmetry we see in our universe, actually is an emergent conservation law appear in this way as a topological excitation appear as a fusion rule of end of string. Okay, so this picture kind of consistent with this recent development in quantum gravity, that the quantum gravity have no global symmetry. Okay, so to summarize that, the string density wave is a gauge field, and the end string gave rise to the gauge charge. So that's the end string is this topological excitation is what we call the electron and the quark and the lepton, things like that. But then you may ask, well, electron and the quark are fermions. The string are formed by bosons. They're just qubits. How can a string gave rise to fermionic particle? So why we have a fermion at all in our universe is again, it's a big mystery. It's just a given. We don't ask where it comes from. But now we want to ask where they come from. And so here I want to say that so actually the string, I already said that the electron can be used as the end of string, but the string itself do not contain energy. So therefore string are invisible. But however, string are not that invisible. Actually, all those strings do not carry energy, but they carry entanglement or they modify entanglement somehow. So this modification of entanglement or this hair or string attached can make electron, can make end of string into a fermion. So sometimes the end of string can be fermions. So I won't really explain why, how that appears, but I just explain what a feature. So we know that one kind of string net liquid is a superposition of all kind of string net configuration with an amplitude O +1. So in this case, the end of string will be boson. So we don't have fermion here. The end of string is a boson. So gauge charge are boson in this case. But however, we can have a different superposition. So like we have ±1 here. Okay. And then when we have a different superposition, the ground state are different, the entanglement are different. It turns out this kind of different entanglement will make end of string into a fermion. More specifically, how do you assign this ± sign to the string net wave function is the following. We need to project a three-dimensional string into 2D. Then into 2D, it's just a trick. We just project in 2D. Then we have this overpass, underpass, these two configurations. Then we say when the string fluctuates from the left configuration to right configuration, the wave function changes sign. So this kind of sign change is the give rise to this ± sign, and this kind of assignment of ± sign will make end string into a fermion. And this works in any dimension actually. Okay. So therefore, this string liquid not only gave rise to the gauge interaction, but also gave rise to Fermi statistics. So in some sense, it's a unification of a gauge interaction and the Fermi statistics. So gauge interaction of Fermi statistics in this picture really is a two sides of same coin. It just they all come from long range entanglement, this topology order. And this particular long range entanglement described by string net liquid. So the string net liquid is just a way to describe a particular kind of a long range entanglement. And that gave rise to a gauge interaction and gave rise to Fermi statistics. Actually, there's a more general entanglement and a wave function, and which may give you something beyond the gauge group, something beyond group things, and also beyond Fermi statistics. In 2 dimensions, we can have onion. In 3 dimensions, certainly we don't have onion. But if this picture in 2 dimensions, we can also have a fractional statistics. Okay. So to summarize that, if using this qubits ocean and assuming this the qubits in the qubit ocean have a particular long-range entanglement described by this string net wave function, then actually we can reproduce the first 7 of 8 mysteries. So identical particle, the wave that satisfies the Metzler equation, wave that satisfies Yang-Mills equation, and the Fermi statistics, and the fractional angular momentum. Actually, the end of string, if it's a fermion, they naturally have a speed 1/2. And also recently, we also find this quantum metabolic system, which can produce a chiral fermion. That's only left-hand fermion interact with the Yang-Mills wave. So even chiral fermion can be produced. And one can also have a Lorentz symmetry, but not naturally. The reason is that you can see in this condensed matter system, we have many modes. So we can have this Yang-Mills equation, Maxwell equation, and we can have the Dirac equation describing end of string and the fermions. But however, there are no requirement that all those equations have the same speed of light. They can have a different speed, different velocity. So in condensed matter system, it is allowed. And so therefore, we have to fine-tune the condensed matter system, fine-tune this lattice system so that all those modes happen to have the same velocity. So it's compatible with the Lorentz symmetry, but the Lorentz symmetry do not appear naturally. So we do not explain why we have Lorentz symmetry in our universe. And also, so far, we have a difficulty to produce gravitons. But I will come back to this point in a moment. So if you ignore the graviton, so for the standard model, we can claim that at the moment we have a design for the interacting quantum system, quantum magnets, such that whose low energy effect theory reproduce a standard model. Okay, and so in this picture, and so this the space actually is an ocean of qubits. This is the fundamental assumption. If these qubits have a special entanglement, basically form a string-net liquid, then the fluctuation of string-net density will be the photon, the gluon, and the string will be electron, the quark, and etc. And so in this new world view, these qubits and the many-body entanglement play a central role. And actually, we have a new mathematics to describe the many-body entanglement. It turns out to be a very abstract mathematical theory called the Brady diffusion hierarchy category, which, just like a group theory, describe a symmetry. The fusion hierarchy category theory describe a many-body entanglement, and so that will be a kind of mathematical foundation for this many-body entanglement. Okay, so how about gravity? Can we produce graviton using this qubits picture, some lattice model? And so here, let's give it a try. Okay, so we can consider rotor model. So we have a 3 rotor on each side. We have cubic lattice and 3 rotor on each side. So we call rotor called the XX rotor, YY rotor, ZZ rotor. And we also place a rotor on the squares. So we have a XY rotor, YZ rotor, and a ZX rotor. Okay, so we have a 6 rotor in different orientation. Okay, and certainly each rotor has its own canonical variable as angular momentum. Okay, so therefore we can write down a lattice Lagrangian describing this lattice rotor model, and so we have some interaction, complete the Hamiltonian to describe the interaction. So roughly speaking, we can see that in this rotor model have a 6 mode. We have 6 rotor. We also have 6 mode, and because their tensor index, so the index under rotation symmetry, it's not hard to convince yourself to see that this rotor is described by symmetric tensor field in the continuum limit. Okay. And the symmetric tensor field have a 6 mode, just have 6 rotor. In terms of helicity, it have helicity 2, helicity 0, helicity plus minus 1, and helicity plus minus 2. Okay. And then to produce gravity, we should somehow get rid of helicity 0 and helicity plus minus 1 and keep only helicity plus minus 2. How to do that? There's one way to do that is we can design this Hamiltonian. It's very complicated. Actually, we find a design such that the helicity plus minus 2 mode have a finite velocity, but other helicity mode have almost a 0 velocity. Not only they have a 0 velocity, we also design the Hamiltonian so that they have very strong quantum fluctuation. Okay, when they have very strong quantum fluctuation, remember those rotor field, those theta field are angular field. If their quantum fluctuations are bigger than 2 pi, that means the angular momentum are quantized, and those modes actually became gapped. So this is the compactness of this scalar field. Because those angular fields are compact, this strong quantum fluctuation really make them gapped. So this actually, this can be done. In this paper, we show that exactly how to achieve this. So therefore, we design a lattice rotor model whose low energy mode is only helicity plus minus 2. So it's kind of like a graviton. Okay. But however, there's a catch. Okay. And actually, we have a 2 lattice model two lattice rotor model. In the first model, it's a more theoretically controlled, and so we can have a controlled approximation to obtain their low energy properties. So remember, this graviton is a low energy property, and from the lattice Hamiltonian to derive low energy property is very difficult. Most time we cannot do it. But however, these lattice models are specially designed, so it's kind of soluble in certain way, called soluble in the semi-classical approximation. Okay, so in this designed lattice Hamiltonian, and we can use a semi-classical approximation and reliably and the controlled approximation derive their low energy property and show that indeed all other modes are gapped, and there's a helicity plus -2 mode gapless, but they have this soft dispersion, this omega k cube dispersion. And it's very weird. You say, why omega k cube? Why not omega k squared? Why not omega k to the 5th power, 4th power? Why not other power? And for those people who are familiar with this Lipschitz gravity, you will see that actually Lipschitz gravity have dispersion relation omega k cube. So essentially what we obtain here is a lattice realization of a Lipschitz gravity. Okay. And so Lipschitz gravity can be put on the lattice. We can have a UV regulation of a Lipschitz gravity. And this is there's a fundamental reason why this dispersion relation appears. And we also construct another lattice model because to have this linear dispersion relation and also helicity plus -2. But unfortunately, in this second lattice model, to deriving this result, we do not have a semi-classical approximation. So therefore, this result is under uncontrolled approximation. So we don't really know whether this result is correct or not. So, but under some uncontrolled approximation, we can get this result, but really we don't know. And so we need a numerical calculation to really show whether this works or not. So this is a big question. It's a three-dimensional quantum lattice model, strongly interacting, and it's almost hopeless to do numerics. And yeah, so this became an open question. And I want to say that this rotor model also works to produce photons. Actually, in this case, we just put a rotor on the links. So therefore, those rotors just like behave like a vector field. The link is like a vector direction. So for the rotor on the link, we have a vector field. Again, using similar idea, we can design. We have a vector field have 3 modes. We can design the Hamiltonian such that longitudinal mode have a very low energy, and the transverse mode have a high energy. And so then the longitudinal mode somehow is gapped because those rotor have a angle is angular variable. Then this way we obtain this rotor model, lattice rotor model, such that the low energy excitation are just two transverse mode. So that's really photon mode. So that's how we get a photon from a lattice model. So therefore, nowadays this development in quantum matter, nowadays we know how to design quantum model on the lattice to produce a photon, Yang-Mills equation, massless fermion, Dirac fermion, and etc. So from purely a bosonic degree freedom, so we can do that. But however, to produce a linear graviton, we have trouble. At the moment, we have trouble. Okay, so this is so we can see that the standard model can be simulated by the quantum material or by the quantum magnets. Okay, and so actually in condensed matter, there's a very strong activity in experiments try to looking for those quantum matter with topology order, and with say like with a spin wave that's satisfy Maxwell equation, and or maybe some emergent fermion, emergent anion, and etc. So it's a very strong push, and there's a lot of candidate material. And there's a lot of sign. Those material have a topology order, have a Maxwell equation, but unfortunately at the moment those material quality is not that perfect. So the interpretation have a room of ambiguity. So we are not completely certain at the moment. So we are still trying in this direction. Okay. And but aside from simulating standard model, we may ask if you can simulate the standard model using qubits. Maybe our universe is a qubits ocean. Is a standard model is come from this way. It's coming from qubits, coming from string net. Okay. Then what is the experimental consequence of such assumption? So one experimental consequence is the following. Probably there's no UV global symmetry, you know, and we don't need that. And but this is a little bit philosophical, and the real experimental consequence is the following: that all gauge fields are compact. Actually, from qubits model, we cannot have emergent non-compact gauge field. The emergent gauge fields are all compact, and also all the representation of a gauge group are present as excitations. So we cannot have a missing representation. So those are predictions, you know, and related to these two predictions is that all the composite fermion must carry non-trivial gauge charge. You know, we know that electron carry non-trivial gauge charge of 1, 2, 3, and the quark carry non-trivial gauge charge of 1, 2, 3. But some combination of electron and quarks probably are totally neutral. So therefore, in the standard model, the standard model do not satisfy this property. There are some composite fermion carry no gauge charge. And also the SU5 one unified theory do not satisfy this property. So therefore, if you assume the emergent standard model from qubits ocean, that rule out the standard model and the SU5 one unified theory. But however, the SU10 one unified theory have these properties. Actually, in a few days ago, there's discussion for SU10 and to discuss their different feature actually is related to this. And the SU10 when the SU10 break down to U1 cross SU2 cross SU3, actually there's additional unbroken Z2 gauge field, which is beyond standard model. And this Z2 gauge field will give rise to new cosmic string. So therefore, this the qubits ocean picture predict new cosmic string. And any scale is not known, and the experimental bound probably is 10 to 15 or maybe 10 to 10. So there's some bound. So I'm not really familiar with this area. Okay. Another prediction for this is that looks like this 15 wire family, 15 wire fermion per family in standard model, again, is not compatible with this qubits model. The qubits model prefers 16 wire fermion per family. So it means we have stereo neutrinos. And the mass gap of stereo neutrino may be similar to this string gap. Yeah, I don't know. Yeah, there's one possibility. So therefore, those are kind of beyond standard model favored by this qubits ocean picture. So there's some kind of testable consequence of this qubits ocean picture. Okay.
Professor Van,
yeah.
Before you start, you have 5 minutes.
Okay, yeah. So maybe I'll finish this. Yeah, this last I want to make a comment. That is you know, here we describe the qubits model, which have emergence of a standard model. Somehow this kind of emergent picture or this condensed matter study, for some reason, are related to our study of quantum gravity. You know, in recent years, there's a field in quantum gravity. They discuss what kind of effective field theory are compatible with gravity. You know, there's many effective field theory, but some of them are incompatible with quantum gravity. It's called a swampland, a swampness. But some effective field theory is compatible with quantum gravity. It's called a landscape. And we have a similar issue in condensed matter. Again, we can write down many effective field theory, which are incompatible with the qubits model. The qubits model on the lattice. Qubits model on the lattice can only produce certain kind of effective field theory at the low energy. So we can call that a condensed matter landscape. The one which can be the effective field theory, which can be produced by qubits model on the lattice. Okay. And then it turns out that the quantum gravity landscape and the condensed matter landscape may be identical. They demand the same set of low energy effective field theory. And for example, this no global symmetry conjecture, the coordinates conjecture, and the completeness conjecture. And the completeness conjecture probably is this all representation of gauge group are present. So this requirement of effective field theory at the low energy from quantum gravity and the requirement of effective field theory from lattice qubit model appear to be the same. And so it's quite amazing. These two branches of physics are developed independently, and at the end, these things produce a very similar result. So I don't understand why this is true. I find it's very amazing. So that's making me to thinking, is this quantum gravity local qubits model? Since there's some such coincidence, so there's some connection between condensed matter physics and quantum gravity. So to end, I will say that maybe matter and space are really quantum information, the gauge interaction Fermi statistics, and the sense of space may all come from the long-range quantum entanglement. Thank you. Yeah.
Thank you for this very nice talk, Professor Wen. We can take some questions. I think there were some questions while you were speaking. One of them was from Qaisar Shafi. If he wants, Professor Shafi, are you there? If you're there, you can unmute yourself and ask your question. He may not be here, and okay, he did not write his question, so I will be moving on with another one. There is a question from Nadir Yavuzkan. He's asking why topological order has been defined as long-range entanglement. Also, why the entanglement in the text has not been defined as ranged interaction. Is there any difference?
Okay, at the beginning, the topological order is just a name. We realize that there are certain phases of matter which are not characterized by symmetry breaking. It's not characterized by the symmetry breaking order parameter. So we need to characterize it by something. And so at the beginning, we find this robust quantity degeneracy and this modular transformation and things like that to characterize this new phase of matter. And we just gave it a name, topological order. It's just a name. And this name is motivated from the realization that the low energy effective theory of this kind of a new phase of matter are strongly related to the topological quantum field theory, which was introduced in the same year, in 1989. And so therefore, just a moment. So therefore, I kind of named this new phase of matter as topological order because their low energy effect theory is a topological quantum field theory. And so that's why we call this topological order. Why topological order is related to the quantum entanglement? We don't know. Topological order is introduced in 1989. At that time, quantum entanglement is certainly known words, but it's not very popular words. And I don't know the qubits. I don't know when the qubits words was named. Maybe after 1989. And so what I try to say that at that time, people do not think about the quantum information, and so there's a decoupling from topological order just viewed as something weird, it takes maybe 20 years. You know, during 1990s, the quantum information kind of take off. Then condensed matter people start to think about quantum information, try to learn quantum information. Then we start to realize that, yeah, this topology order, which we define differently, it's directly correspond to entanglement, and correspond to a particular entanglement called the long-range entanglement. So after 20 years later, so we formulated the way to use a long-range entanglement and quantum circuit, this quantum information language, to more rigorously define what is a topology order. So that's kind of a story. That's the topology order is a concept from condensed matter, but later we realized that they have very close tie with the quantum information. And why they have something to do with interaction is as I explained here. And when you have a material with a topology order, you may have a collective excitation satisfy Maxwell equation, and that is an electromagnetic interaction. So that's a definition for electromagnetic interaction, is that interaction caused by the collective mode that satisfy Maxwell equation. And so with topology order, and we are able to find this kind of a condensed matter system, design the condensed matter system which have a Maxwell equation in it. Yeah.
Thank you, Professor Wen. I guess we have a question from you, Professor Demir. Please.
Thank you for the talk. I was wondering, I mean, you have certainly given strong arguments in favor of emergent nature of the light, gravity, matter, the spin statistics, etc. But I mean, do you have a concrete model? For example, do you have Higgs sector of the standard model as a concrete model as a result of this mechanism?
Thank you. Yeah, this is a really good question, and the simple answer is no. And because I study condensed matter, not particle physics, so to really study Higgs sector, you really need to know the details, all these details of particle physics, which I don't have. But I wish I can do. But
okay,
that's maybe that's maybe too wide. But the point, let me put it this way: in Higgs model, there are some constraint on Higgs model, because Higgs field is a bosonic field, and for example, the bosonic field should not be in the spinor representation of SU2. You know, the spinor representation of SU2 probably has to be fermion. So there are some constraint. So in a sense, I believe that if you believe standard model emerged from this cubical ocean, then there are some constraint on what kind of Higgs field we can put in, so that all the composite fermion must carry gauge charge. This can put a constraint on the Higgs sector. Certain Higgs representation is not allowed, because that makes certain fermion gauge neutral and also fermion. And I did not study in this direction, but I believe there is a constraint in this. Okay. And maybe this constraint is so severe that they rule out this picture, because looks like we have pretty good knowledge what the Higgs sector should be. And maybe Higgs sector already killed this idea. So this is the picture I present here is falsifiable. It's actually, especially by your question, this Higgs sector may not work. You know, I did not study this. Yeah. Very, very good question. And I wish I can really study this.
Thank you. Thank you for the answer. Thank you.
We have a few more minutes for an additional question. But if there is none, thank you for this very nice talk, Professor Wen.
Thank you.
Oh, there is sorry. There is another question apparently from Shahram Jalalzadeh. If you can unmute you, we can take your question.
Thank you, Professor Wayne, for your good representation. I had a question about the time, nature of time here. You started with space, that space in your tour is the ocean of qubits. What about time? Could you please give a bit of information about the time?
Yeah. And
thanks.
You know, again, I have to say that I wear the hat of condensed matter physics, which means it's forbidden for me to study time. So then because that's not the condensed matter. You know, and as long as I study Hamiltonian, I can still claim I'm doing condensed matter physics. And but that's a certain joke. And the time, certainly, you know, what I really try to say is that the presentation I have here are really based on the Hamiltonian formulation and based on quantum physics. Okay. In quantum physics, the time is absolute. Okay. So therefore, if you want to study times, I need to abandon quantum physics. And then I don't know where do I start. You know, here I try to push quantum physics to the extreme. We find we can have everything in standard model emerge from qubits within the framework of quantum physics. And maybe it's okay, maybe it's right, we have trouble in gravity, because gravity may involve time, because in quantum relativity tells us the time is also dynamical, just like a space. So, and also Lorentz symmetry, we have trouble to produce Lorentz symmetry, also have same reason. We treat the time as an absolute time. So therefore, we have no natural interpretation of Lorentz symmetry. We need to treat the space and time at equal footing to have a natural explanation of a Lorentz symmetry, and maybe to have a natural theory for gravities. But because I'm limited to work within quantum theory with an absolute time, with a Hilbert space, with Hamiltonian, so I have no answer to time. But my comment is really that any study of time as dynamic variable need to abandon quantum physics. And so that means we need to formulate a new theory where time is not absolute. And at the moment, we don't have any clue how to abandon quantum physics. And so this became a rather difficult issue. Yeah.
Thank you for your answer, Professor Wen. Are there any other questions? Let me ask so that I don't skip any other questions. Okay, so I don't think there are any more questions, any further questions. So thank you once again.
Thank you. Yeah.
If you kindly please stop sharing your screen, maybe we can, Professor Korda can.
Let me see, I have to share it.
Thank you.
Okay. Yeah.
Professor Korda, you can start sharing your screen.
Yes, I am here. I start, do you listen me? Yes?
Yes, we can hear you very well.
Then I start with sharing my screen.
Yes. And while you do, let me start introducing you. So you will be, Professor Korda will be giving the closing talk of today, the last day of the meeting. And he's one of our international organizers. He's from Istituto Levi in Italy. And he's also affiliated with other places such as International Institute for Applicable Mathematics and Information Sciences in Florida, Birla Science Center in India. He also has other responsibilities such as being the editor-in-chief of Journal of High Energy Physics, Gravitation and Cosmology, and of Theoretical Physics. His research interests lie in gravitational waves and cosmology, and today he will be talking to us about the secrets of planets perihelion between Newton and Einstein. So the screen is yours, Professor Korda.
Thank you very much. Do you see my screen now with the presentation?
Yes.
Okay, then we can start. First of all, I would like to thank and to congratulate with Professor Aydıner and the local organizing committee, because they made an excellent work with this very prestigious conference. I am also very honored to can deliver this talk, which will be also I think the closing talk of the conference. Then we can start. The title of my talk is, as you can read in the presentation, The Secrets of Planet Perihelion between Newton and Einstein. And let us start with the abstract. In this talk, it is shown that contrary to a long-standing conviction, which is older than 160 years, the advance of mercury perihelion can be achieved in Newtonian gravity with a very high precision by correctly analyzing this equation without neglecting Mercury's mass. The Newtonian formula, which will be derived of the advances of planet perihelion, breaks down for the other planets. The predicted Newtonian result is indeed too large for Venus and the Earth. Therefore, it will be also shown that correction due to gravitational and rotational time dilation in an intermediate framework which analyzes gravity between Newtonian theory and Einstein general theory of relativity can solve the problem. If one adds such correction, a result consistent with the one of the general theory of relativity will be indeed obtained. Thus, the most important result that I'm going to present in this lecture are two. The first one, it is not correct that the Newtonian theory cannot predict the anomalous rate of precession of the perihelion of planet's orbit. The real problem with the Newtonian framework is instead that a pure Newtonian prediction is too large. Second, perihelion precession can be achieved with the same precision of general relativity by extending Newtonian gravity via the inclusion of gravitational and rotational time dilation effects. And this talk arises from a research paper that I published 1 year ago in Physics of the Dark Universe. This is the reference. Christian Corda, Physics of the Dark Universe, Volume 32, May 2021, number 100-834. Then I will, in this lecture, I will use the approximation of circular orbit, but I have shown in the cheated paper that one can give, by using the same idea, also more precise calculation. I prefer to discuss the approximation of circular orbit because I think the real, the very important use of this problem can be better understood in a circular orbit. Okay, then one starts from the case in which Mercury's mass is considered negligible with respect to the mass of the Sun. That means one considers the planet as being at its mass immersed in the Newtonian gravitational field of the Sun. This is a very common assumption in astrophysics. In addition, one considers Mercury's orbit as being circular instead of elliptical. In any case, this is the case under consideration here is the simplest one. But I have also to recall that all the orbits of the planets in the solar system are more circular. Then this remains a very good approximation. Then one takes the origin of the frame of reference in the center of the Sun. In that case, if one uses the traditional Newtonian equations in order to obtain the orbital period, one has to merely equal the gravitational force with the centripetal one, as in the first equation in this slide. In this equation, in the first equation, J is the big J is the gravitational constant, big M is the solar mass, little m is the mass of Mercury, and R0 the orbit's radius, with V0 the velocity of rotation of the planet. Then from previous equation, one easily get the velocity of the Sun as the second equation in this slide. Okay. From this equation, then one can also calculate the Newtonian orbital period as the first equation in this slide. T0 is the ratio between 2p R0 to 3 to 2. Divided the GM, the square root of GM. Okay. To this corresponds an angular velocity which is given by the second equation in this slide. Then in radians per revolution, the angular distance that Mercury sweeps during the Newtonian orbital periods is simply given by 2p. Okay. Now let us ask, what does it happen if one removes the approximation to consider Mercury's mass negligible with respect to the solar mass? One argues that a Newtonian observer set in the center of the sun must replace the forces equality with the following one, okay? Because this is nothing else than relative force acting between the sun and Mercury. In fact, the Newtonian law of universal gravitation can be written down in this general form for Mercury and the sun in this form. Okay, this is the traditional equation of the Newtonian interaction for an external inertial observer. And in this equation, R0 is the distance between the sun and Mercury, while UR is the unit vector in the radial direction. Then for an external inertial Newtonian observer, the Newtonian equation of motion are the two ones that appear here, okay, respectively. And in those equations, ES is the acceleration of the sun and AM is the acceleration of the planet, in this case of Mercury. Then one obtains the relative acceleration of Mercury with respect to the sun with this formula, the first formula in the slide. Thus, the total force acting on Mercury, as it is seen by a Newtonian observer, centering the center of the sun, because now the center of the sun is no more an inertial observer, but a non-inertial observer, because there is the back creation of the planet. This is the key point, is this one, okay? And this equation immediately justifies previous forces equality. Then one gets immediately the perturbed velocity of rotation of the planet with respect to the sun as this final equation in this slide. Now, if you confront this equation with the previous one, with the velocity v0, which was here, you can see that V in the non-inertial reference frame of the sun is greater than V0. Okay, this is exactly the key point which will permit to obtain the precision in Newtonian physics. Why? Because the time T0 is the same for both the reference frames, the approximated inertial reference frame and the correct non-inertial reference frame of the sun. Okay, then this corresponds to a period T which instead is minor than previous period. This is the key point. As it is also big M plus little m elevated to 1 to 2 is equal. This is m elevated minus 1 to 2, which multiplies 1 plus the ratio between little mass and grand mass, the mass of the planet, the sun, again elevated to minus 1 to 2. If one insert this equation in the above periods, then one gets that this is the key point. One can see that the period in this case is smaller than the period previous period. Okay, the period in the approximated inertial frame of the sun. Then one gets a corresponding perturbated angular velocity, which instead is higher than the unperturbed angular velocity. Then the final result, in the non-inertial reference frame of the sun, the angle that Mercury sweeps during the period T0, which is invariant in both the reference frames, is longer than 2p. This is the equation, is 2p, which multiplies 1 plus the ratio between the mass of the planet 2 times the mass of the sun. This is in radian per revolution, where in the last step, the first order approximation in the ratio between the mass of the planet and the mass of the sun has been used. Because it is, of course, the mass of the planet, the mass of Mercury, is much minor than the mass of the sun. Then, in each complete revolution around the sun, Mercury sweeps an angle larger than the unperturbed angle, and then difference in radius per revolution is exactly P, which multiply the mass of the planet to the mass of the sun. And this is the Newtonian formula of planet's perihelion. If one now checks the NASA official data, one gets for Mercury a value of mass of 3.3 for 10 to 23 kilograms, the mass of the sun, which is 1.9 for 10 to 30 kilograms. And one, by replacing the values, gets a value of precision in radian per revolution of order 10 to minus 7, okay, which corresponds to about 0.107 arc seconds. On the other hand, the Mercury-Earth ratio of the topical orbit period is 0.241. Thus, one gets 44.39 seconds per tropical periods. And this represents a remarkable result that shows that despite the above computation has been made in the approximation of his circular orbit, the correct value of the contribution of Newtonian theory to the precision of perihelion for Mercury per tropical century well approximates the value of about 42.98 seconds per tropical century of general relativity, and the well-known observational value of 43 seconds per tropical century. Okay. And as I previously told you, there are two more precise approaches which permit to obtain the same result in my paper. Okay. Those are one, analyzing Mercury orbit as harmonic oscillation, which is a traditional method to attempt to see if there are precession in the orbits in Newtonian physics, and two, via the Kepler's law. In order to film when the interested scholar, the interested student can read my paper that I repeat here, Christian Korda, Physics of the Dark Universe, Volume 32, May 2021, number 100-834. On the other hand, the approximation of circular orbits permits to clarify the physical meaning of my Newtonian formula. It is Mercury back reaction in terms of Newton per level motion. To every action, there is always an opposite and equal reaction that generates the advance of perihelion of Mercury in the Newtonian framework. Okay. But now one has also to see what happens for the other planets. Okay, for the other planets, there is a breakdown of this Newtonian formula. Let us see what's happened. Let us apply the Newtonian formula to Venus trajectory. The mass of Venus is 4.87 per 10 to 24 kilograms. Then in this case, obtains a value of precession of 7.68 for 10 to minus 6 radians per revolution. That corresponds to about 1.6 arc seconds. The Venus-Earth ratio of the tropical orbit period is 0.615. Then one gets 258.6 seconds per tropical century. But this is about 30 times larger than the observational value of 8.62 seconds. Similar results are obtained if one considers Earth's data. In that case, the mass of Earth is M of Earth is 5.97 for 10 to 24 kilograms, and this gives us a precision value of 9.42 for 10 to minus 6 radian per revolution. That corresponds to about 1.94 arc seconds. Then one gets 194 seconds per tropical century, and this is about 50 times larger than the observational value, which is of 3.83 seconds. Thus, I have shown that, contrary to a long-standing conviction, which is older than 160 years, the real problem of Newtonian theory concerning the anomalous rate of precession of the perihelion of planets' orbit is not the absence of a prediction. The real problem with Newtonian physics is that such a prediction is too large. Okay, in order to obtain a correct result, I will extend the Newtonian theory by adding to it gravitational and rotational time dilation effects. In fact, another key point is the following. In Newtonian physics, time is absolute. So time passes in the same way in one reference frame as in the other reference frame. In the framework of the anomalous rate of precession of the perihelion of planets orbited, time dilation effects must be taken into account. Here, one realizes an analysis in an intermediate framework which analyzes gravity between Newtonian theory and Einstein's general theory of relativity. It will be indeed shown by taking into account both gravitational and rotational time dilation that the Newtonian framework will achieve with high precision the advance of perihelion completely consistent with the general relativistic results for all the planets. For the sake of simplicity, this approach will be again performed in the approximation of circular orbit. The period T in previous equation measured by Newtonian observers that sees time as absolute. But based on gravitational time dilation, the period that is really measured by a relativistic observer must be different. In a general relativistic framework, gravitational time dilation is well approximated by this equation that one can find in all the textbook of general relativity, in the book of gravitation, Metzler, Thorne, Wheeler, also in the book of Landau. Okay, this formula is presented in I think in all the books of general relativity. In this formula, G00 is the coefficient of the coordinate time in the metric describing the gravitational field, while Tg is the proper time between two events for an unmoved observer, which is located at a distance R0 from the source of the gravitational field. In other words, this is a local observer, while TL is the coordinate time between the events for an observer at an infinite distance from the source of the gravitational field. Then, in a weak field approximation, one can consider a local inertia non-rotating free-falling coordinate system with origin at the sun center, and writes an approximate solution of Einstein field equation in isotropic spherical coordinate, which is the equation in this slide. Then one gets for the sun gravitational field, the light time is given by the first formula in this new slide, slide. Here, Rg is the sun gravitational radius and R0 the radial distance between the sun and the planet. Then one considers the variation due to time dilation as being correction with respect to the Newtonian observer. In other words, here I am defining a new observer having again the origin of the frame of reference in the center of the sun, which sees again the spatial direction as being a Newtonian observer. But the new observer measures the time between two events by using Tg in the above Tg in the above equation instead of the absolute Newtonian time. One can define this new observer as correct Newtonian observer, C and O. Then one also notes that together with the time dilation, there is also a variation of the proper radial distance between the sun and the planet with respect to a Newtonian observer. If this latter observer measures the distance, say R0 equal the speed of the light for T0, the correct Newtonian observer will measure a distance which has to be corrected with this equation. The correction to the proper radial distance between the sun and the planet, which is due to spatial curvature, here will not be considered because one is assuming that the correct Newtonian observer sees the spatial direction as being a pure Newtonian observer, which means that the spatial direction are considered as being Euclidean. Then one performs the following replacement concerning time and distance in the formula of the Newtonian period. Okay, one has to insert the replacement in the first equation in this slide, and to obtain in the second equation of this slide the correct time Tf, which is given by this equation. And this represent the general relativistic perturbed orbital period, which is measured by the correct Newtonian observer. This will permit to obtain the corresponding perturbed angular velocity and the angle that Mercury sweeps during its total revolution. Such an angle will be larger than 2p, with a difference with respect to the Newtonian unperturbed angle, which is given by this equation. Okay, this equation is the first general relativistic correlation to Newtonian theory in terms of the real precession of the periodium. But one also a rotational effect to consider. In fact, rotation generates indeed another dilation effect. In order to understand the necessity of an additional effect of rotational dilation, one has to stress that the time differences of the previous analysis have been calculated by the correct Newtonian observer that sees the planet as being at rest. Then a key point is that the planet is moving instead. Thus, the correct Newtonian observer must consider an additional effect, which is due to rotational time dilation. This rotational time dilation is due a very long-standing story. Such a story started from a famous paper of Einstein. You can see Albert Einstein, the collected papers, volume 6, Berlin years, written 1914 till 1917. And there is also an English translation supplement. The key points of this idea of Einstein is the Einstein equivalence principle, which enables the equivalence between gravitation and inertial force. In a full general relativistic analysis, one considers a transformation from an inertial coordinate system with the zeta axis perpendicular to the plane of the rotational motion to a second coordinate system which rotates around the zeta axis in cylindrical coordinates. For a flat Lorentzian coordinate system, the metric is the standard metric of Lorentz-Minkowski of spatial relativity, which is the first equation in this slide. Okay, but one considered the following transformation to a reference frame rotating with an angular velocity omega. This transformation one, which is the Langevin transformation, which generates the famous Langevin metric, which is the first equation in this new slide. The key point is that the Einstein equivalence principle permits to interpret the Langevin metric as a static gravitational field. Thus, one obtains the following relation for the rotational gravitational field. Okay, again, the proper time is connected with the time coordinated by this new equation. In this equation, tau is the proper time between two events for the rotating observer at a distance r0 from the origin and having an angular velocità omega 0. And t is the coordinate time between the events for a static observer at the origin of the coordinate system. Then one can rewrite the last equation in function of the gravitational radius of the sun, obtain the first equation in this new slide. This generates a correlation to the period measured by the correct Newtonian observer. Then one must again correct TF to TT, which is again, you can see there is another contraction of time, which is the final contraction of time. And this will permit to obtain the further perturbed angular velocity and the final angle that Mercury sweeps during this revolution is the final result here. The total precession of the planet is about 3 pi multiplied for the ratio between the gravitational radius and the distance between the sun and the planet. And remarkably, this result is exactly the same result of the general theory of relativity for a circular motion. Okay, thus my analysis obtained a perfect consistency with the original result of Einstein for the precession of the periodium of the planets. Then here we have the conclusion remarks. It has been shown that, contrary to a long-standing condition older than 150 years, the orbit of Mercury behaves as required by Newton's equation with a very high precision if one correctly analyzes the situation without neglecting the mass of Mercury. The results obtained are remarkable. The real value predicted by Newtonian theory concerning the advance of the periodion of Mercury is of 44.39 seconds per tropical century. That well approximates the value of about 42.98 seconds per tropical century of the general theory of relativity, and also the well-known observational value, which is of 43 seconds per tropical century. Thus, the real difference between Einstein's and Newton's prevision between Newtonian theory and the general theory of the relativity concerning the advance of the periodion of Mercury is not of about 43 seconds as astronomers and researchers were thinking for more than 100 years. Instead, such a difference is only 1.41 seconds per tropical century. The physical interpretation of this result is that it is Mercury's back reaction in terms of Newton's third law of motion that generates the advance of the periodion of Mercury in Newtonian framework. General relativity remains more precise than Newtonian theory regarding the precession of Mercury periodion, but the difference results to be very, very little. On the other hand, the Newtonian formula of the advance of planets periodion breaks down for the other planet. And this means that the predicted Newtonian result is too large for Venus and Earth. Thus, I have also shown that correlation due to gravitational and rotational time dilation in an intermediate framework which analyzes gravitational theory between Newtonian theory and Einstein's general theory of relativity can solve the problem. In fact, by adding such correction, a result consistent with the one of the general theory of relativity is well obtained. Then, finalizing and summarizing, the most important result of my lecture are two. One, it is not correct that Newtonian theory cannot predict the anomalous rate of precession of periodion of planet's orbit. The real problem is instead that a pure Newtonian prediction is too large. Two, periodion precession can be achieved with the same precision of general relativity by extending Newtonian gravity via the inclusion of gravitational and rotational time dilation effect. Again, I stress that this talk has been derived by my paper, Christian Corda, Physics of the Dark Universe, volume 32, published on May 2021, 1 year ago. The number is 10834. Thank you very much.
Thank you, Professor Corda, for this nice talk. We can take some questions. We are a little bit early. Professor Demir, you can unmute yourself.
Thank you for the talk. It's indeed interesting. I mean, your results for Mercury is really meaningful. I mean, agrees with the data. I was wondering, for example, while you were computing the shift and the angle for Earth and Venus or other planets, maybe you should have taken into account the presence of other planets, because in that case, their gravities would partially cancel the gravity from the sun. And I would suppose that you might get something closer because, you know, I mean, gravity would be in the opposite direction compared to the sun's direction. I mean, I'm just speculating somehow. Maybe you have already checked it, but I was just wondering. Thank you.
Yes, this is Professor Demir. This is a very interesting point, which was raised by the referee of my paper.
Oh, I was not the referee. Okay.
No. Yes, but but this no problem for this. But the key point in the opinion of the referee, and they reported this in the paper because it is a good point, it's that Mercury is the most internal planet of the Sun.
Right.
Then maybe
closest to the sun.
Okay, there's not for the other planet one need at least not a two-body problem, but at least a three-body problem, which becomes very complicated. Okay, this can be one of the reasons because the formula works only for Mercury. Another reason is that the time dilation becomes the dominant effect and completely cancel the effect of the Newtonian effect. But your point is very profound.
I see. Thank you.
Do we have any other questions? Well, it seems that there is no other questions, so I thank you for this interesting talk once again, Professor Korda. There were many great talks, and I will leave the screen to Professor Aydıner for some closing remarks.
Thank you, Korda, for very nice talk. I want to give a short speech for closing. We have successfully completed this meeting. I received very nice feedback from the speakers and participants during the meeting. It's a pleasure to host this prestigious meeting. First of all, I would like to thank our invited speakers. I am grateful to participants who show great interest. I also thank our membership of International Organizing Committee, Professor Siddharth, Marisa, Christian, Mark, Douglas, and Claus. And many thanks to chair and moderators who have the critical roles for managing all seasons. I am also grateful to Ayhan and Emre, our members of our university, for their technical help. And thanks my friend Özgür and Erkan, who helped me in my office during the meeting for 4 days. I would like to express my gratitude to our rector, Mahmut Haq, and Istanbul University. They give us the chance for FFP organizing. On the other hand, Klaus and Leonard couldn't attend, as you know, our meeting due to health reasons, health problems. I hope they get well soon. Thank you very much to everybody. I hope we can meet next year in physical meeting. Thanks again. See you next meeting.
Thank you. Thank you for organizing.
Thank you, Ekrem Hocam.
This was a fantastic symposium. Thank you very much for arranging it.
Thanks, everyone.
Thank you indeed. Thank you.
Thank you very much.
Thank you, Qaisar.
Thank you, Ekrem Hocam.
Hocam,
Ekrem Hoca, I hope you can get some rest after this. So.
Yeah.
It is very difficult because I want to go to my home. It is
and crash. Just sleep.
Yes.
You will get a very deep
I am very tired. Indeed, I can sleep in my home. Yeah. Thank you. Thank you, Izzet. Thank you, Qaisar. Thank you. I hope see you again.
Excellent organization, I must say. Excellent.
Thank you so much. Dennis, okay.
Hope we can meet in person. Yep, that would be fun.
Fine.
Yeah, in person next time.
I hope next time.
All the best. Take care. Bye-bye.
All the best. Good night.
All the best. All the best. Good night. Good night.
Bye-bye. Good night.
Bye-bye.
Good night. Bye-bye.
Tekrar çok teşekkürler, çok tebrikler. Harika bir sempozyumdu. Her konuşma mükemmeldi. Teşekkürler.
Esasında daha katılımcılarımız olacaktı ama şöyle bir şey oldu. Biz toplantıyı çok geç bir zamanda organize ettik. Dolayısıyla yani aslında 15 Ocak'ta çıktı bu toplantı. Birkaç gün içerisinde organize ettik. Ama şey yapamadık, siz söyleyin. Yani düşündüğüm bazı konuşmacılar önceden programlarını yaptıkları için katılamadılar ve üzüntülerini belirttiler bize. Umarım...
Yine de çok tebrikler yani. Bir kez daha takdir ettim. Bu kadar kısa zamanda bu kadar güzel bir sempozyumu bir araya getirmişsiniz.
Evet.
Harika olmuş.
Yani epeyce yani esasında toplantıyı organize etmek o kadar zor olmadı ama şu son 4 gün ve öncesinde birkaç hazırlık evresinde bayağı bir zorlandık. Bu arada moderatör arkadaşlarımız işte burada Kerem, Cem var, Durmuş Hocam, şehir olarak İzzet, Biddoğlu arkadaşımız çok emek verdi, çok yardımcı oldular. Hepsine ayrı ayrı teşekkür ediyorum. Yani sizler olmasaydınız bu toplantı ortaya çıkmazdı. Yani işbirliği, ondan sonra bilimsel kültürü, onun öyle bir perspektifle bu işi ortaya çıkardık. Yani bu tek başıma benim yaptığım bir şey olmadı. Bütün arkadaşların çabası ve emeği var. Hepsine ayrı ayrı teşekkür ediyorum.
Ellerinize, aklınıza sağlık. İyi geceler.
İyi geceler.
Aksine yani
Hoşça kalın. Çok teşekkürler arkadaşlar.
İyi geceler.
İyi geceler. Teşekkürler.
Emre'cim, sana çok teşekkür ediyorum. Bizim elimiz kolumuz oldu Emre. Bir de Ayhan arkadaşımız var. Rektörlükte bilgi işlem ve işte uzaktan eğitim alanında çalışmalar yapan arkadaşlarımız. Onlar gece bu saate kadar bizi beklediler. İşte sabah 7'den akşam 12.30'a 1'e kadar. İşte Zoom toplantılar kayıtlarımızı aldık. Yani epey yani hem bulut sistemine kaydettik, hem üniversitenin kişisel bilgisayarlarına kayıt alındı, hem Facebook'ta yayınlandı, YouTube'da da yayınlarımız çıktı. Bazı yerlerde bir problemler olmuş, durmuş ya da birkaç arkadaşımız uyarmıştı. Tam hatırlayamıyorum.
Dünkü şeyde hocam.
Evet.
Robert Mann'ın konuşması karışmış hocam.
Yani o YouTube'da bir herhalde bir
YouTube.
Evet, o kısma bakacağız. Biz arkadaşlarla da konuştuk. Oraları düzeltebileceksek düzelteceğiz. Tamam. Tamam hocam, çok teşekkür ederim. Yani evet, ben aslında arkadaşlardan videoyu dönüp izlerseniz, hani videolarda bulabileceğiniz hataları bize bildirirseniz yaparız. Biz de arkadaşlara iletiriz. O şekilde problemi çözmeye çalışırız diye düşünüyorum.
Ekrem hocam çok teşekkür ediyorum. Harikaydı. Elinize sağlık.
Katıldığın için bütün konuşmaları çok izledin. Ben de çok mutlu oldum. Durmuş hocam, Nadir bizim üniversiteden, fizik bölümünden mezun bir arkadaşımız.
Öyle mi? Ha.
Evet.
Nadir Hoca'nın adını gördüm ama tanışmadık. Tanışırız umarım başka zaman. Yani.
Selam hocam. İnşallah.
Selam hocam. Selam. Hatta LinkedIn'den girip baktım sizin isminize. Tanışmadığınız için görebilirsiniz.
Çok iyi.
Teşekkür ederim hocam. Sağ olun.
Şimdi eklerim ben sizi. Tamam.
Tamam.
Çok memnun oldum. Ekrem hocam, emekleriniz için dolu dolu teşekkürler. Çok büyük bir emekti.
Sağ olun.
Ben ayrıca yani mazeret bildirmem lazım. Konuşmamı zamanında yetiştiremedim. Konuşmamı hazırlayacağım derken konuşma günümü atlamak zorunda kaldım falan,
Evet,
ama
evet,
anlayışlı davrandı. Çok çok teşekkür ediyorum. Sağ ol hocam.
Yani biz teşekkür ederiz. Katıldın hocam. Teşekkürler. Güzel oldu. Ben de toplantıyı yani başta çok telaşlıydım. Birinci gün korkunç iş yükü vardı. Aynı anda 5-6 tane, 10 tane işi bir arada götürdük. O ilk gün telaşı bizi çok yordu. Ama birinci oturumdan sonra işler kolaylaştı. Yani ondan sonra biz sizlerin, yani artık zaten siz aldınız götürdünüz ya. Çok teşekkürler. Çok hoşça kalın.
Akşamlar hocalarım. Çok çok teşekkürler. Memnun oldum herkesi gördüğüme, tanıdığıma. Çok memnun oldum.
İyi geceler.
İyi geceler, iyi akşamlar hocalarım.
Ekrem hocam, ellerinize sağlık, emeklerinize sağlık. Tüm arkadaşlar adına da bir kez daha teşekkür ediyorum ben de. Selamlar. Keremcan selamlar. Nadir abi selamlar. Elinize sağlık hocam. Şahaneydi. Harika günlerdi.
Hoşça kalın.
İyi bak Deniz.
Sesini yapıyorsan sana da
İyi akşamlar hocam. Teşekkür ederim her şey için. Çok güzeldi. Harikaydı.
good night friends. Eduardo and Chan. Hoşça kalın.